Hi, just checking everything works. Is my mic okay in video?
Hello, good morning. So I would say that we can start with some announcements. First of all, please remember to upload the presentations by midnight of the day before on our folders. Thank you so much. Then coffee break, we have the conference picture, which is gonna be where? Okay, we will know where. Then tonight we have the social dinner. It's gonna be at Mestizo at 7:30. And the restaurant is at the end of the park that you see here on the left. It's Parque Bicentenario. You just go at the end and the restaurant is there. Anything else? No. So I will leave it to Matthias, the first chair of today. And yeah, that's it.
Okay, good morning, everyone, and welcome to today's session. We're going to start off with a online talk by Peter Cicluna on the Nearby Evolved Star Survey, giving us a statistical view of the local evolved stars in the submillimeter. I hope Peter is online.
Yes, I am.
Good.
I hope you can hear me okay.
Excellent. Peter, I'll give you a 5-minute warning through the microphone.
Okay.
And a 1-minute warning. Cool. And you won't see the sign, so should be okay.
Yeah. Okay.
Get going.
Great. Yes, thank you for the chance to speak. I'm really sorry I'm not there in person. I really wanted to be. It would have been great to see everyone after what seems like a very long time. But I'm going to try and whiz through some things about the Nearby Evolved Stars survey today. In case you don't know me, I'm Peter. I'm from the University of Hertfordshire in the UK, but I'm speaking on behalf of a big team of about 80 people who are behind the Nearby Evolved Stars survey. For those of you who haven't seen me give a similar talk before, a little bit about why we're doing this. Well, there's a few big open problems from our perspective. So mass loss, we know, dominates the evolution of evolved stars. But when it happens along the AGB is surprisingly important. Changing, for example, which parts of the nucleosynthesis processes happen or don't, and how, therefore, what the yields can be. And this means that there's an interplay between mass loss and the stellar physics, which feeds into this as well. But the big question that we're really trying to look at is on the scale of our galaxy, how much material is returned by AGB stars, and where does it go? What fraction of that is dust? What does the dust look like? And so on. You may wonder why these are important questions, particularly the last one. Well, there's been a lot of great studies of how much dust is produced in nearby galaxies, particularly with Spitzer. But our own galaxy has always been conspicuously missing from this because it's hard to study the population when you're looking through the disk, because distances are hard to deal with, extinction is a problem. But the trade-off is that we can study sources in detail, individual sources in great detail. So NES is trying to put these two things together to have a big enough sample to do some statistics, but sources where we can actually look at the details too. And so to do that, we've put together a sample of about 852 stars within 3 kiloparsecs, with these sort of selections so that we go further in the most dusty sources so that we kind of have roughly equal statistics across the whole set of, across the range of dust production. They're dust selected, so we're essentially selecting based on how big their infrared excess is in the IRAS bands, and then trying to figure out what's going on in the submillimeter with CO lines and the submillimeter continuum emission. I'm going to keep trying to speed through these first couple of slides, but the big point to make here is that these red dots are sources where NES sources where we've found literature studies, and all the sort of gray dots is the whole NES sample. So we're probing this low dust production rate regime for more or less the first time in a statistical sense. But we're also trying to dramatically improve the statistics at these higher dust production rates by just trying to add more sources in this bigger picture view. It's a big program. We've got over 2,000 hours of observing time. Plus, obviously, AGB stars are stupendously bright, which is wonderful. So there's lots of archival data. If you're looking for things that I don't manage to cover, because it's a big team, there's lots of other team members here. Sundar's talk coming up after mine will also cover some aspects of NES. And he's got a poster, and Alfonso and Ian both have posters which look at some parts of this data set in some way, shape, or form. So I encourage you to go check those out. Okay, now I'm going to go through some of the results that we've produced so far. So it's a lot of data. So I'm just selecting a couple of the newer results that I hope people haven't seen me talk about to death in previous talks. So one of our sort of most recent results was publishing a large chunk of the CO line data in a paper led by Sofia Wallström, published this year. Now there's only CO 2-1 and 3-2 in this data set, and there are 13 CO isotopologues. But even that, with such a large data set, about 400 sources are in this paper. The data is very, very rich. So there's a whole load of results I could pull out, but I'm just going to pull out 2 results from this paper to look at here the dust production rate and mass loss rate of these sources. So those sort of axes in and of themselves are not the interesting thing. What's interesting is that the relationship between these, right, is the gas to dust ratio. And the data are consistent with a non-constant gas to dust ratio. So this is a sublinear relationship where the mass loss rate, the gas mass loss rate, increases slower than the dust mass loss rate. So we're seeing hints of higher condensation efficiency as we go to higher mass loss rates. But this also means that actually as you increase the dust production rate, you're getting, if the fraction of the material is dust, you're able to extract more radiative momentum and transfer that to the wind. So when we saw this, we were starting to wonder, where does this momentum go? Could it be going into reaching higher outflow velocities rather than higher mass loss rates, right? So you've got the same amount of momentum, but you're putting part of it into the V rather than the M term. And when we looked at the relationship between mass loss rate and expansion velocity, that does seem to be consistent with the results. And I was also very pleasantly surprised to see MLE's results yesterday, which visually at least look very similar to this plot on the right, showing this sort of same overall trend, which we've just modeled as sort of a broken power law, but is probably something a little more interesting and subtle than that. However, bear in mind, these are all dust selected sources. So if there's some sort of weird systematics that we've injected by doing that, yeah, that's a caveat to beware of there that we hope to dig into more in some future papers. Now that's just sort of the point source component, but we've got extended emission in a lot of these, and I'll just skim over this very quickly to get to something else in a minute. But when we started looking at these, we immediately saw that lots of these nearby sources with sort of moderate to high dust production rates are extended on sort of scales of half an arc minute or so. And we see similar things in other transitions out to CO 1 to 0, observed with the Nobuyama 45 meter or the IRAM 30 meter. But the Nobuyama data are particularly funky because we also see some extended 13 CO. Now I think in these plots, the black line is the 12 CO and the gray dashed line is the 13 CO. And I don't remember what I should have checked what all of these lines are ahead of time. But we see sort of clear, significant extension in the different traces. And to see this at higher resolution, I suggest you go check out Alfonso's poster, which I believe is number 23. Okay, that was all about gas. I'm a dust person personally, so I'm going to move on to my favorite part of the talk. So when we started looking at the Scuba 2 submillimeter observations that we got from this data set, we started to see something rather odd. So the sources were all selected based on the grid of red supergiant and AGB model spectra, or grams. And so when we compare the fluxes that we were observing, which is, I didn't put the fluxes themselves on this slide, unfortunately. I should remember to do that. The fluxes we were observing and compared those to what's predicted in the grams models, we see that the submillimeter flux that we've observed is typically a factor of sort of 10-ish, or 3 to 30, 3 to 10-ish higher than what we predicted. In and of itself, that's not super surprising because grams is tuned for the mid-IR. So there could be, a reservoir of cold dust that's not included in the grams models. But if you transform these to a spectral index, it gets a little weirder. So I'm plotting over here alpha, which is in the limit, in the Rayleigh-Jeans limit. This is beta plus 2. So this is the sort of observed spectral index, and then beta is the spectral slope of the opacities that are implied by that. Right? So -2 is therefore the behavior of a black body, whereas this dotted line here is the what you might expect for drain type interstellar dust. So there's quite a significant difference here, right? That this dust is completely different to the interstellar dust and not consistent with what you would expect for most sort of grain analogs for an AGB star. Now, we could try and explain this with coal dust, but this would imply a truly enormous dust reservoir. And it could instead be that we simply don't understand the dust properties very well. Similar to Matthias's talk yesterday, I expect that maybe using some data based on Karine Demique's lab data might get closer to this. So we're continuing to try and improve the Scuba 2 data reduction to try and fix this or understand where it's coming from for sure. That is, however, pretty hard. So we thought we would take a slightly different approach to explore this in a bit more detail.
You've got 1 minute.
Oh, wow. I'm talking way too slow. Okay. I'll try and get to some cool results and then bring it to an end. So we tried stacking Planck data and discovered that these things have huge envelopes on average when you stack them. If you stack basically a large fraction of the nest sources, this is 350 micron, you can see this stack has an envelope size which is tens of parsecs. Now, we don't know for sure that that's really all of the AGBs, like all that dust is coming from the AGB star, but it is consistent with essentially the entire lifetime thermally pulsating AGB lifetime dust production. And these, if you again measure an alpha for these, the slope evolves significantly with radius, tending towards the background sort of Milky Way value. And seeing as I just got a 1 minute warning a minute ago, I'll just comment on this slide and then skip to the end. We also see a substantial difference in these indices between the oxygen-rich and carbon-rich stars. And now I will skip over the potential problems I wanted to highlight and bring the talk to an end and say thank you again. And I would love to take any questions you have.
Thanks a lot, Peter, for that great talk. And my apologies for not giving you the 5 minute warning. I didn't know how to interrupt you. You were in such a good flow. But we have time for a couple of questions. Angela.
So you said that the dust doesn't behave how you would expect for an AGB star. I would say that we have no idea what's going on with the dust in AGB stars. But one of the questions I have is, what data are you using? You mentioned Karine Demique's work, which absolutely we should look at. But I'm just curious as to what optical constants are currently being used, partly in order to maybe help guide towards what might help with those spectral index issues.
Right. Yes. So grams uses, I don't remember exactly which optical constants grams uses off the top of my head. I will check in with Sundar and get back to you. But yes, we would like to shift to using things like Korean's data and stuff like that in future.
Okay, we have one more question here.
Yes, I couldn't read very well. The question is, what is the maximum mass loss rate at the end of the evolution of AGB stars?
Are you talking about this plot?
The first one, actually. The rate in solar masses per year.
Yeah, so the highest we're detecting so far is several times 10 to the minus 5 solar masses per year in mass loss rate.
Oh, several times. Okay. That can reach to 10 to the minus 4 solar masses?
I mean, I think that's been claimed in previous previous observations. How much of an impact, the geometry of the envelope has, whether that's an artifact of interpreting it with a spherical envelope when it's not, I don't know. So there's some systematic uncertainties there to be dealt with. But yes, getting to that order is maybe within the bounds of possibility.
Okay, thank you.
Thank you. We're going to have to wrap it up here. But if you have more questions for Peter, don't hesitate to ask them on the Slack, of course. And also, please remember to submit questions on the Slack for the discussion session later today. And also for the previous talks, of course, the Slack is a good place to discuss any further questions. But for the next talk, we'll have Sundar Srinivasan talk about reconstructing AGB envelopes by bridging observations across wavelengths. And this is an in-person talk, so I'll be better at giving you the 5-minute warning.
Can everyone hear me? Okay, good. Okay, thank you very much to the organizers for allowing me to talk a little bit more about NES. So I'll show you some other results that hopefully Peter did not show you. Yes, so this is again a tiny thing we started out a couple of years ago, thinking that now we have all these data that we'd like to kind of combine together and get better constraints on parameters. So disclaimer, of course, none of this is going to be new to you. There have already been some great talks where people are doing very, very detailed modeling and various different aspects of it, so it's not going to be new to you. The goal was just to kind of demonstrate the range of data that we have, the kind of things we have, and just some of the preliminary modeling we've been doing, and just solicit feedback. So yeah, it's not going to be surprising. Okay, so I'll show you, quickly scroll through some of the results that we have. So NES is, again, just to remind you, it has about just about under 800 evolved stars in it, and it samples, as Peter showed, not just the evolved population of sources, but also the early phases of mass loss. It is a very complex data set once you combine with the existing, the archival observations with what we have. And there's quite a few papers, and Peter mentioned some of them, that have, 3 of them up there these 2 were published this year, and there are a couple more in prep. There's another one that's, I think, submitted as well, the NRO paper, which I forgot to add here. So there's a broad range in wavelength, the length scales probed by these wavelengths, and in the circumstellar shell as well. So this is well suited for a unified modeling scheme. So this is a result that Peter luckily did not show. One of the things we see in SOFIA's JCMT heterodyne data is, again, something that has been seen before. Our population has these CO profiles, the shapes of these profiles. So most of them are consistent with a constant velocity, spherically symmetric soft parabola profile, but we do have a few % of sources that either have multiple components, most of them are oxygen-rich, low mass loss rate sources, or we have sources that have asymmetric winds as well. And again, it's known in the literature, the reasons for things to be non-soft parabola profiles. So again, well documented. This is ALMA ACA data, that a paper that Alfonso is working on, that he has a poster about a different aspect of it. But we had an undergrad student who looked at a similar analysis to what Sophia did for the JCMT data. So this is a southern sample, so it's a good complement to the JCMT data. The results that we get are very similar to what Peter was talking about regarding, so the mass loss rate versus the velocities, that's the x-axis has the velocity there, has this sort of tapering off effect, which is similar to what Emily showed in her paper as well, talk as well, and also the Death Star poster outside by Miura also has a similar kind of tapering effect. Okay, we have a couple of images from the LMT as well in a pilot study, and it's nice to have the LMT because, again, the beam size is complementary to what the JCMT has, and this is 1 to 0. So we do have images. We have not yet had the time to analyze them, but that's the UANT image over there on the right, and on the left, that's W Hydra. We have distances for these sources from Ian's paper, which he has compiled using various techniques, and compiled SEDs as well. The good thing is now these SEDs are extremely well sampled. So this is just, this I think is UANT, and this is going from about, this is the optical through just the mid-infrared, this one. So this is a bad example to show for something that has, we do have for some sources information up to the radio wavelengths as well. So it's, I think it's a total of 180-ish bands. It's a gigantic file, really annoying to read. So yeah, we have a huge amount of data. Again, this is something everybody knows, and there's just not enough time to look through all of it. Oops, time, right. I completely forgot about time, yes. We also have time series data in this, that we can incorporate. So one of my master's students, this is exactly what he did. He wrote code to automatically query various archives of light curves and obtained for 700 sources, which is a huge fraction of our sample. He obtained almost 7,000 light curves over, I think, 28 bands or so from the optical to the mid-infrared. So this set of light curves that are not very visible on the giant screen here are for teleporous. So that's the ASAS light curve on the left. The top right is all the Gaia bands, and the bottom right is the Kobe Derby bands. So for this one, we have data up to about 5 micron or so. Peter's working on a code that uses Gaussian processes to do multi-wavelength inference on this. So this is just an example of the fits for a single source. And this is something I'm very excited about because I haven't worked very much on variability, and this allows us to do many things. One of the things I'm very interested in is figuring out phase lag. And this is something we've done before to see if, if there's how does information travel from the optical through the infrared, and therefore from near the surface of the star through the dust shell. That would be very interesting to know. So this is something we're working on. There are also, this database just, I think, is relatively new. So I was very excited about this because they have a minimum of 100 epochs or so for sources in their sample. And I looked, and we have about a very small number of AGB stars in there that we can actually look at. So this would be, thank you, this would be useful for tracking changes in molecular absorption close to the surface, which would let us know a little bit more about, we can constrain some of the pulsational properties and perhaps the variation of the stellar parameters as well using this. And finally, there's near-infrared spectra as well. Now, this is not necessarily a time series yet, but we do have an overlap, and getting time series spectra of AGB stars at this resolution, again, would be amazing, because to get stellar parameters out, to get metallicities out, this would be an amazing thing to do. Okay, in the last few minutes that I have, I'm going to tell you a little bit about some of the preliminary modeling that we've started working on. So I just mentioned, there we go. I just mentioned how you can get stellar parameters out of near-infrared molecular absorption features. One of the things that is typically ignored is, or typically not treated well, is the fact that AGB stars, dusty AGB stars, they do extinguish molecular features. So what you're seeing here in this figure, the blue curve is a dust-free AGB star from the LMC. What we did is the black curve here is a dusty AGB star. You can see that a lot of the CO features basically get either extinguished or they're basically missing or extremely extinguished. And we can simulate this by just adding a 400K black body to this blue curve here. So this is the kind of stuff that is not really systematically done when deriving stellar parameters, because I guess typically people are working with dust-free sources in this regime. So this is something that we want to do simultaneously. Mid-infrared features, it's not so bad. Dust emission should, in principle, extinguish molecular features, but it has been known for a while, since before Spitzer, that there are molecular features that, in lower metallicity environments especially, the dustier stars have deeper molecular features. And so we think this is a circumstellar gas, but typical analyses of this sort of stuff involves a slab model. And the problem is that you cannot constrain the location of the slab model, which is important to derive the actual gas mass loss rate. So that is something that we would like to account for as well. There are some new techniques that we've been using, so machine learning and neural posterior estimation. Neural posterior estimation is basically where, come to my poster and tell you more about it. But this is an example where we had, so Greg Sloan published 3 spectra for LMC stars, MIRI spectra, and they had these nice molecular features here. What we did is, I was like, oh, let's do a toy model and see if we can very quickly get some parameters out of this. So I took the grams dust models, and for every grams model and every column density that we had in this acetylene model grid, we just produced a new model and then trained a neural network on that grid to try and fit these exact spectra. I was pleasantly surprised. It was extremely rudimentary, but I was pleasantly surprised at how good the fit is, especially for the dustiest object here. So this allows us to get a good initial guess on the parameters to go and do more detailed modeling. We can also do SED fits. This is what the poster is about, so come check that out. And so where this is headed is that we would like to simultaneously model the gas and the dust. As a beginning, as an initial point, I've taken the grams models that have dust temperatures from the grams models and use that as input to gas models with RADMC3D to try and simulate the lowest J, the lowest J transitions. Because the 12 CO is optically thick, you can't directly compare these results with the data. This is what Sophia found, and I think a lot of other people are finding as well. But we can, for the sources where we have relatively reliable 13 CO emission, we can directly compare the predictions to the observations here with the NEST data. That's just a starting point. The idea would be to eventually take this method and integrate it, to integrate near-infrared spectra into it as well, for which, of course, the neural posterior estimation gives us good initial guesses. So it's a gigantic parameter space, but the idea with all of these quick and dirty techniques is we're trying to reduce the volume through which we have to traverse in order for this to happen. So yes, NEST is a great sample, a huge sample. It samples a large range of mass loss rates, some of which has not been statistically probed before, as Peter said. We don't have enough people and not enough time, but this is always the problem. This was all very preliminary, so any feedback you have, I'd be very thankful. Thank you.
Thank you, Sundar. Any questions? Lynn, please.
Hi, Sundar. Thanks for the talk. I was wondering, when you have been showing now the results of your neural network, predictions towards the three spectra of Greg Sloan. How does the posterior distribution looks like, or with other words, how degenerate or non-degenerate are the model parameters?
Good question. It is so the way this grid that Jan Kami generated, the way that was done is the coverage was not very refined. So it does end up being relatively degenerate, but not as bad as when we did the simple fits back in 2017 or so. So there is still degeneracy in there. So luckily in this case, we only vary two parameters. I think the temperature and the column density of the gas. But I think in principle, there are other things that, yeah, yes. So there is definitely, we still have degeneracy. Yeah.
Yes, one more question here.
Hi, I'm Max from Macquarie University. Thank you for a very informative talk, Sundar. I had a small question about the luminosity derivation that you were talking about. Could you please go into more details on how you account for the reddening, the interstellar and, if applicable, circumstellar?
Yes. So that is in Ian's paper. I don't remember it right now, but I can bring it up for you at a coffee break or something we can talk about.
Sure. Thank you.
Okay, great. Then let's thanks Sundar one more time. And next we have an invited talk by Martha Boyer, telling us about AGB populations in the infrared era and HST and WST results. Thanks, Martha.
Okay, just waiting for slides. Well, thank you for having me. I am really glad to be at an AGB meeting again. It's been a long time and it's nice to see everybody, and I'm learning a lot this week. So this is really great that we were able to do this. So I'm going to talk about AGB populations in the infrared era. I'm going to focus on work that's been done with, yeah?
The microphone closer to your mouth.
Okay, sorry. All right, I'm going to talk about AGB populations, mostly with HST and JWST. And the motivation here is that the extragalactic community is very interested in looking at galaxies that are farther and farther and farther away. And the AGB stars in the near infrared are some of the brightest things in galaxies. And so they would really like to use the AGB stars to derive galaxy properties like distances, star formation histories, etc. And so AGB stars are kind of having a moment right now because we have all of these near-infrared telescopes and AGB stars are in all of the data. And so there have been a few attempts to try to see what we can do with AGB stars. And one of them, Martin already talked about the very first talk this week about the JAGB distance method. And so I'm not going to go into a lot of detail here, but the idea is that the carbon star branch, which is here, if you take this region in the blue, that it has a sort of constant flux in the J band, so about 1 micron. And you can use that as a standard candle. And this has been of great interest to the cosmologists who are trying to constrain H0. And you can see the Hubble tension here, where the CMB measurements are over here, and then everything else from TRGB and Cepheids, et cetera, are all over here. The JAGB measurements are down here, and Martin already mentioned this discrepancy between the two different groups. But, you know, forget about H0 for a second. This technique is just a really potentially powerful technique just for getting distances, period, whether you're interested in H0 or not. But there are a couple of potential issues here. And this is illustrated really well by this plot from Giada Pastorelli. And these are models, AGB models. And this is metallicity versus the measurement that you would get if you were looking at just carbon stars or just M stars or everything together. And they're in these models, they're, first of all, this doesn't look constant at all, right? There's this range with metallicity, and it gets much worse up here at high metallicity because now you have a lot of M stars. And the M stars, if you looked at just those, you would skew the measurements down. And if you break it down by age, the luminosity function of the M stars seems to change quite a lot. So I think that it's a little bit dangerous at the moment to be using JAGB, the JAGB method, but I think that this can be calibrated, and this could become a very powerful method. Another strategy, which Martin also mentioned, is looking at unresolved populations where you can see the signatures of AGB stars. And I just wanted to, so Martin already talked a lot about this, so I just wanted to point out this one quote though from Bevacqua. This is their spectrum, and they have all of these different near-infrared spectral features that they're looking at, and they noted that the analysis of several of these indices show that the models just can't reproduce the observations. So there's definitely, again, same with JAGB method, there are some concerns here regarding the models. And then there is a lot of effort trying to look at how well we can derive star formation histories with AGB stars. And this was proposed back in the 90s or something, that AGB stars could be a powerful tool for this. But the limitation has always been the quality of the stellar evolution models. And so not very many people have attempted it over the years, but there have been a few brave souls that have given it a try. And I'm just showing a couple of examples here. This one's from Melbourne et al., where they fit the optical color magnitude diagram down to the red clump, which is sort of a standard for getting a star formation history. And then they compared it to the infrared, where they have pretty much only AGB stars. And they got a very different answer. So here, at least in 2010, it didn't look like the AGB stars were ready yet. And then Javadi et al. Tried something totally different. They looked at variable stars and then used the pulsation to try to estimate the masses of the stars, and then translated this mass function into a star formation history. And this was an interesting strategy, and the star formation rate that they have is about right when you compare it to the main sequence turnoff measurements, but these peaks are not really reproduced in those measurements, so it's not really clear how well this strategy is working yet. And then another strategy is to just look at the ratio of the AGB stars in blue to the red giant branch stars in red to use as a constraint on when the most recent epoch of star formation occurred. And this is particularly interesting to the people who are looking at stellar mergers and things like that, or galaxy mergers. And what they found is, so there's a few different studies that have done this, but this paper looked at a bunch of galaxies and measured the ratio of AGB to RGB stars as a function of this parameter is the epoch of the most recent star formation. And they get a pretty good agreement with the models in the data. So it looks like this is potentially a pretty powerful technique. And then just last year, Abigail Lee tried to do another star formation history by fitting the color magnitude diagram, which is similar to what Jason Melbourne had done in 2010. And here she really restricted herself to only the AGB stars up here in the color magnitude diagram and only fit those, and got this black line. This is this cumulative star formation history. And it has pretty decent agreement with measurements of a deeper fitting of the main sequence turnoff. The red and blue lines are sort of the ones you should be looking at. And it looks pretty good, but there are a couple of regions where the stellar mass or the star formation rate is a little too high, like here, and maybe it's a little bit low over here. So it looks okay, but one of the things that was sort of puzzling to me when I saw this paper is that they decided to do this in M31. And M31 is a metal-rich galaxy. It's solar metallicity or even supersolar. And that's the place where the stellar evolution models might actually be the least constrained. So, so I think that, considering that they're getting such a good answer, even with sort of unconstrained models, is, I think, really promising that the models are, actually improving a lot over the years and maybe getting there. So, all of these things that I've mentioned, as you've probably heard this theme, that they all depend on the models, and there are these model uncertainties that we have to deal with. And so I'm going to talk about the work that's been done with Hubble to try to constrain the AGB stellar evolution models. But before I talk about Hubble, I want to just remind you what has been done in the Magellanic Clouds. So, of course, in the Magellanic Clouds, we have a ton of data, right? We've got optical, we've got 2MASS, we've got Spitzer, mid-infrared, we've got pulsation, we've got basically anything you could want in the Magellanic Clouds. So these are, of course, a place where a lot of people go to try to constrain the AGB models. And that was done by Giada Pastorelli a few years back, and what they did was they took the VMC survey, the very deep near-infrared data of the LMC and SMC to get a star formation history, which is down here. And then they used this star formation history to simulate the galaxy. and then compared that to the data. And the nice thing about this is that they could separate all the different stellar types and measure, compare the luminosity functions to the data of all the different kinds of stellar types. And they got a really nice calibration by doing this. It works very well. But it doesn't cover the whole parameter space, right? So this is just a cartoon of the initial mass of an AGB star versus metallicity. And I've put, or Ian McDonald actually made this, not me, put Amanda's models in the background just to show approximately where the carbon stars are versus the oxygen-rich stars. And the LMC and the SMC are kind of right in the middle, which is great, but there's all of this other space that we'd like to cover. And that is where HST comes in, because HST can reach galaxies out to 1520 megaparsecs in the near infrared, and you can constrain this whole parameter space. And that is what several programs have been doing. The Angst survey and the Lovett survey are focused over here on the low metallicity end, and some surveys of M31 and M33 are over here at the high metallicity end. So I'm going to talk about all of these surveys. And I'll start with Angst. So this is data from Phil Rosenfield's papers where they have something like 15 or 20 galaxies, I think. This is some of them here. And this is the data that they have where they've got wideband filters in Hubble, and they pick out the AGB stars here, fit the luminosity functions similar to what Jada did in the Magellanic Clouds. And with this program, they were able to make a really great improvement to the models. So this is the previous models up here. It's the comparison of the observed AGB stars to the modeled AGB stars, to the number of stars. And the previous models were up here, and the new models were down here with really good agreement between the observed and the predicted numbers. So that was really promising. But one of the issues here is that with these filters, these Hubble wide filters, you can't separate the carbon stars and the M stars. They sit right on top of each other. And this proved to be, being able to separate these populations proved to be really important in the Magellanic Clouds. So there you have two mass where you can get this nice separation between the carbon stars and the M stars. And this plot from Jada shows that, so this is all the models that they had tried to fit to the data in the Magellanic Clouds. And this is the chi-squared. And you can see that in some cases, the carbon stars fit the models really well, but the M stars don't. And then there's others where the opposite is true, where the M stars fit and the carbon stars don't. And so this allowed her to figure out which models fit both, right? There's sort of options that they had settled on. And and this really improved the models a lot and gave some really high quality calibrations. So what do you do if you have Hubble? And the answer is that you actually go to narrower filters. So the wide filters are down here. And these are a couple of AGB spectra, and you can see that the narrower filters sample these features really well. So there's a water feature in M stars, and then CN and C2 in carbon stars. And when you plot these filters against each other, you get this really nice separation. The oxygen-rich stars go this way, carbon stars go this way, and you can now do the same kind of work that Jada was doing in the Magellanic Clouds. And that's exactly what she is doing. She's continuing this work in using the Lovett program. And this program looked at all the Angst galaxies and this time used those narrower filters with Hubble. And it's the same exact process where we have now optical data and deep wide field or wideband infrared data. And you can use these to get your star formation history. And then you can use that to simulate the galaxy and then compare that to this separation of oxygen-rich stars and carbon stars in the data. And just to give you sort of the preliminary results here, this is 4 of the galaxies. There's about 20 of them total. And this is comparisons between the model and the data. And they actually look pretty good. These are the current models. These are not the newly calibrated models. And they look decent, but there are some issues, like this one in particular, where there's way more M stars in the prediction than there is in the data. So, so there's definitely some work to be done here. At the high metallicity end, there have been observations of M31 and M33. In 2019, we published some of the M31 data. The M33 stuff is still in prep. But what was really interesting there is that when you look at the relationship between the carbon and the oxygen-rich stars with metallicity, you get this relationship where you have fewer and fewer carbon stars as you go to high metallicity. And that's been known for a long time. But in M31, it drops off really dramatically. And this was not necessarily predicted in the models, and it was a little bit of a surprise. But then Amanda Karakis came along and did some modeling and found that what might be happening here is that M31 might have an enhanced helium abundance. And so these are some of her models showing the C/O ratio as a function of initial mass. And with a little bit of helium, you really do narrow the mass range that you get for a carbon star. And if you add a little bit more, you can make the carbon stars basically disappear. And so, so M31 is maybe somewhere in the middle there. We never found a field that had 0 carbon stars, but we found some that only had a handful. All right, and the other nice thing about Hubble and M31 is that we were able to pick out stellar clusters because Hubble can actually resolve them. So here's just a couple of examples. And about 100 of them in M31 have AGB stars. And clusters are super useful for calibrating models because now they're clusters, so we can get their ages and their metallicities. And this is just a histogram of the ones that include AGB stars. And then you can do sort of similar work to what was done in the Magellanic Cloud with those clusters. This is constraining the lifetimes of the carbon stars in the Magellanic Cloud clusters. And now we have the ability to do this in M31. But what we would really like to do is move this kind of work to JWST, because JWST has a higher angular resolution in the near infrared and is more sensitive, so you can reach even more environments. And in particularly clusters, you can go much further than M31, and you can get nice high resolution images of clusters. And so I'm just going to talk about how you classify AGB stars with JWST for a second. This is the standard 2-mass diagram with the carbon stars and the M stars separated, and this is sort of the equivalent in JWST filters. And Flavia showed, I don't know if she showed this exact plot, but she showed something similar. And you get the same idea. The carbon stars are over here, and the oxygen-rich stars are over here, and it looks really nice. But I do want to urge a little bit of caution, because one of the lessons that we learned in M31 is that when you select carbon stars this way in broadband near-infrared filters, you can actually get contamination from oxygen-rich stars. So all these green points, these were identified as carbon stars by Davidge in 2005 by using 2-mass filters, basically. And but when we looked with Hubble, they all turned out to be oxygen-rich stars. And what was making them red in the broadband filters is deep water absorption. And so if you have a high metallicity galaxy, you can actually have a lot of oxygen-rich stars over here. So depending on what you're trying to do, you have to be a little bit careful here. So one of the options with JWST is to try to use different filter combinations. And some of them are very promising. This one was a study in the Galaxy WLM where we had Hubble classifications that we could compare to. And in these filters, you get a really nice separation of the carbon stars and the M stars. And what's nice about this is that as you go to higher metallicity, now here's a simulation, but as you go to higher metallicity, this separation becomes much cleaner. So here it's a little bit dicey. If you didn't have the Hubble data to help you, you wouldn't know maybe exactly where to draw that line. But at high metallicity, it's very clear. So if you can't do it with these filters at high metallicity, you can maybe do it with these filters. All right, so if I'm going to talk about JWST, I have to talk about dust because, of course, and I just came from a dust conference last week, so that's what's on my mind right now. So I'm going to sort of shift gears a little bit and talk about dust. But before I get to JWST, I'm going to talk about, just sort of remind you where we were in the Magellanic Clouds doing similar kind of work. So of course, this is again the SAGE data from Spitzer of the SMC, and we also have the LMC. And of course, here you can just pick out the AGB stars. They're the brightest things. They're really easy to identify. And because Spitzer was so sensitive, it could get all the way from 3.5 or 3.6 microns to 24 microns, and you could constrain the SEDs really well and get nice fits to produce dust production rates. And this was done by a whole bunch of people. I've listed some of the surface down here, including Cinder. And what you can do then is then add up the whole population. So you know how much dust the carbon stars are making, how much dust the oxygen-rich stars are making. You can compare it to the red supergiants. And that's really great. This is it provides a really nice constraint to the total dust budget of a galaxy. And you can then compare these numbers to what's in the ISM. But if you wanted to go past the Magellanic Clouds it got a little bit dicier. So this survey, we went to sort of the edge of the local group here and looking at a whole bunch of dwarf galaxies. And it's a lot harder to identify the AGB stars when you go with Spitzer, when you go out farther. And part of that is because we only have 3.6 and 4.5 microns. And part of that is because the resolution means that it's hard to separate them from unresolved background galaxies. And so we did our best. We got some of them. We didn't get a complete sample of the AGB stars. But what was interesting here is that we see that even in these very metal-poor galaxies, we're making just as much dust as we are in stars in the LMC. So, so clearly, AGB stars are very efficient dust producers. But we didn't really know anything else. We didn't know if these were carbon stars. We didn't know if they were oxygen-rich stars. But Flavia went and tried to model this data. This is the Spitzer data. She matched it to some ground-based near-infrared data, and then simulated the galaxy and got a really nice match. This is the luminosity function, and then could use the, once there was a good match, you could use the models to try to infer the total dust budget, which is great. It provided some really nice constraints, and also there's some work by Gavetti, and he's giving a talk later, I think, on similar type of work. And but what we really like is longer wavelength data, where we can actually constrain the data and not just the models, right? So to do that, you have to use Webb, and Webb is kind of perfect for this. It's like they made it for us, really. So this is a SED of AGB stars, and the NIRCam coverage is here, and the MIRI coverage is here, so we cover the whole SED. And we have a bazillion filters. So, pick your molecular feature or your dust feature, and it's going to be sampled by one of these filters, right? So you can get really nice sampling of SEDs, and you can really learn a lot about the stars with JWST. And there have been several studies that have been trying to do this. These are just some examples. This is NGC 6822 from Nally et al. And in this, you can see just how gorgeous this data is. It goes very, very deep. And you can see they've identified the carbon stars and the oxygen-rich stars, and then they've moved into MIRI to try to figure out how much dust they're making. And unfortunately, I can't show you their dust budgets yet. They're still working on the SED fitting, but stay tuned for that. And then another program is in Sextans A, and Elizabeth Tarantino is going to give a talk about this later, so I won't say much about it. And also check out Tom Henry's poster. But we found a lot of very dusty AGB stars in Sextans A. But these are just the sort of dedicated AGB programs with JWST. There's also just a ton of data in the archive. And just to give you sort of a taste of that, this is a galaxy from, I think, the FEAST program. It's at 5 megaparsecs. It's about LMC metallicity or so. And when Elizabeth Tarantino did just sort of a quick and dirty photometry run on this with the MIRI data, the AGB stars pop right out. And if you did this more carefully, it would be much cleaner, of course. But it's very easy to identify the dusty AGB stars out to 5 megaparsecs. And then if you go to this galaxy, this is from the FANGS survey. It's at 11 megaparsecs. It's supersolar metallicity. And you can see it has just thousands of AGB stars to work with. And they also have MIRI data, so you can constrain the SEDs. And then this galaxy is at 18, this is 16818, it's at 18.2 megaparsecs at only 3% solar metallicity. And even there, with NIRCam and with MIRI, you can identify about 20 to 25 dusty AGB stars. So also see the poster by Tom Henry to learn more about that program. And so that means, we now have this situation where we just have tons of AGB information in galaxies. And this is a paper that just came out about a month ago from Hassani et al. And these are all the FANGS galaxies. There's something like 20 of them. And they've classified all the stars. Most of the objects that they're seeing at 10 and 20 microns are star-forming regions. But then the carbon stars are red here, and the oxygen-rich stars are these lighter blue boxes. And you can see just the diversity of the galaxies here. There are some that have just a ton of AGB stars, and some that maybe not so much, or the star formation sort of just wipes it out. But they're not really looking at the dust produced by the AGB stars yet, but they did make a plot of the, this is the flux at 21 microns and at 10 microns, I believe. And at 21 microns, the oxygen-rich stars aren't really contributing at all. The carbon stars are though, and they are sort of producing about as much flux as the star-forming regions. And then at 10 microns, the oxygen-rich stars sort of come into play and are becoming important to the total flux. So we're entering this era where we had dust production measurements from AGB stars in 2 or 3 galaxies to having it in dozens of galaxies, right? And so I think we're moving to a situation where we can really maybe start to answer some of these questions that we have about, for example, high redshift dust. So this is a plot from Wittstock et al. Showing this 2175 angstrom bump, suggesting that there's dust at, I think this was redshift 8. And it's really unclear, are AGB stars contributing at this redshift? And I think the picture that most extragalactic astronomers have in their mind is something like this. This is from a review paper by Schneider and Molino, showing that the AGB stars are not really contributing, the metal poor AGB stars are not really contributing until you get to pretty low redshift, maybe 4 or 5, compared to supernova. But there's really, constraints on this plot. This is all models. And so with all of these galaxies in the JWST archive, we're really going to be able to start, putting some data points down on this. And that's just what's in the archive today, right? There's already something like, 30 galaxies in the archive, and there's more programs coming. Like I think Flavia mentioned, there's this program in the Virgo cluster that's going to get even more galaxies. And that's it. So I'll just stop with my summary here. The AGB stars are becoming these popular diagnostic tools with JWST and with Webb. HST is doing a great job in constraining the models. And with JWST, we're also going to be able to do something similar where we can separate these stars. And we are now moving to an era where we're going to have just more data than we know what to do with. And so that's it. Thank you very much.
Thank you, Martha, and talk about why galaxies should care about AGB stars. I think that really made the point very nicely. Any questions? Please.
Hi, Martha. Thank you for that really interesting talk and fantastic results. I have 2 questions. My first one is, how do you deal with contamination from young stars? But you also did say that, they contribute to quite a lot of the 21 micron flux. So how do you deal with that? Because many of the plots you had, I think they overlap in terms of the dust.
Yeah, so one of the nice things about Webb and Hubble is that you also get the optical data. So a lot of it you can just look at the colors or look at the shapes of the SEDs and it's pretty clear what you're looking at. It gets a little bit dicier when you have like an embedded object where it's sometimes those SEDs look very similar to AGB stars. And I think it boils down to just the shape of the SED because we have enough data where we can actually do some fits and some modeling. And so I think it's looking at the shape of the SED compared to some of the models for like YSO stars and things like that.
Okay. May I ask my second question very quickly? Thank you. So my second question is, when you talk about the 21 micron flux, are you referring to the 21 micron feature? No. Okay, just make
the total flux.
So the total flux, that's there. Okay.
Yeah, it's a broad filter.
So. Right. Okay. Thank you.
Mm-hmm.
Thanks. Sophie, you had a question?
Yes, Sophie Vanek from Brussels. How do we deal with the contamination with extrinsic stars? So stars polluted in carbon by a binary companion, because from the color diagram, there will be difficult to disentangle. Do you use a magnitude cut?
Yeah, I mean, the only magnitude cut that people usually use is the tip of the red giant branch. So if it's fainter than that, it'll get excluded. But otherwise, there's no way to do it with this data that I know of. We kind of just pretend they don't exist and go from there. I mean, it's all about statistics, which is why it's so nice that we can now go to these very distant galaxies and get more galaxies and more stars, and we can start to not worry so much about contamination in an individual galaxy, right? Because we have statistics of many. Right.
Okay, Hans, you had a question.
Hans Seneca from Universidad Autónoma de Chile. About the production of dust at low metallicity. You mentioned the implication for cosmology and for high redshift universe, but is there a prediction of the dust to gas ratio as a function of metallicity? Because it seems to go down. Overall, although the AGB stars that exist at low metallicity, they produce a lot of dust, but overall, I think the dust in a galaxy goes down with the metallicity of the gas of that galaxy.
Yeah, I mean, in the ISM, that's definitely true. And I think that's true for oxygen-rich AGB stars because they depend on the pre-existing metals to make their dust. But carbon stars, of course, they can make their own carbon and they just make a ton of dust. Just as much dust at 1% solar metallicity as you get at much higher metallicity. So it just depends on which stars you're looking at.
Yeah, but my question is has there been a prediction for the dust to gas ratio for lower metallicity as we have in the early universe?
In the stars, I mean, there are predictions in the models. I don't know that we've been able to measure that, right? Because we just don't until we just didn't have the data. So people are looking into that.
And Theo had one question also. You can use this one.
Hi, thanks for the very nice talk. I was wondering, when you retrieve the star formation rates from the AGB stars, what is the main uncertainty there? Is it just the AGB duration, or are there other things that are also?
Yeah, I mean, it's the main uncertainties in the models are things like dredge up, lifetimes, mass loss, all of these things all play a role in that uncertainty, and that's why it's been a little bit dicey to try to use them, right? Because the models just haven't been at the calibration level that we need them to be until pretty recently. So, but I think some of those uncertainties with all this data we can try to constrain. So.
Okay, great. Let's thank Martha one more time. Sorry, Lane. One more time. So our next speaker is Tanya Kushwaha, who will be talking about classifying carbon-rich and oxygen-rich sources in the Milky Way with Gaia Data Release 3.
Hello, I'm presenting my talk online.
Do we have our speaker somewhere? Online, okay, good.
Yes.
I didn't know.
Sorry, even after
So our next talk is
I
online.
couldn't come even after spending 2 days at the airport for some reason. So really sorry about that. I'll just share my screen now.
Is our next talk online?
Can you see my screen?
There we go.
Hello? Can you see my screen?
Yes.
Oh, okay, perfect. Hello, everyone. My name is Tanya Kushwaha, and I'm from Cardiff University, working with Mikako Matsura and Timothy Davis. I was supposed to come, but I couldn't come because of some issues at the airport. So the title of my talk was Unveiling Milky Way's AGB stars and their classification in Gaia DR3 data. However, now the title of my talk is Unveiling the Milky Way structure with AGB stars, and I'll show you some of the results that we got in the past few months. So the content of my talk is, I'll begin with a quick introduction. I'll talk about the classification that we did using machine learning of carbon-rich and oxygen-rich AGB stars. Then I'll give you some details about the spatial distributions of carbon-rich and oxygen-rich stars and AGB stars as tracers of galactic warp. Then I'll conclude my talk with the few main points. So here I'll give you a brief introduction. I'm pretty sure we all know about what AGB stars are. AGB stars trace intermediate age stellar populations. They have two main chemical types, carbon-rich and oxygen-rich, and we basically wanted to classify the two types and study galactic structure and stellar population gradients with the two populations. So before I started my PhD, Gaia DR3 was launched, and it has 1.5 billion stars with precise astrometry and photometry. It provided low resolution spectra for 220 million stars. So we saw it a very good opportunity to use machine learning on this data, as it provides scalable, efficient, and robust classification. And we wanted to expand the catalogs of carbon-rich and oxygen-rich AGB stars using multidimensional features, including both photometry and spectroscopy. So in this machine learning classification, we did a two-step method. We first applied a similarity analysis to limit the number of sources that we were giving for classification in classification algorithm. So in similarity analysis, we basically compared the features of an unknown source from Gaia DR3 and prepared a candidate catalog of AGB stars. Then as a second step, we used XGBoost, which is a classification algorithm to classify between carbon-rich and oxygen-rich AGB stars. Then we also validated our classification by using importances of features, which basically provides which features were contributing the most to the classification. And we found that colors such as G-K, G-H, which are typically used in literature as well for a 2D, for a classification in color magnitude diagram was actually contributing the most in this kind of classification. We also found important features in the spectroscopic coefficients that we were providing. We also validated the classification by plotting color magnitude diagrams and see the clusters of carbon-rich and oxygen-rich AGB stars. And the red clusters for carbon-rich AGB stars and the blue clusters for oxygen-rich AGB stars. And they are separated, but there is this overlap between the two clusters. Then we also checked the Gaia optical spectra for the classified sources. The top panel is for carbon-rich AGB stars, and the bottom panel is for oxygen-rich AGB stars. The top panel shows typical carbon-rich features such as CN, C2, and TiO and vanadium oxide features, and the oxygen-rich spectra in the bottom panel. We further studied Gaia 2-mass diagram for the classified sources in the Milky Way. So Gaia 2-mass diagram is basically plotting Wishon height function on the x-axis and k magnitude on the y-axis. So Wishon height function is basically a reddening-free parameter, which was plotted for LMC in Levjalter et al. 2018 paper. And we can see that the classified sources in the Milky Way are occupying these distinct regions. In this diagram, so oxygen-rich AGB stars are occupying mostly the low mass and RGB region. Some are found in the intermediate mass region and very few stars in the massive region, and carbon-rich stars occupying the carbon-rich and extreme carbon-rich regions. To further study the ages and masses, we also overlaid theoretical isochrones on this diagram, and we found that so the isochrones have different masses and ages. So it's 1 gigayear isochrone of about 2.3 solar mass, which is transforming to become carbon-rich here. And then we have low mass oxygen-rich AGB stars and intermediate mass oxygen-rich AGB stars occupying the two regions. Here I'm showing you the 2D spatial distribution of carbon-rich and oxygen-rich populations. Oxygen-rich stars are occupying the inner galaxy, whereas carbon-rich AGB stars seem to have a more uniform distribution in the outer galaxy. After that, we also analyzed the 3D projections of carbon-rich and oxygen-rich stars. Here I'm showing you 3 projections, XY, XZ, and YZ projections. The sun is shown by the yellow star and the galactic center by this cross. These are in galactocentric frame. And you can clearly see that the XY projection shows that carbon-rich AGB stars are more towards the outer galaxy here. The XG projection showed a clear void towards the galactic center. This is very likely due to interstellar extinction, due to which we couldn't find sources towards the galactic center. Very interesting plot was this YZ projection, where most of the carbon-rich AGB stars were between plus minus 1 kiloparsec in vertical Z direction. However, after 10 kiloparsec, there seemed to be a divergence from the galactic plane. So from 0, you can see a divergence in the second and the fourth quadrant. We saw a very similar trend in the intermediate mass oxygen-rich stars that we plotted. So here, this is the XY projection. We removed sources which were which were within 7 kiloparsec around the galactic center to avoid sources which were affected by extinction. And we also color coded the two clusters that we were seeing, so in purple and in green. So you can see the purple sources have a positive Z value and green sources have a negative Z value. They are below the galactic plane. And if you see the YZ projection, you can see that the purple sources seem to have a positive Z value in the second quadrant, and the green points have a negative Z value, so they are below the galactic plane. Again, what this means that we are possibly tracing galactic warp with AGB stars. So what is a galactic warp? A galactic warp is basically a wavy deformation in a galaxy in the vertical direction, which causes it to bend. So if you have a spiral arm galaxy, it could be affected by galactic warp, which causes an upward or a downward bend in the galaxy. It has been observed in many galaxies, and it has also been studied in our galaxy using other stellar sources such as RR Lyrae, Cepheids, and H1 gas. So in this plot, this is a plot made for Cepheids, which are 300 mega-year-old population. The sun is situated here with this dot surrounded by a circle, and this is also a galactocentric frame. The direction is anti-clockwise direction here, and we plotted a similar plot with carbonate AGB stars, which is 1 giga-year-old population. Here, the direction of rotation is clockwise. However, I have color-coded the same bins. So if we start going from anti-clockwise direction, the sky blue and the dark blue points, if I compare the two plots here, you can see there is a very similar trend in carbon-rich stars that we see at around 15 kiloparsec. Sorry, I forgot to put the labels here. So this is also R in kiloparsec and Z in kiloparsec. So you can see there is a similar downward trend in these two beams. If you see the green bins here, the light green and the dark green pins, you can again see a similar downward trend. There is slightly more scatter here, but you can see at around 15 kiloparsec, there is a similar downward trend. If you further go towards the galactic direction, we found fewer points with more scatter, but again, there is a clear, there is a downward trend, which is very similar to the plots with Cepheids. We did not plot these two bins because they were closer to the galactic center and were affected by extinction. However, we plotted the bins in the purple colors here, the two bins, and we also see an upward trend as shown by the results from Cepheids, and the yellow and the brown bins here, which were again close to the sun. And you can see a slightly downward trend in our plots as well. So it looks like we see very similar results to Cepheids. So it might be that AGB stars can be used as galactic warp tracers. We also tried to study the spiral structure with carbonate AGB stars, and we overlaid the SREED 2019 model in our plot. They had 7 main spiral arms, and there are some overdensities in the Perseus and in the outer arm. Also, there is some overdensity in this Orion arm. So it is also very interesting. We are still looking into this. So to conclude my talk, we use machine learning to identify and classify AGB stars from a massive data set from Gaia DR3. And galactic distributions of intermediate mass, O-rich, and carbonate AGB stars indicate the presence of galactic warp. Carbonate AGB stars indicate the same amplitude of galactic warp as is seen when studied by Cepheids. There is a difference in the two. There is a difference in age in the two populations. Carbonate AGB stars are approximately 1 giga-year-old population, whereas Cepheids are 300 million-year-old population. And there has been a debate whether warp amplitude depends on the age of the stellar population. However, in our study, we have seen that there is no age dependence, and we see very similar trend to what was seen with Cepheids. So the future work is to measure warp amplitude and study galactic warp with our results. Thank you very much.
Thank you, Tanya, for that really nice talk and for sticking perfectly to the time. I didn't even have to interrupt with the microphone. Any questions? Yes, please.
Hi, Michele Trabucchi from University of Padova. Thank you for this very interesting talk. I was wondering if you could comment a bit more on the features you use for the machine learning, and in particular, whether you also use variability properties if you input the actual time series from Gaia, for instance, in the algorithm. Thank you.
No, so in this classification, we did not use any variability properties. We only used Gaia 2 mass and Y colors and XP spectral features from Gaia.
Okay, thank you.
Thank you.
Any more questions?
Any more questions?
Okay, I have a, oh, yeah, go ahead. No, you go ahead.
Hi, Tanya. Thanks for the nice talk. I was wondering, in your Gaia 2 mass diagram, you have, well, I don't know if you can go back to the slides or not, but you have these bunch of carbon stars in the RGB faint, AGB, like the oxygen-rich zone. And could you just comment about it a bit?
So this is likely the overlap between
the
so this
Lebzelter diagram.
Oh, sorry. This one?
I don't know, the slide is not changing here. Yes, yes, this one and the one in the next slide as well. Yeah.
Yeah. So in that some of the stars are you see in the other region.
Yes. And you have it in the next slide as well, where you have the pink dots as carbon-rich stars. So I was just wondering, yeah, exactly, here.
Yeah, so we have verified these stars with XP spectra, and it looks like that these are the few stars which have slightly noisier spectra. And if you look at these spectra, even by eye, it's quite difficult to say whether they're carbonate or oxygenate AGB stars. So, and even in the color magnitude diagram, they have slight overlap. And this is the point where machine learning kind of, I think, got a bit confused with the classification. So I think that's why we see some stars in this region, but there are very few stars compared to the ones on the right-hand side.
Okay, thank you.
Thank you.
Okay, great. Then let's thank Tanya one more time.
Thank you.
And then for the final talk before the coffee break, we'll have Ian Baeza talk about the variable nature of mass loss in low mass red giants.
So, first of all, good morning, everyone, and thank you for the opportunity to present my work here. And today I'm going to talk about what is so far my PhD project, a PhD student at Universidad Andrés Bello here in Chile, and also recently I have started my studentship at ESO. So the main idea of the project is to study the unconstrained mass loss mechanism in low mass red giants. So I've never felt so comfortable of saying that mass loss is a fundamental process. And this is true because every star experiences mass loss. Therefore, since the first star born is shaping the evolution of the universe itself. However, we were not very well understanding what were the underlying mechanisms that is driving the mass loss. However, the last decades, a growing effort has been drawing a really consistent picture of what are the underlying mechanisms across the AHR diagram. So specifically useful for my subset of population of stars that I want to study are global cluster, because here we have a bunch of red giant stars that can share similar composition, age, and distance. Even being well described by this extreme ideal single star population. And if we study photometrically, you can see that there are this really well-defined sequence of evolution in these clusters. So These objects has been longly been used to study mass loss for these kind of stars by the mean of the horizontal branch extension and to infer the integrated mass loss that is experienced along the red giant branch. For this subset of stars, we know that most of the mass that lost during the life of these stars occurs in this phase, coined with about 20 to 25% of the mass is lost from the original mass of the stars is lost in this phase. Think that these stars are around 1 solar mass or 0.8 solar masses at the beginning of their life. So by this extension of the horizontal range, we can infer that it is losing around 0.2 solar masses. However, if we want to use this useful object, we have to be aware there are not single star population, there are in fact multiple star population. And what I'm showing here is just a way of evidence with this specific set of filters in the UV and near infrared, where you can see there is this splitting on the main sequence of evolution. This is caused by an intrinsic light element dispersion, spread, and anticorrelation, being the most common one, the sodium-oxygen anticorrelation. The appearance of these patterns is not well understood yet, but why I'm interested here is that has been pointed out that this difference in substellar population might seem to be affecting mass loss differentially. And what I'm showing here, all the dots are RGB stars and the triangles are AGB stars. And this is the same sodium-oxygen anticorrelation for the nearest global cluster that we have. And as you can see, there is an extreme lack of AGB star in one of the populations. And has been pointed out that maybe this is by an extreme mass loss that they are experiencing this star during the RGB and preventing to evolve to the AGB. In fact, in another global cluster has been recently measured from asteroseismic masses that exist a bimodality in AGB star relative to the RGB stars. Another thing that is worth to mention here that is the long debated Okay.
Online, please mute your microphone.
Thank you. Okay, there is a dependence on metallicity that has been longly debated because for this range of stars, we don't expect that there should be a strong dependence. But from this modeling of horizontal branch for the lower end of metallicity has been measured this in global clusters, and from asteroseismic measurements of field stars for the high end of metallicity, and we end up with this weird-like trend where we have like a peak of integrated mass loss around minus 0.1 to minus 0.5x. And the origin of this is so far not well understood as far as I know. So I wanted to study the mass loss mechanism that operates in these stars. And roughly and naively, we can agglomerate this in two groups, the gaseous mechanism and the dusty pulsation mechanism, which has been pretty well covered in this conference. But we think that this gaseous mechanism operate on low end of brightness of the red giant stars. And call gaseous mechanism all the collection of models that predicts a steep gradient of pressure in the outer layers of the stars. And the energy that came to the material to leave the star came from the dissipation of mechanical waves and magnetodynamical waves. The original idea was that this was a steady outflow, but right now we think that this is more a clumpy-like structure, where this, the magnetic fields might be playing a major role in helping in encapsulating material and ejecting from the star. So this is tightly connected to chromosphere, and here I'm just showing a model atmosphere of the sun just for illustrative purpose. But we have here how the temperature and density varies from a certain point above of the photosphere of reference. And the environment that just described for the gaseous mechanism is basically a chromosphere, where we have this steep gradient of pressure and magnetic fields playing a major role. And also, if we get information from this overlayer of the photosphere, we get immediate information what is going on just in the border of your star. So, by the mean of use of chromospheric lines, it means just a line that has enough opacity in their core to be formed way above of the photosphere. You can get information of what is the relative motion of the material outside in the nearby of your star. And if you are able to measure an outflow, you can get that in average, you are actually having an outflow. And if you assume your model atmosphere, you can infer a mass loss rate. However, there is a lot of degeneracy in how we model this nowadays, but we can restrain ourselves to just observables because the idea is solid. And this has been done for some global clusters where you measure a H alpha line, and you can see that there is as the stars ascend on the red giant branch, it means this became brighter and cooler. You see that there is an increase in the outflow that we measure from these lines. So here's where our project started, and to try to tackle these caveats, we wanted to study the transition between gaseous and dusty mechanisms by the use of several epochs of measurements. And for this, we have used 47 talk by the same reason that I mentioned at the beginning, constrained stellar parameters. And also we will be able to study in the framework's multiple star population, which has been pointed out to be relevant. We come with data from Flames, GIRAS UVs, and Viscerex Shooter. Here's more or less a summary of the stars that we were working with. But for this talk, I'm just talking about the blue ones that are GIRAF data, and the other ones are which are RGB and AGB stars, and the other instrument we're targeting very well-known variables that I will mention at the end of the talk. So the first thing that we have to do is to constrain variability, because a lot is said in literature that we have variability in mass loss, but never really constrain this in a systematic way. So since we have several epochs, we were able to define a very well parameter to measure and quantify this variability. So far, you can ask me for these details later. But with this variability, we are able to take a pair of spectra, separate at different times, at different separation on time, and see when appreciable variation in our stars appear to be perceptible in our spectra. And limited by our sample of time in our spectra, we got this is one of the major results where we have a variation, appreciable variation in between 2 to 4 days already in chromosphere of these stars. With this parameter and with this threshold, we established that we have 9 relevant epochs in our data. And if we compare the variability across all the stars, across 9 epochs, we end up with a plot like this. And the important thing that we can get from this is that the stars become more variable as they ascend in the red giant branch, not just in mean, but also in amplitude. This means if you get an spectra from the low end of the luminosity of the giants, you can get somehow a relatively representative spectra of what you should get from your stars. But if you go to the higher end, this doesn't longer hold true. So with single epoch observation, it's hard to draw conclusions. And this drives us to what we wanted to test, if the stability over time from the previous trends is comparable to what has been previously measured. And so far, here I'm just showing the mean trends of what has been measured. And we have a really good agreement with previous studies at which point start the be irrelevant, the outflows. But drawing conclusion of the high end and compared with single epoch observation, as you just mentioned, is hard to infer if the trends that we measure are relevant or not. So far, also, there is a dependence on metallicity that has been pointed out. And so far, also, our results support these findings. But just be aware that maybe not true this and further study are needed. Also, we have correlated with radial velocity pulsation, not really pulsation, but radial velocity variation, because this also can be related with overshooting by giant convective cells. And there is kind of a correlation in here, but I will also be not really confident on this result, because we expect that chromosphere might be fueled by the dissipation of mechanical waves. But also the stars tend to develop a pulsation and overshooting in the giant phase. Also, we wanted to test the multiple star population, and we did this by integrating specific CN bands on our spectra. What I'm showing here is just that we separate well the population just for temperatures below or higher than 4,000 Kelvin, because after that we have a strong contamination from other molecular bands. And so far we have found not really good dependence on the population in any of our measurements of outflow or variability. So this is the first time that we got an average mass loss, this kind of stars. And so far the outflows increase with luminosity and no And we do not support that this kind of end up at certain point of the luminosity. So future work that I want to mention that we want to connect with dusty pulsation mechanisms. And we have a measure from visible spectra where we have this variation in time in the infrared. And we want to look this specific feature that you can see if they are favored in a specific phase of the pulsation of the stars. Also, another thing that I want to mention, I think you have heard about these lithium-rich giant stars on Monday, where you have this weird subset of stars that show enhanced lithium abundance. And for this star has been measured that is an correlation with chromospheric lines. And therefore, if there is an enhancement of chromospheric activity, maybe correlate with this gaseous mechanism of mass loss. And so far, this has not been tested. And these are things that we want to explore. So thanks for your attention.
Thank you, Ian, for your talk. Any questions? Yes, Hans.
Thanks for the nice talk. I have a question with respect to the multiple visits that you have on those stars. Did you read out the binaries, or you did not encounter binaries or signatures of binarity?
I think I have like 3 or 4 binaries. I haven't confirmed yet, but I'm exploring this. For example, in this plot where you see are color coded by radial velocity amplitude, there is one that is really poor colored, sorry about that. That is black in here, and this is a confirmed binary. But these other like pink ones, also I think they are binaries, but I have not confirmed so far. That was the idea.
Binaries are often hidden, right? So, any more questions? No? Is there anything online? No. Okay, if you come up with more questions, you can either meet Ian in the coffee break or ask on the Slack. Then I'd suggest that we thank all the speakers of the morning session one more time. It was a great session. And well, there's a coffee break now for 30 minutes, and we're coming back at 11:15. Is that right? Great. Thanks, everyone.
We have the picture of the conference. I don't know. Follow him. Yeah. So follow Luciano. We take the picture and then we get the coffee.
Please, let's go to take the picture, everyone.
Or can I get funding to
Sophie, Daniel, Martin, picture. No, Ian is already there. Jaime, let's go to get the picture.
Change of chair. Oops, I'm with a pen mic. Yes.
Ciao.
Good morning, everybody. Again, you can sit to start this session. I'm Flavia Dell'Agli from the Observatory of Rome, and I will chair this really nice session. Now we have Alessio Liberatori with the comparative analysis of carbon stars population in the Milky Way and Magellanic Clouds.
Hi, everyone. I'm Alessio Liberatori. I'm a PhD student at the third year at the University of Athens in Greece. And my work is about characterizing AGB carbon-rich stars into the Magellanic Clouds and the Milky Way from Gaia. So to understand how Gaia is able to see the carbon-rich stars. Just because we are not in an AGB conference, as more introduction on what is a carbon star. So I mean, I'll go fast. We know that these are AGB stars with a C over O equal or higher than 1. They can be variable star like Miras. They could have also very high mass loss rates, and we know that they are dust factories. They are important contributors to the infrared light of the galaxies, and they could also be used as galactic distance estimators through the JAGB method. And in my past 2 years of PhD, studying all the papers available on this topic, I found a lot of papers studying these type of stars into the Magellanic Clouds, but not so many that have a very high sample of stars into the Milky Way. So I found the Gaia golden sample of carbon stars, and we went to study it. So the goal of the research is to characterize the Gaia, Milky Way, and Magellanic Clouds AGB carbon stars through the photometric SED fitting. So this is a quick outline of the work. I will go through all these points. So we took the Gaia golden sample of carbon stars, 15,000 something stars. We applied the extinction correction. We apply a correction for the variability. We create the grid of the models with Dusty, and we apply the SED fitting. So first thing, the sample. How is the sample made? You see here a sky map in blue only. The Milky Way stars, red, green, SMC, and LMC. You see that we have 5,000 stars for the LMC, almost 1,000 for the SMC, and more than 9,000 for the Milky Way. And let's see how these stars are in the J minus K against K diagram, in the 2-mass diagram. And the colors are the same. So blue, red, green, Milky Way, LMC, SMC. And for our SED fitting, we took data from Gaia, 2-mass, and WISE. And we applied the extinction using the 3D dust map by Lallement with the distances from Baylor-Jones 21. And you see how the samples are composed. And I also would like to outline where are the stars in the Gaia 2-mass diagram, which I think it's a quite important instrument to understand which type of AGB stars we are looking at. And you basically see that almost all the stars from this sample fall inside the circular region, which is the one in which we expect to observe the carbon-rich and extreme carbon-rich stars. So once we took the photometry, we had to deal with the variability. We know that these stars are pulsator stars. They could also be Miras. And I want you to quickly see this test that I did. So I basically took a synthetic star, let's say, for which we have a synthetic set of magnitudes. In particular, on the x-axis, the pulsation phase, 0 to 100, on the y, the G band. And I basically applied to all these data points my SED fitting models, and we found this temperature. So you can really see how the temperature goes from 2.6 K to 4,000 K. So we decided to go through to this problem and to correct magnitudes for the SCT fitting, only the Gaia ones, only for the Miras. And how we did it? We basically created a code, a multi-band light curve fitting code, which takes for all the Miras in our sample 2,600. The Gaia GPRP multi-band time series and also Ogle were available, and we create a model of pulsation. And we basically use for the SCD fitting only for the Miras, we use the mean magnitude values that we derive from the best fit model to have the best reliable data that are average data, no? So to have the best average view of which star we are looking at. So after dealing with the photometry, we had to create the models. We used the COMARC's atmospheric models with a temperature, a surface temperature of from 2.5 to 5,000 Kelvin. Mass is lower than 5, and C over O, of course, equal or higher than 1. And we gave it to Dusty, so COMARC's in input to Dusty, with a dust temperature of from 400 to 1.2 K, optical depth from 10 to the minus 4 to 30, and dust composition mainly made by AMC, and also a little bit of SIC. And then we went to the SCD fitting. This is one example of a good fit that we have. The red points, of course, are the photometric data. The blue line is the best fit model. And for each star, we derive the temperature, the optical depth, the dust composition. So if it's entirely made of amorphous carbon, or we also observe a little bit of SiC, the dust temperature at the inner bound of the dust shell, and the mass loss rate, and the C over O ratio, and the stellar mass. Now, very important, the uncertainties. I tried to study how to deal with them, and I basically found this kind of method. So we basically take every star and every photometry value of every filter for every star, and we randomize it in a Gaussian distribution picked at the mean magnitude that you can retrieve online, with the 1 sigma value of the distribution being the uncertainty on that specific photometric value. And we basically do the SCD fitting for each star 150 times. And at the end, for each star, we will have a distribution of parameters, and we take the mean value as the parameter, the mean value of the distribution as the parameter of that star, and the standard deviation of the distribution as the uncertainty. And these are the results. You should mention again that we use for all the stars Gaia to mass wise. All the stars that we study have all these filters, so our analysis is completely homogeneous. And you see on the left the mass loss rate, which are basically centered at the same value, and there is the spread basically due to the sampling. And on the right, the TF, which is a bit different between the Milky Way in blue and the two Magellanic Clouds. I cannot go through in detail of this, so I will go with the summary, and which is that we created a COMARC's plus Dusty grid. We computed the average magnitudes for Miras of our sample, and we derived stellar and dust parameters for these stars homogeneously, and also the uncertainties. But I also think it could be interesting to, I don't know, to show you what I think it could be a possible work for the future. And I have 3 of this. The first, on the left, I actually saw a poster, number 23, which did it. So use machine learning to interpolate between the grid and create a continuous grid and do the SCD fitting with Bayesian statistics on it, which I think it's very important. Second, I think it could be interesting to take a sample of Miras, take this a sample of AGB carbon-rich Miras, and study how these stars vary the values of temperature, for example, alongside the position site. Trace for this star, which is the max, the mean temperature, and the value, and also the other parameters. And the third one is something that I'm working on now, kind of. So I went to Skinakas Observatory in Crete 2,000 meter high telescope, 1.2 meters, and I took some carbon stars, and I found that some of these stars had very strong HF emission. Some of other carbon stars did not show this emission, and I saw that this emission was varying during time from 1 year to another. And I started to study what is going on. This probably is due to shock waves induced by the position on the surrounding environment of the star, but we should expect to see this line at the peak of the position phase, so when the luminosity is the max. But it's not the case. I'm saying this because I've read some papers in the past 20 years. It's not the case. We are finding something different from what we expected. And yeah, if you are interested in this topic, please come talk to me, because I need to learn what you think about this. And yes, I would be very happy to. So thank you very much for your attention, and I'm open to collaboration and suggestions. Thank you.
Thank you, Alessio. You're perfectly on time, and thanks for the interesting presentation. Do we have a question?
Hi, Alessio. Thanks for the nice talk. It's cool to have stellar parameters for this large sample. I was just wondering if you have a comparison with any standards or something where you know that this method is working well. Where you can compare stellar parameters from other complementary methods or from high resolution, etc.
You mean comparing the temperature, for example, from other kind of...
Yes, and the CO growth and some other parameters, so that you know how accurate it is.
We did it for the temperature. We basically we did an SSD fitting using the models that I did with the low resolution spectra of Gaia and other spectra, which I don't remember actually where we took it from. I mean, I basically supervised a master student in doing this, and we found that our values of temperature are compatible with what this person found. So it's different because we are fitting the complete SCD now, and so and not the photometric points. Yeah.
Other questions? If not, we thank Alessio again. Now we have the talk by Claudio Galetti, Understanding the Evolved Stellar Population and Dust Production in M31.
Okay. Good morning. I am Claudio Gavetti, a second-year PhD student from the Observatory of Rome. And my first PhD project is part of a general discussion on evolution and dust production from AGB stars. And it's focused on the study of the galaxy closest to the Milky Way, Andromeda. In detail, I will focus on how Andromeda's AGB, the observations of the Andromeda's AGB stars can help us to understand how effectively and in which way the mechanism of dust production operates in the winds of the asymptotic giant branch stars. Andromeda is one of the most interesting and well-studied galaxies. With a distance of 776 kiloparsec, it's the spiral galaxy closest to the Milky Way. So its large size on the sky allows to measure its resolved stellar population in depth. A big step forward in this respect was given by the fanchromatic Hubble Andromeda's Treasury, which imaged about 30% of the M31's stellar disk in different bands from infrared to ultraviolet. This survey has allowed a series of studies from which important results were determined, such as the derivation of the ancient and the recent star formation history of the galaxy and its metallicity distribution. In particular, this last analysis revealed that the stellar population of M31 formed during the last 10 gigayears is dominated by a solar metallicity component, which is quite unusual, if not unique, compared with the other galaxies of the local group. To carry out my work, I used a large sample of candidate AGB stars in M31, for which the HST and Spitzer photometry is available. The HST data are complete up to 4 magnitudes below the tip of the red giant branch, and so they can be used for the statistical analysis of the AGB distribution in M31. Instead, the Spitzer data are affected by a significant incompleteness, so they can't be used for the same statistical analysis, but these are the data to be considered for the study of the dust produced from the AGB stars in M31. The aim of my work is to analyze the AGB distribution in M31 in order to obtain a complete characterization of the individual sources in terms of mass, metallicity, age formation of the progenitors, as well as the current evolutionary stage and the dust production rate. In order to this, I followed an approach of stellar population synthesis based on my AGB stellar models of different mass and metallicity, and on the description of the dust production in the wind. The ingredients to obtain a synthetic distribution are the star formation history of the galaxy and the metallicity distribution. The age metallicity relationship of M31 revealed that after an early phase in which Andromeda was a metal-poor environment, instead, during the last 10 gigayears, the galaxy was characterized by solar or nearly solar chemical composition. The star formation history of M31 is characterized by an early phase of intense activity, extending over the first 6 gigayears of the galaxy's history. Then, a later episode of intense activity took place in M31 between 1 and 2 gigayears ago. Some star formation occurred in M31 also in more recent epochs, which reflects into the presence of younger and more massive stars in the current stellar population. So, by combining the information on the star formation history and the metallicity distribution of M31 with the evolutionary timescales of my AGB stellar models of different mass and metallicity, I can predict how many stars for each mass and metallicity are currently evolving in AGB in M31. Here I show you the distribution of the M31's observed sources in the near-infrared color magnitude diagram obtained with the HST filters. Overlaid on the data points shown with gray dots are the evolutionary tracks of some selected stellar models of different mass and metallicity. The intense of the red color of the tracks is connected to the dust production rate. From the analysis of this plane, we can see that as we go up to higher luminosities, only the stars with greater mass appear. This is the reason why at higher luminosities, the plane is increasingly depopulated by stars. In fact, both the stars with greater mass evolve more rapidly, but as we have seen, most of the star formation occurred in M31 during the first 6 gigayears of the galaxy's history, when only the low mass stars that are formed are evolving nowadays in AGB. The individual evolutionary tracks rise vertically on this plane because their luminosity increases as a consequence of the growth of their core mass. Then they begin to curve when they are colored with a more intense red, and when the dust production begins, dust which absorbed the electromagnetic radiation emitted by the stellar photosphere and re-emits it at wavelengths higher than 3 micron, causing a rapid decrease of the flux at 1.6 microns. And the results of my stellar population synthesis are reported in this histogram, which shows the distribution of the sources included in the observational sample, shown with a solid black line, compared with the results of my statistical analysis, shown with a dashed red line, which aims to characterize the individual AGB sources in M31. For this purpose, I considered beam of intense, increasingly magnitude, each of 0.5 mag width, in order to understand which stars populate the various beam. I found that approximately half of the stars populate the faintest beam. These are the oldest stars of M31, formed during the first 6 gigayears of the galaxy's histories, and so they are characterized by low masses and different metallicities. The remaining sources are distributed in the other beams. In particular, this beam is populated by stars characterized by low masses, but solar or nearly solar chemical composition. Instead, this beam is filled by the stars formed during the recent burst in the star formation history of M31 occurred between 1 and 2 gigayears ago. These stars are characterized by masses of around 2 solar masses and only solar chemical composition, and during their AGB evolution experience several episodes of third dredge up and become carbon stars and produce carbonaceous dust. The higher luminosity beams are reached only by the younger and the more massive stars. And in particular, the highest luminosity beam is reached only by the stars with an initial mass greater than 4 solar masses, which during their AGB evolution experience the hot bottom burning process, a proton capture nucleosynthesis process which hits the carbon surface and favors the production of silicates dust. The statistics obtained turns out to be very sensitive to the assumptions on the mass loss suffered by the low mass stars during their evolution into the red giant branch. In fact, the luminosity reached by the low mass stars and consequently whether and how many stars enter the low luminosity beam, which is the most statistically relevant since it contains most of the stars in M31, depends clearly on the initial mass of the star. The greater the initial mass of the star, the higher its luminosity reached in AGB. So this allowed me to calibrate the mass loss suffered by the low mass stars during their evolution into the red giant branch as the metallicity varies. And I found that the synthetic distribution which better reproduces the observation is obtained by assuming an average mass loss between 0.2 and 0.3 solar masses with a slight trend with metallicity. While the HST color magnitude diagram allows for a detailed statistical analysis of the AGB stars in M31, information on dust and dust around these stars can be obtained by studying the infrared color magnitude diagram. Here I show you the distribution of the M31's observed sources on the infrared color magnitude diagram obtained with the Spitzer filters. Overlaid on the data points shown with gray dots are the same evolutionary tracks of different mass and metallicity shown in the previous plane. Unlike the HST plane, here we can see that the tracks curve more gradually when the dust production begins and collapse only when a large amount of dust is produced. That is during the very final stages. Here we can recognize the obscuration sequences of the stars with an initial mass between 1.25 and 3.5 solar masses, which during their AGB evolution become carbon stars and produce carbonaceous dust, and that of the stars with an initial mass greater than 4 solar masses, which during their AGB evolution experience the hot bottom burning process and produce silicates dust. Overall, based on the AGB models which better reproduce the observations, I estimate the overall dust production rate from AGB stars in M31, separating the contribution of carbonaceous dust from that of silicates dust. To summarize my results, the statistical analysis of the AGB stars in AGB distribution in M31 revealed that the vast majority of the stars is characterized by old ages, low masses, and different chemical composition. About 15% of AGB stars are characterized by masses of around 2 solar masses and the solar chemical composition, and they are the stars which become carbon stars and produce carbonaceous dust. Only with a smaller percentages of stars with which during their AGB evolution experience the hot bottom burning process and produce silicates dust. Regarding the dust production rate of M31, I found that this is dominated by the carbon stars, which a smaller contribution from that the silicates dust. Thank you for the attention.
Thank you, Claudio. Do we have questions for Claudio? Angela?
So when you were talking about your model tracks on the color magnitude diagrams, how sensitive are you to the precise choice of dust that you're putting into those models?
Sorry, how?
How sensitive are those tracks to what you choose for the dust that you put into the models? Yeah, there was that
on the Spitzer plane, for example. Yes, I found that during the initial evolutionary phases, there is no dust produced, and so the tracks evolve vertically on the plane. And only when the dust production begins, this causes the bending of the tracks to the red part of the plane, which for the carbon stars, so the stars with an initial mass between 1.25 and 3.5 solar masses, occurs when the C over O ratio is greater than 1. And while for the hot bottom, the stars with initial mass greater than 4 solar masses occurred when the hot bottom burning process is in its higher strong effects.
Can I clarify?
Yes, we have short time.
Okay, so when you get the downturn in the 3.6, that's because you've got dust that's absorbing the light, right?
Yes.
If you change the dust, what happens? The type of dust?
This dust is that predicted by my models, and so I didn't understand the.
I'll talk offline.
Okay, yes, thank you. So we can thank again Claudio and move to the other. Now we have the invited talk by Largil Pons, which is on tracing the first AGB stars, formation, evolution, and galactic imprint. It's coming, I'm sure.
Hello. Hello, and thanks for inviting me to this fantastic conference. I would like to talk about perhaps the first AGB stars. Actually, I would like to talk about metal poor stars that are key to understand how the first stellar generations formed, what was the nature, how evolved, how the early universe evolved. But they are challenging. They are challenging from the observational and from the theoretical, from the modeling point of view. Extremely metal poor stars are rare, and we only know about 25, a bit less than 25 stars with ion over hydrogen lower than -4. The modeling involve extreme situations, extreme conditions like the ones that Lionel explained on Monday, and dealing with huge uncertainties. I'm not sure that's part of the motivation, but anyway, we will overview the current progress and challenges of our knowledge of these stars. And this is a bit of my agenda. So I'll talk very briefly about the primitive IMF, the big service, and the classification of metal poor stars. I will talk about the expected progenitors or the candidate progenitors, a few comments on galactic chemical evolution, and a case star that I consider very, very interesting, that's Travel Star. Okay, we can somewhat constrain the primitive IMF with indirect observations, and also with Arc Astronomy Service. So that's studying the lowest metallicity stars in the universe. And in terms of modeling, we can use the very complicated cosmological models that involve hydrodynamics and chemical evolution of the gas. And we can also rely on stellar evolution and nucleosynthesis. Up to the early thousands, the general idea, so first analytical calculations and the early hydrodynamical models had it very clear that only massive or very, very massive stars could form in the primitive universe, so essentially in primordial clouds. There were some calculations proposing that perhaps with hydrogen molecule transition, rotational transition, and vibrational transitions, there could be cooling to reach a sort of bimodal initial mass function with two peaks, one near one solar mass and another one in the massive that is here. This in the review, but Klesen and Glover, there's this interesting and messy plot about what we expect about the primordial IMF now. So you can tell that it's messy. Because at the end of the day, calculations have either to sacrifice spatial or temporal resolution, and depending on what you do, you get a smaller, you get to get a smaller or higher masses. So the concept of critical metallicity. So with this idea that only primordial, massive, or very massive star could form, the concept of critical metallicity was introduced. So a metallicity below which only massive stars could form was introduced by Brom in 2003, and it goes relatively high. So now we can see stars with metallicities lower than this one. Froebel gave it a more observational flavor, and recently Chiaki et al. in 2017, well, not so recently, 2017, proposed that dust cooling was necessary to form stars of 0.8 solar masses or less. These are the ones that, if they form in the early universe, still survives. So we can still see them today. And put a limit in the carbon abundance related to iron, so to determine whether stars form by cooling due to carbon dust or silicon dust. Anyway, moving to big surface and classification, just a bit about the notation. This is the classic, well, this is the nomenclature that Bonifacio in his recent review proposed, and it's very similar to the early classification by Beers and Kruslevin in the early 2000s. Just beware that we are not always careful with the nomenclature. So metal poor stars, in general, anything below minus 0.5. Extreme metal poor stars in principle should be here, but we also extended even up to minus 2 point something. So just when you listen or hear about extreme metal poor stars, try to make sure that what's the ion over hydrogen is exactly, because things can be different. And I put together this plot because it's very exciting what has happened in the last 20, 25 years, or 30 years perhaps, because the extremely metal poor, understanding -3 or less, panorama was pretty scarce up to actually the mid-80s, early 90s, with the HK and the HES service. We started having tens of stars and of extremely poor metallicity, and then with SLOAN and the pristine service, we have this. Well, it's not a lot compared to normal metallicity stars, but it's quite exciting if you think of what we had decades ago. I wanted to show you, just out of curiosity, what the most metal poor stars look like. Well, it changes a bit from author to author, but these are essentially what the 8 most metal poor stars look like. And it's not easy to find regularities, but they tend to have quite a lot of carbon. The pattern is that there is no pattern, there's a considerable scatter. And also beware, because I'm not sure you can see them well, but there are many triangles pointing down, and this means that we only know upper limits about them. So we don't have a lot of information about these objects. Take a look at the zinc in Preble star HE 1327, because I will talk about zinc later on. So it's as metal poor stars piled up, it was interesting to classify them more finely, so not only in terms of their metallicity, because with classification we can find patterns and we can try and find information about different groups of stars. So first, as I was saying, the idea that many of them are carbon enhanced, so first separation, carbon or not carbon enhanced, and then depending on the heavy elements. And then the ones enriched, especially enriched in strontium and barium, would be Camp S. With our process, especially europium, would be Camp R stars. With both, would be RS stars. And of course, Camp No, when they have nothing. And this paper was interesting because UNETAL found that essentially looking at how much carbon one star has, you can tell essentially whether it's going to have to be a Camp S or not. And they divided the metallicity, or the carbon abundance metallicity space in 3 main groups. Group 1 would be the Camp S. Group 2 and 3 would be the Camp Nos. And well, this is a slightly different way of expressing carbon abundance, but this is essentially the same. And these groups are related to different expected origins. Essentially, these Camp S or Camp RS stars are expected to be the small mass companion in a binary system who accreted mass from an AGB that probably has now become a white dwarf. Actually, most of Camp S stars are found in binary systems, and up to 10 or 15 years ago, the model, the way of finding S process was only low mass stars. So this idea was pretty consolidated. Then the Camp No stars, so group 3 and, well, actually also the group 2 here, are expected to come from single evolution. So a supernova explodes, pollutes a primordial cloud or a metal poor cloud, and in that cloud polluted by supernova, you form the low mass stars that we can see still now. The difference between group 3 and group 2, so this Camp No, was proposed again by Jackie et al., saying that essentially they were both Camp No coming from a supernova progenitor, but cooling down by different types of dust-dominated environment. And finally, this is my last classification, but it's again very interesting, by Hansen et al., because as they realized that essentially if you know the relation between strontium and barium, you can tell whether you have a ChemPairs, ChemPair-RS, or Chem. It helps to give us an idea of what the progenitor, the theoretical progenitor is, and apparently from the observational point of view, they are good indicators. Okay, so about the progenitors. Very quickly, because certainly galaxies also care about supernova. So, and supernova in the metal pore field are very creative and are particularly interesting. So first of all, from the epoch when only massive or very massive stars could form the parent stability supernova. So more than 150 solar masses initially, and losing radiation pressure that sustained them by electron positron creation. So they collapse. And from the nucleosynthetic point of view, the whole point is that they do not complete, they have elements from incomplete silicon burning. So not a lot of ion peak elements compared to other normal supernova, and certainly not enough of the zinc that we'll talk about. They struggle to match observation. There was an article, I think 2 years ago, that seemed to have found a counterpart, but it's not clear. Then this would be the standard core collapse supernova. And I have two nucleosynthetic yields plots from FishNet, who included rotation in their models and showed that they could increase the nitrogen production and they could produce S process. And that's very important because initially we thought that S process could only come from low mass stars. And Roberti et al. with Marco Limongi and Alessandro Chieffi provided these explosive yields. This is important because these yields, FishNet yields, were before the explosion. So these are what you would expect, actually, the Roberti et al. Again, they produce more nitrogen, and then they can produce this process. It's not very clear here, but one characteristic in the models is that they tend to produce more strontium than barium. And then there's this faint supernova, or later high energy supernova. The whole point is that supernova yields depend a lot on the initial mass, depend a lot on the energy of the explosion, which is not well constrained. And also, part of the core of the supernova might collapse into a black hole and then do not provide yields to enrich the interstellar medium. So these models made by the group of Ken Nomoto and many other people, essentially in Japan, essentially, proposes the mixing and foldback mechanism. So part of the star collapses, part of the outer layers of the core mix, and they can choose different cuts from where to collapse, where to mix. They play with the energy, so it's a lot of parameters to play with, which is very convenient and have been very successful at matching the abundance pattern of metal core stars. Especially when they introduce asymmetric explosions, they can add an additional parameter. So both with the low energy and with the high energy supernova, the hypernova, they do a pretty good job at matching abundances. Even they can even get zinc. Okay, so in a world where everybody believes that all this star had to be essentially massive, there was a village of indomitable goers and people from other villages that is still calculated non-massive stellar models of very low metallicities. So these Greek ones are primordials. And well, you can see, I don't know, or perhaps not, that there are someone with Z up to essentially solar, but even these articles include calculations from Z10 to the -5. So ion over oxygen around, ion over hydrogen around -3 or less. And it's a big family. It's a big family picture. And it's curious because here in the 80s, the first models could not even identify thermal pulses. And but what they identified was that stars, metal stars experience with mixing phenomena. And in the 2000s, actually 2001, there was the paper by Alessandro Chieffi and Inma Dominguez that was followed by the paper by Lionel Sis, and they did a very complete exploration of what was the evolution of AGB stars or low and intermediate mass stars in the primordial masses. Okay, I admit I did that plot for fun before. So what is in general, what is the characteristic of the evolution of these stars? So they are hotter, they are more compact, they burn faster, so their lifetimes are shorter, considerably shorter. If you have an intermediate mass star of up to 10 to the minus 4 or Z 10 to the minus 3, it will not experience a red giant branch. So the first enrichment will be in the AGB. And as Lionel said, because of their composition, their entropy barriers are lower and convection can advance faster. We saw from Lionel a plot similar to this. So it's telling us about what the mixing episodes are expected to get as a function of their metallicity and their initial mass. Lionel presented an updated version, but this is from Campbell and Latanzio in 2008. So these flashes are characteristic of the most metal poor stars. So these events that are described here. And essentially, this is what we call dual core flashes or shell flashes are proton-ingestion episodes, similar to the ones that Lionel described on Monday. So essentially, protons enter into high temperature regions where there's helium burning. So there's carbon available. Carbon captures protons. You get nitrogen beta decays to carbon-13, and then we have a neutron source. That's in this golden plots can get densities of 10 to the 14, 10 to the 15, so the intermediate process regime. And then this interesting inclusions that Lionel explained happened. There's also another case in the most massive AGB stars, the super AGB stars at the uppermost range, that is the Dredge-out phenomenon, where this phenomenon could happen as well. And what we have here is a standard second Dredge-up, a corrosive second Dredge-up. This is more abundant, more frequent in low metallicity stars. And essentially, the base of the convective envelope, even before the tip AGB, can go so deep that it can take helium burning products and enrich the envelope of the star in carbon. And it means that the star essentially will start the TPGB with some metal enrichment, considerable metal enrichment, and develop a normal TPGB. So this is what Lionel explained, so I will skip it. And this is a very sad plot. I think, yes, it's I should be quiet from after this one, because stellar are uncertain in normal metallicity or in normal, metal poor regime. But when you go to, this is iron over hydrogen minus 3.2, so it's not so much. But we really are at a loss. There's no calibration. And what the best we can do is try and use the standard mass flow rates models. So this is a lot of thermal pulses. Anyway, so still, depending on whether we use the blocker with an eta or 0.01, the blocker prescription corrected, or the Vasiletis, we get very different nucleus synthetic yields, but qualitatively there's a reasonable pattern. So we get the carbon, nitrogen, oxygen peak, then we get this slide. So there are things that are still there, but not knowing the wind system for sun. So this is a plot about the fates of these stars, the ones that end up as carbon oxygen as a function of initial mass for Z10 to the minus 4 to solar. The ones that will end up as oxygen in white dwarfs, the ones that will end up as supernovae. And this is the continuation to the lowest metallicities. Just out of curiosity, the mass limit between the carbon, oxygen, and oxygen neon white dwarfs leads to hybrid carbon oxygen neon cores that might explode as supernovae, as faint supernovae, if in a binary. And this mass limit between the oxygen neon and the normal core collapse supernova, a 0.1 solar mass limit, this is the famous electron capture supernova that are still being looked for. At this point, about the fates of the most metal poor stars, I think important to recognize the value of the opacities that Paula Marigo put to the community. And well, just to say very quickly that, that third JCHAP is particularly efficient in metal poor stars. Hot bottom burning, so even with hot bottom burning, in many cases, we still produce lots of carbon. So we keep having carbon stars all the time. This is another sad, very quickly, another sad explanation of what the effects of using different codes with different input physics. So at the end of the day, the nucleosynthesis with Ventura and Flavia, Paolo Ventura and Flavia Draghi code, and our code is Monash and Ström law, yield very different yields at the same metallicity. So that's going to affect dust. And exploring the space parameters is interesting. So we have done quite a lot in terms of modeling. This is summarized here. And in terms of galactic evolution, our stars, so at least Z10 to the minus 5 stars, updating models might help to match our problems with nitrogen. And again, zinc is a problem. And just show you this scatter. This is scatter in heavy elements at the lower metallicity. So that might point to different progenitors. Could AGB stars form? So very quickly, this part that it's certainly the most exciting part of the talk, at least to me. This is Frevel star in 2005. That has been, and a recent paper in 2019 that provided new calculations, measured zinc 0.8, and provided a fit to one of these hypernova. Without considering strontium, because Frevel star has a strontium, and we know this from the beginning. This is a couple of fits from supernova, are very good, but the strontium and the barium are not fitted, not even intended, not even appear in the papers. And barium was measured 2 years ago and presented by Molaro. Barium is 1.3. So we have about 1.08 of strontium over ion, 1.3 of barium. And so if we put strontium barium at the correct, it's abundance that we can get with sparse stars. This metallicity pattern that is similar to what we knew for Frevel stars, the existence of zinc that made us propose a hypothetical formation scenario for Frevel stars. So imagine a primordial supernova, perhaps like the one they proposed in Zedin, Italy in 2019, that provides zinc, pollutes a cloud. In these clouds, a 3 solar mass stars. This 3 solar mass star lives, dies, and pollutes. Again, it provides a second pollution in the cloud. And here forms the star that we know now as Frevel star. And perhaps instead of having a sequentially pollution scenario, we could have a binary. But there's no evidence of binarity in Frevel stars. So we tested this hypothesis with models and following the detailed nucleosynthesis with different carbon-13 pockets, which is another problem with uncertainty. And we could match nicely the strontium and the barium. We have problems with oxygen, but the observation story of oxygen seems a bit complicated as well. And the whole point is that, well, this star, Frevel star, is below iron over hydrogen -5. So this is very, very, very metal poor. And the best we can do to fit it at the moment is a combination of a supernova and an AGB star. Where, even assuming this is correct, do we know that this was a general case? Because Fragile star is very, very, very rare, or these metal poor stars are very, very, very rare. So perhaps, okay, they existed, perhaps they were supernova, sorry, they could be explained with the contribution of an AGB star, but perhaps they are describing a very strange, very exotic place of the a poorly mixed early universe. So perhaps these crazily metal poor stars are interesting laboratories, but perhaps what they yield us, the information they give us, cannot be so easily matched with galactic chemical evolution. So they are outsiders, they are liars. But I think that still the question remains, when should galaxies, or when do galaxies should care or should start caring about AGB stars? This question remains to answer. Thank you very much. Sorry.
Thank you very much. Do we have questions? Amanda?
Hi, Pilar. That was a really nice review. A question about the formation scenario of, I guess, Freible star. So you mentioned a primordial supernova is needed for zinc, but it'll also make other things. It'll make a lot of other things. So how does that fit in with your formation scenario?
Right. Yes, I wanted to talk about that. So that's fantastic. One of the things is that at the end of the day, what we fit to Freible star is a cloud in which only 3% of the matter is from a supernova. That was very important, and I should have said it. So essentially, the bulk of what we produce is from the AGB star. The thing is that there are things that we cannot do. We cannot do zinc, certainly. And that zinc, essentially, the one that we have initially, this is 0.8, is essentially the one that we have at the end. So it remains unaltered. But for the rest, carbon, oxygen, well, of course, the nitrogen, and the S process, of course, and all of the elements, the light elements slide. The composition of the AGB is what dominates our fit. So it was 3% of supernova and the rest AGB matter. Thanks.
We have time for another question or comment, even from remote, if this is the case. Well, if it's not, I would like to see again the comparison between your models, if you comment.
Yes, sorry. I made it too long. Okay. Yes, it's a pity because we cannot see. I can show it to you later. But what we should be comparing, I don't know if you see this dotted line, which is somewhere near the red, and between the red and the green. So this could be our 6 solar mass model computed with the Vasiliadis and Wood, which is the mass law rates that you used in this paper. So essentially, this would be, and you should compare that with this dashed black. So it's a big difference in the yields, certainly. So I think because we have so many uncertainties, it's always very useful and very healthy to compare what happens with different codes, with different input physics. And calculations are long, so it's not easy to repeat many. And to explore the space parameter, which is something that's probably necessary in this metallicity range, is tough.
Okay, thank you very much. We can now move to the next talk, and thank again, Pilar. Now we have Elizabeth Tarantino who will talk about dust production from metal-poor AGB stars, JWST results from Sextans A. Thank you.
Hi, everyone. My name is Liz or Elizabeth Tarantino. I'm a postdoc at the Space Telescope Science Institute, and I'm really excited to be here today, and especially this topic of the conference. My background is in understanding nearby galaxies and their ISM, so answering the question, why do galaxies care about AGB stars, is one that's very close to my heart. And I'm going to be doing an overview of this program that JWST observed with Sextans A. And we have a very large team. Many of those are in the audience today that are highlighted in purple. And I'm just going to start by talking about AGB stars producing dust. So this is obvious to everyone in this room. We've been talking about AGB star dust production all week long. And one of the things that I just want to highlight here is it's pretty clear in the local universe that AGB star dust production matters a lot. We see this in presolar grains, we see this in the Milky Way, we see this in the Magellanic Clouds. So locally, AGB stars matter a lot. However, it's unclear the role of AGB stars at high redshift. And this was already touched upon by a variety of people, including Martin's beginning talk that kicked us off. So there's this observation of the 2175 angstrom bump at about a redshift of 7. And this bump comes from small carbonaceous grains. We also see very large dust reservoirs at redshift of 8 and 9 in these very, very early galaxies. However, if you look at models, AGB stars don't really begin producing dust until later in the development of the universe. Martha also showed this great plot from the Schneider and Milano review article that came out last year. So there's two main questions for AGB star dust production at high redshift. The first is, do metal-poor AGB stars have high enough dust production rates to even contribute at this level? As you can see, there's two different pathways for metal-poor versus metal-rich AGB stars. And then the second question is, can AGB stars contribute to the reservoir of dust at early enough times because they have much longer lifetimes than supernovae? And most of the analysis of understanding this has been done with models, but we really need more data to constrain these models. The models are very uncertain. So that's where these observations come into play. We all know that AGB star chemistry depends on the metallicity. So this is a visualization that Ian made that visualized the amazing models from Amanda. And essentially, what happens is when you're at this metal-poor regime, your maximum mass for carbon stars can increase. So this means that metal-poor carbon stars can begin forming dust just 200 million years after they form. This is really important because the carbon stars will be making their own carbon, so their dust production rate doesn't depend on existing metals as much. However, we also really want to understand the massive oxygen-rich stars because they're going to be producing dust the earliest, and they are the most well unconstrained currently. So over here, we have the metallicity of Sextans A, which is the galaxy that we're targeting, and the main stars that we're looking at are going to be these really massive AGB stars. Okay, so the Sextans A program. So Sextans A is a perfect galaxy for the study because it is very metal poor. Its oxygen abundance is about 7% solar, and if you look at the stellar population abundances, it ranges from about 1% to 5% depending on the age of the star. It also harbors a large stellar population and a variety of AGB stars, so there's going to be a lot of samples that we can look at and actually do statistics on the data. It's also one of the most metal-poor galaxies that has a detection of ISM dust. So we know that dust is there, and we have an estimate of the dust mass. It's nearby, means that we can resolve the stars at really nice detail. It's at the very edge of the local group. And as I mentioned before, it has known dusty stars that have already been characterized from Spitzer. So we targeted Sextans A. Martha Boyer is the PI of this program with using a combination of imaging and spectroscopy. So we have 13 wide and medium band filters, 8 from NIRCam in the near infrared, and 5 from MIRI in the mid infrared. And you can see the coverage on the galaxy here. We cover most of the stellar disk, avoiding this bright foreground star right here. We also carried out some LRS spectroscopy. This is about 5 to 14 microns of 6 interesting sources that were identified in Spitzer. So I love images. I love staring at JWST images. So there haven't been a lot of images of galaxies in this conference. So I just wanted to highlight the beautiful JWST data that we have. Often dwarf galaxies don't look as pretty as dramatic spirals like Andromeda, but if you work on them a lot, they become near and dear to your heart, and images like this make me smile. So this is our pretty JWST image, and it kind of looks like a puzzle piece because of the way that the observations were carried out. Okay, so identifying the AGB star population. We identify the population by calculating the tip of the red giant branch, and then identifying all the sources that are brighter in the F150 or the F277 filter. That's 1.5 or about 2.77 microns for those that are unfamiliar with JWST filters. We then find all of the sources that are red by doing a cutoff on F090 minus F150, and then we do a secondary cutoff using our widest range and color space from NIRCam to remove the red supergiant branch. This results in about 241 JWST AGB candidate stars, and this is way more than what was found in HST and Spitzer. And you can see all of these AGB stars overlaid on that RGB map that I was showing before. They kind of cover the full disk of the galaxy and are mostly randomly distributed. They don't really, they're not really concentrated on the star formation region here, or there's another star formation region here. Okay, so Martha already did a great introduction to this morning about classifying the AGB stars and a lot of the groundwork that was performed with Hubble and how we want to translate that to JWST filters. So essentially the name of the game is looking at all of these near-infrared molecular features from things like CO and the waterline, and using those in color diagrams to carve out a space where most of the carbon stars will be residing and most of the M stars will be residing. For our program, we have the F140, F150, and F277 filters that can do this. And it ends up being a little bit more challenging than originally was thought. So let me show you here on the left. These are the simulations of what these, of what these stars look like in this color space, where the carbon stars are in red and the M stars are in blue. And then we also have previous classifications from HST that are overplotted here. So the HST ones are in those red triangles and the M stars are in blue. And you can simply just draw a line that should separate these two populations, both from HST and informed by the models that carve out this color space. However, when you draw that line, what ends up happening is our C over M ratio is very low compared to what we see in Hubble. So Hubble gets a C to M ratio of about 7, whereas we're finding something around 1. This is similar to what was calculated in JHK photometry, but one of the reasons why this is there's just this cloud of points in the color space that have these featureless SEDs in the mid-infrared. So for this star, this is one that's well classified. You see a deep H2O feature, a deep water feature, whereas the other ones are essentially featureless, which makes it really difficult to classify them. So I just want to highlight that take caution when you're using JWST filters to classify AGB stars, especially at low metallicities. There may be a variety of contaminants, such as red supergiants, even though we attempted to remove them, and YSOs that could be contributing to this low over C of M ratio. Okay, so now let's talk about the dust. So the stars in Sextans A are incredibly dusty. You can see this through this 277 minus 7.7 micron CMD. And essentially what I did here is I just drew a line to find the dustiest ones. And we have about 36 extremely dusty carbon stars. And you can see their SEDs featured here compared to a dust-free star. And then we just have 2 dusty oxygen-rich stars. So even though our C over M ratio is about unity, most of those stars aren't dusty. We just have 2 dusty M stars. So we can calculate a color-based dust production rate based off of the sample of dusty stars. We use a parameterization from Martin and Greg Sloan's paper from 2018 that uses a sample from the Magellanic Clouds as well as dwarf spheroidals. And we find a dust production rate of about 10 to the minus 8. So of this dust production rate, carbon dust contributes about 93% of the total, which makes sense since it's such a metal-poor galaxy. And if we compare this to the ISM dust found in Sextans A, we get one of these classic many orders of magnitude range for the contribution that AGB stars may be making, from 0.3 to about a maximum of 20% in the most optimistic cases. However, this is just done with a color-based DPR. Those are well known to be inaccurate. So I just want to highlight to see the poster from Tom Henry, who's doing SED modeling of all of these sources. Okay, I'm going to very quickly talk about spectroscopy. I don't have that much time, but we have spectroscopy of these 6 interesting sources. 5 of them are carbon stars, and you can see there's acetylene feature right here, and then one of them is this oxygen-rich source. So the carbon star, I'm just going to focus on one of them here that has a prominent SiC feature. And one of the interesting things here is this means that silicon can be produced or exists in this star. AGB stars are not efficient producers of silicon. So the silicon that's here is likely was made a priori before the star formed. So, and also the SiC feature is just as prominent as stars in the SMC, even though it's a factor of 4 lower metallicity. Okay, now I'm gonna try and go through this quickly. This is a really interesting high redshift analog oxygen-rich star. So it's about 4 to 5 solar masses. It has a very deep water feature around here. And what I'm showing in this plot is the spectroscopy here and a variety of fits that we tried to fit the star. So this right here is the photosphere fit. And the difference between the photosphere fit and the data indicates that the star is very dusty. So one of the cool things is there's no silicate bump in a characteristic 10 micron silicate bump in this star. So we try a variety of models and essentially rule out all of these models and find that our data is most consistent with metallic iron dust. Metallic iron dust is featureless in the mid-infrared, so it fits our data well, and we rule out a bunch of these other options. If you have questions about this, you can ask me later because I think I'm over time. Okay, I'll just leave my summary slide up here, and I'm looking forward to hearing your questions.
Thank you very much, Liz. It's really interesting, this overview. And do we have a question? Okay, Sundar.
Hi, Sundar Srinivasan, Area Unam. I had a question about that one oxygen-rich star.
Yeah, sorry, I went through it really quickly.
About it?
What?
What is special about that one star that's all the way out in the carbon region there?
Oh, which one?
So you had the straight line that separated the carbon stars from the oxygen-rich stars, and there was that one oxygen-rich star.
Yeah. So this, this
special?
one is a misclassified carbon-rich star that was classified as oxygen-rich in the HST data, and it's actually pretty straightforward because I can just show you. Oh wait, I went past it. So this line right here is imperfect. You see how some of the dusty carbon stars can go over to the M star portion of the diagram. That's exactly what happened here. We actually have spectroscopy of that source. So it's one of the ones that we have spectroscopy of, and it's very clearly a carbon-rich star. So the filter, color diagram classifications, even in Hubble, are a little imperfect.
Okay. So, Beth? Okay.
Hi, Beth Sargent, SETI Institute. So also the oxygen-rich star LRS spectrum. Can those look like water vapor absorptions at the shortest wavelengths? Does that tell you, could that be photospheric, and could that tell you how much dust is there based on how much you can fill it in from some sort of continuum source like iron?
The ones here? Or the ones over there?
No, in the LRS, the black spectrum from like 5 to 8 yeah.
Right there. Yeah, so I guess I don't fully understand your question. We do see water vapor in the spectrum, but I don't know what that could tell us about the dust. It's in the photosphere model, if that helps.
Like if you had a photosphere, I guess you would need to constrain the spectral type of the photosphere. I'm just trying to figure out if that could tell you how much dust is present based on how much it's filling in.
Yeah, so you can see right here, the photosphere model is the gray line. Sorry, that things are a little shaky. So the photosphere model actually fits that water feature pretty nicely. You can see that there's a little bit of excess that can be explained by the dust.
Okay. You're pointing to like the near infrared, but I was talking about the
Oh, I see. Yeah, this is another water feature. So I was just pointing that one out where the dust isn't contributing as much.
Okay.
Okay, one last question by Theo.
Hi. So I was wondering if I followed right, that in these very metal ore stars that you see this metallic iron dust, and the other one where you see SiC, and both these elements are not expected to be produced by these stars. So then have you considered how much of these elements you actually need to make all the dust that you need for the models? Because I would expect that you don't have a lot.
We have not done that calculation yet, but oh, yes, Martha's nodding her head. Okay, Martha, you want to go ahead?
Yeah, we did do that calculation for this star. It does have enough iron to explain this much dust. Yeah.
Okay, I think that we can really thank Liz and all the other speakers of this session. Are there other announcements? No? Okay, so we will meet back again at 2. Okay, see you later. Welcome back, everybody. We can start. Now we have one talk before discussion, and we welcome Hedi Abdullahi, who will talk about the INT survey of LG dwarf galaxies number 8, detection of the LPV of Andromeda dwarf satellites. Thank you.
Hello, everyone. My name is Hediye, and I'm a postdoctoral researcher at Concoli Observatory. I'm working on RR Lyrae stars, but also I'm part of INT survey project. Here you can see the PI of the project, Jacques Van Loon, and also the other my colleagues which are participating in the scientific part of this project. And as observations took more than 3 years, so I have lots of other colleagues which are participating in the observational part. This project was designed to observe dwarf galaxies, which is observable from the northern hemisphere. And here you can see about 59 objects which we observed. Some of them are satellites of Andromeda, satellites of Milky Way, and also some isolated dwarf galaxies, including also some globular clusters. Okay, we use INT telescope, and as most objects are small, so they fit well into 4 CCDs in WFGAM by 34 at 34 arc minutes field of view, and observation took around 3 years in 9 epochs, and finally we observed around 59 objects. And actually we wanted to observe dwarf galaxies to identify the long period variable stars, to rebuild a star formation history based on them, and after that calculating their mass loss. But in the first step, today I just talk about the step 1, which is publishing about the long period variable stars catalog from the Andromeda dwarf satellites. Okay. This plot is from Martin. Actually, I use it because it has a good resolution. All the objects here is around 24 dwarf satellites of Andromeda, which we observed. The blue one already studied in our group in separate papers, and 4 of these dwarfs actually has very few observations, so we couldn't use them as to identify long period variable stars. And for this paper, we used 17 dwarf satellites, which here you can see with the purple points. But totally, after the observation, we reducted all frames, and it was around more than 560 frames. We use telepipeline for reduction, and we use a Stetson package, and in some cases photoutils for photometry. Here is one of our output as a photometry. You can see it's for AND IX. And after the photometry is done, we check the accuracy of the photometry by some methods. Like here, we use some simulation. We add some artificial stars in each frames in different filters, and we calculated the attributed and also the recovered magnitude and compare them to each other. And also we compare our catalog, our final catalog with other available catalogs in same filters. We also calculated the completeness limit for each frames. So after we are sure that our final catalog is reliable, we go to the next step, which is identifying the long period variable stars. We use variability index algorithm by Estetson, which works based on the correlation between the deviation, the magnitude and deviation of the mean magnitude in different observational night and filters. And with this method, each star have a specific variability index. And as we are searching for long period variable stars, so we just mostly focus between the RGB tip and AGB tip, and we divided our catalog into different intervals, magnitude intervals. And based on this histogram, we put a threshold for each magnitude interval to determine in each group what is the threshold for being a variable star. So as the variable stars couldn't have the negative index, so we mirror the histogram, and whenever we reach to 90% of our population is variable, we decided that in that variable index, the stars with higher variable index than threshold could be variable. And for checking this method, also we use some simulation. In the figure 9, you can see that we add some artificial stars in frames, which they are constant star, not variable. And we repeated again our procedures, and we saw that we decided that this star is exactly constant and not variable. So here you can see, for one example, is Andromeda 2, I think, is one of the most largest satellites of Andromeda, which occupied around 3 CCDs of IMT telescope. And the red circles show the long period variable stars. We focus on long period and we omitted the short amplitude one. And also, I have another example here is Andromeda 3, if I can see here. Yes. And here is another example for the light curves. In most cases, we can fit a smooth curve on them, but there are some cases that couldn't show a really good fit, but still we have them in our catalog because just we introducing the long period variable candidates. And after that, we calculated the half-light radius and also the tip of the RGB for each dwarf galaxies. We fitted 3 different profiles on the number density and surface brightness of each dwarf galaxies. And in most cases, also the output results are very close to each other, and also is in good agreement with other literature. And in figure 14, you can see the distribution of Andromeda satellites, which is based on the half-light radius we calculated. Of course, it's multiplied by 100. And also the color bar shows the distance, which we calculated based on the TRGB. And for TRGB, we use Sobel filter, as you can see. And in figure 16, you can see our calculated, thank you, our calculated numbers with a black circle. And the red error bar is from other literature, which we just gather. And also it has a good agreement with other literature. Okay, and it's the final CMD, which we rebuilt it. And the long period variable candidates, we tend to have light rarity, shown here with a blue square, and also the LPVs in all observed field is with shown with a purple one. Here is the CMDs for all 17 CMDs, 17 dwarf satellites of Andromeda. And final, actually in the next paper, we want to publish the star formation history based on the long period variable stars. And we estimated their burst mass, their age, and also the pulsation duration. And we rebuilt the star formation history based on them. And also we calculated their mass loss ratio based on the CMD fitting, SED fitting, sorry. And here is just an example. And we are going to publish Andromeda dwarf satellite LPV catalog very soon. And after that, the other series could be the Milky Way and also the star formation of them. So, yeah.
Thank you. Time for questions or comments. Thank you, Andrea.
Hey, it's weird to try and ask a question for someone who's behind me. You said that you started on modeling some of the SEDs. What are you using to do the modeling? What RT code?
We used actually Dusty, but after that we published a grid, which in our group we are working on it, which use all the grids, all the other grids which are available in the Dusty, but it's not. There isn't any need to use Dusty by eyes. We can just use it with just one code. And we just gather all the grids together in one grid. Yes.
Other questions, comments? No? If not, we thank Eddie. And I pass the floor to Claudia for the discussion.
Yes. So can you hear me? Oh, by the way, if you didn't notice, this microphone can be moved. It's not fixed on the table, so we all become giraffe. So I collected the discussion topics that I received and that we had on Slack via email, etc. And they will be now shown up. And can you check, please, online if some people then want to intervene or ask questions?
So far?
Yeah, no, because I didn't ask any question right now. So what I will do, I will read some of the questions are specifically to some colleagues that spoke until now. And some others are just point of reflection. Here they are. Thank you, Matthias. Can we make an applause to our IT support? They are doing a fantastic job. I hope you agree with me. So the first point is AGB variability is as powerful as complex. Do we need to better anchor the LPV classification to the physics and chemistry of stellar interiors, atmosphere, circumstellar environments? So anybody wants to reply to this question? Do you have ideas? Don't be shy.
So I kind of hinted at this in the question that I asked to Michele, that only yesterday. Anyway, so when we're talking about, anchoring to the physics or, thinking about the connection between the interior, the atmosphere, and the circumstellar environments,
One of the things for certainly the dust that is forming is that there's definitely a key spectral feature that appears for semi-regular variables much more often than it does for Myra variables. And so to my mind, that's in this space of, okay, I have no idea why that particular material only forms or preferentially forms in semi-regulars, but it must be linked to these other things. So I think that that's a starting point for a conversation of, okay, how do we make this stuff? And then how does that link back to what's going on with the star?
Seems like our community is not used to discuss. We all have, most of us have microphone in front. Come on. Leo.
Sorry. So it's a bit difficult for me to understand exactly where to go with this question, because I thought that from the presentation of Michele yesterday, this pulsation bands, tracks, whatever is the name that they have, sequences, thank you. They are very clearly linked to the mode, so to the physics, and then how large these pulsations will be at the surface, and that's linked to how much mass or to how high the density scale height of these atmospheres will be, which then in turn is probably connected to the dust. But it's not clear to me then how do we improve on this phenomenological classification, which already seems to be linked to the physics. Well, I don't know if this made sense.
I think we have two sides. One is from the modeling point of view, and the other one is from the observational, providing constraints for all of this, right?
So I don't know if the questions are anonymous, but so I asked the question. So guilty as charged. So I'll just try to clarify. This is in the line of the, say, provocation I cast yesterday about the fact that semi-regular variables, for instance, in Myras, in a certain range, they're probably the same thing, but it's not something we are used to. Just to give you an idea, if you, well, there was this paper by Reed and Golson in 2002, where they clarified why Myra changes by a factor 1,000 in luminosity in the visual, but not in volumetric. That's because you form molecules, of course, right? So if you are in a low metallicity environment and you form pure molecules, does the definition of a Myra change? Because Myra is above 2.5 magnitudes in amplitude in the visual band. So is a classification of an object dependent on the environment? Seems a bit strange to me. Then again, Martin said in the very first talk, where is Martin? Hi, Martin. That when you want to measure distances with Myras, with pure luminous relations, you kind of say we try to get rid of as many semi-regulars as we can. We risk getting rid of Myras. So how do we play with that? Another example that comes to mind is in the 2023 Gaia DR3 paper with the catalog of long pure variables. We compare with the Assassin survey, and there's a bunch of stars there that are classified as semi-regulars that are very clearly Myras in the Gaia catalog, because Assassin telescopes do not have the same kind of resolution. So you have blended sources. So the amplitude, the light curves are like compressed. So you have a classification that is then strongly dependent on instrumental effects. So nowhere here the actual physics of pulsation, atmospheres, barely evolution, and it's something that people in various fields, including cosmology, apply. but it relies very little, in my opinion, on the physics of stars. I'm not saying I mean, it's very convenient classification because you only select Myras that arguably many of them, most of them have very clear advantages in applications, many applications, but it's a slippery slope, okay?
I guess I would add something. Do we see, I mean, this is a question for you, I think. Do we see, I mean, the SMC has metallicity, that's 1/5 of the galaxy. Do we see differences in the pulsation properties between the SMC for Myras compared to our galaxy? That's a very different metallicity environment.
On average, we do. For instance, basically in amplitude, if you can do the exercise with the Ogle tree catalogs in the there is even Ogle 4 there is for part of the disk of the galaxy, and at a given period, on average, you have larger amplitude in more metal-rich environment. It's an average trend, but it's there. So yeah.
No more comments? Just open your micro. It's like we are in a setup where we can just talk.
I think regarding what Michelle has told, that it could be interesting also to explore the variability, the time variability in different wavelengths, very different wavelengths. Hopefully something in the ultraviolet, maybe something in the far infrared, maybe also variability of lines, but not the radial velocity, but the intensity and maybe the shape of the lines. Would be also good to differentiate the physics, the physical mechanisms.
Michele, a question again to you. If you compare your semiregulars and Myra predictions in terms of how they change in amplitude in different bands, can you say that there is a differential difference, bit of a difficult word, between Myras and semiregulars, or between classes of stars that could help us towards another definition?
I don't know. Sorry. It's a very interesting point. There is a paper by Wanek, 2022, I guess, from the Ogle group, who did a multi-wavelength study, but I think that it was limited on Myras. And then again, why the poor semi-regulars are never studied? Well, that's not true, but then again.
There is a comment online. I don't know if Joseph wants to open his mic himself.
Not really. But I wrote what I mean.
Cannot. Yes.
So if you want to read me, if you base the classification on amplitude, you have to consider that the variation in spectrum of a carbon star in the optical is much smaller than for an M star because of the titanium oxide in the M stars. So usually it can happen that the carbon semi-regular is actually a Myra, but it's just the visual amplitude that's too small because of the CN and C2 variations.
Actually, that is something that I learned from Joseph during my PhD, and I'm wondering now, since my PhD is like 14 years, we are still relying on that. Isn't it time that somebody starts to study and make a new classification of Myras for carbon stars? We have a lot of carbon stars. We have a lot of data of carbon stars. Then we make also Joseph happy. We look more at carbon stars.
I think I'm a bit confused about this whole semi-regular Myra thing, because there's different types of semi-regulars in our classification. So which ones do you keep referring to? Is it only the semi-regular A's or also the B's and the C's? And where do you draw the line? Because if the semi-regular A's, so if I remember correctly, it's the A's that are also actually regular, just with a low amplitude. But can't you then just bunch them all together with the MIRAs and then see if there's any amplitude level where things would change or not? And if it doesn't, then that's just one category. Then they all belong together. And then the Bs and the Cs, those you can treat differently. Or am I missing something?
That's a very good point. So actually, I should clarify that since I'm normally used to to use the Ogle catalogs, I use their definition of semi-regulars, which, to be honest, it's not so clear how it relates to the other ones. It kind of combines SRA and SRB as far as I understand. Okay, but that's a very good point. So there is confusion in the classification, right? But one good thing about the SRV definition in Ogle is that it's very self-consistent because they have a consistent, large, statistically significant sample with long light curves, with dense sampling. So they simply distinguish these stars from the OSEX and the MIRAs. So it's a useful one. But I agree, this is a confused landscape.
I agree fully with you. I think we really have to separate this classical approach to well-known and well-studied semi-regulars and even irregulars in the old catalogs. There, the classification was often based on bad sampling and combination of data that did not fit together, and a systematic approach where from a large survey that treat the stars homogeneously. We did in the 80s with regulars and semi-regulars, and did this also in the 90s. In all these cases, when you looked at the more physical parameters, if you neglected amplitude and light curve regularity, if you exclude this, but if you look only in time scales of variations, that's sometimes easier. If you then compare, for instance, properties, mass loss rate versus time scale of variation, they are all the same. They are essentially the same. There's no big difference. We did a large survey in CO of irregulars of type B and semi-regulars of type B if they have the same chemistry or so. So there's a strong traditional observational bias. And you can overcome this only by this more systematic surveys where you treat them in the same way from the light curves. And the amplitude is really not a good argument. This was said before that this has to do. The only thing where the amplitude is really relevant is, of course, for the very large amplitudes where you see even emission lines in the spectra. There, obviously, this is then related to atmospheric properties. In all the other cases, it's really an opacity problem that you see in the visual range.
There's still a related note online. Ian, if you want to speak up, otherwise I read it, what you're saying.
Yes, hi everyone. Sorry not to be there in person. I was just wondering that there's all this talk about LPVs and semi-regulars versus MIRAs. Are we missing the point that we should be talking about fundamental mode, first overtone, etc.? Are these not more significant differences? And is this overlooked when we simply just look at MIRA versus semi-regular?
Yes, thank you. That's that's a very good point. I would love to. I didn't want to be the one to propose this, but I would love to have a classification where you just say this pulsating one mode fundamental, two modes. We actually proposed this in the paper with Nami Molavi and Thomas Lepselta. So we have semi-regulars that pulsate primarily in the fundamental and a secondary first overtone, or the other way around, or just one of the two. Okay. Then again, we get a bloated classification because when you get a star that pulsates in three modes, the combinations are many more. So it may be meaningful, it may be inefficient, okay? But at least when you have at most two active modes, two periods, maybe a long secondary period, so let's not forget about that, it's definitely physically more meaningful. One relevant aspect here is that pulsation originates in the in the star. It's interesting, in the envelope of the star. Variability depends on position and depends on how the atmosphere, the dynamic atmosphere, reprocess that. So it cannot be only, and then of course on how we detect it photometrically, etc. It cannot be only a matter of modeling position. It's a matter also of modeling everything else above. So that's one of the difficulties. Okay, and that's why I haven't shown any synthetic light curve, because just with position, you don't really get to make them. And just to add a point, this is I think this is very timely and relevant aspect, because the LSD survey is starting now, and in a few years we will have great data on long period variables that we want to be able to interpret in a consistent fashion, and we will find out new stuff, that maybe new kind of variables that we didn't know. So it's better to be anchored in physics than in traditional classification. I don't know.
But isn't it then not a bit similar towards astroseismology, where one is just quoting the L, M, and N values for a star, where we would be quoting, you know, the fundamenta and the overtones, or potentially several of them? Shall we move to the next? Actually, I have 3 slides. It's not only this one. Well, it means we have, it's nice. It means we have also arguments for the next discussion. So how much do we think AGB stars contribute in what ways at different times in the universe? What do we tell local higher redshift or high redshift galaxy people to explain why they should come to the next AGB meeting? What would we want to tell them, and what would we want them to tell us? How do we want them to talk to us, and how should we talk to them?
Since we're staying anonymous, I don't know who posted this question. I imagine the person was thinking this was more of a sort of a step back philosophical question that maybe makes more sense towards the end of the conference, especially if you have 3 more slides of concrete questions. I do think it's an important question for us to think about, to sort of get out of the bubble of this room where we all sort of like each other, and talk to people who also decide about our fundings, but who might also want to come to the next conference. So maybe we can, if people are interested, maybe we can take this towards the end of the conference. I would suggest that.
But this is a relevant question. We know from the very beginning, because the naming of the conference series was exactly directed in this.
Exactly.
We did not always fulfill, of course, the program that we had, but I think we can work on this. So the idea is there from the beginning. Yeah. Why caring?
But I think we might still have talks coming that would feed into this question. So maybe we should do it in the next session.
And we can change it also to why and when caring, because today we learned also that it's when is also the important part.
Can I make maybe one remark on this topic? I mean, I've been in review panels also for James Webb, and the argument is always AGB stars are not important because they are a few giga-years old. They cannot contribute. And that's, you know, the bias in their minds. So, how to get rid of that bias. I mean, the lifetime of an 8 solar mass star and a 15 solar mass star is not that different. Right? And the more 8 solar mass stars born than 15 solar mass stars. Yet this argument of time is what you see again and again. That's what I see when I read those proposals. And yeah, that simplicity is difficult to get rid of, it seems.
Is that also what brought us from being 245 people at the conference to 100? The fact that we cannot answer that question?
Maybe, because, maybe those people will not come to the next AGB meeting. Maybe they want to download a grid of predictions they can use in their models. and they do not necessarily care about the details. It is what this community can provide to them. They don't necessarily want to know how, dust grains stick to each other or, all the details that are we discussing right now. They want to have the big picture from the AGB star community.
But I agree, but I also disagree, because at Chalmers, for example, we have this dust project where we're talking to high Z people, and I mean, in our group, and we even have someone from chemistry who's really confused about the language that we use. But even as astronomers, and we kind of come around, well, maybe Theo, you can say more about this, because I have never managed to go to the meetings really, but for other reasons. But I think it's often a communication issue, and there is a lot of overlap. And sure, they don't maybe have to go to 4 days of talks on the details of AGB stars, but I think it is also, so we can't as a community sit and say like, but we are so important, and then get annoyed with high Z people not happily coming to our meetings and taking in all these details that sometimes can maybe be overwhelming even for us if it's not right on our topic. So I think if we want to stay relevant as a community and really be relevant, it's also our responsibility to translate what we do into something that is accessible to the other people. So yeah, that's why I agree and disagree.
I mean, for example, we discussed optical constants and opacities. Just with you and Angela made a few remarks on that. I mean, if you change your optical constants, maybe you change whether you use me theory or hollow spheres. Your opacity can change by, so say pessimistically a factor of 10. It's a factor of a few, and that translates immediately into a mass loss rate, which will translate into dust production rates, which will influence exactly this point.
Which will make your galaxy person panic about their latest publication.
So a high Z person would not necessarily be interested in, whether optical constants A are better or not. We should somehow find that out and then make the best possible predictions.
Yeah, I was just going to make the point. So, I mean, part of this question that you asked is how do we get them to come to this meeting? But I think probably the better thing to do is to get us to go to their meetings. Because then, we can come with a message and try to make it clear about why it's important. And I know I've been to a few meetings in other fields, and sometimes I'm the only AGB talk there, and people will come up to me and be like, I had no idea that AGB stars could do that. And so I think it's a matter of outreach to the community.
I absolutely agree. And whoever asked this question was trying to include all the relevant bits, but then actually you started with your talk. So I sort of just sent it off. But yeah, I agree. We should try to sneak into other meetings and with confidence submit talks on AGB stars. And even if we don't get the talk, if our funding allows, we can still go and listen to what these people talk about and pitch in and coffee breaks or comments afterwards. I agree.
I would also say that when it happens that you work with them, you realize that they have a really poor resolution in things, so that sometimes I have the feeling that we overestimate our uncertainties with respect to the other things that they put in their models. An example, for example, is supernovae and their dust production, or retrieving star formation history from AGBs. They sometimes have a poor resolution. I mean, they are not really sensitive on our changing in, for example, mass loss prescription, because they have to fit a large CMD with many phases, so they really lose the resolution on things on which we are discussing from ages. And so probably if we go to the other conferences and pick up the things on which we are agreeing, and there are, I think, something, or the ones where we have smaller uncertainties, then we can go much more clearly to them, and probably it could be a good goal for this kind of conferences to put some pillars of and and go ahead.
Just can I add one final thing? Because I think what's also very difficult here is to step out of our own world and what we think is important. So, for example, I can get really, really excited about measuring the width of a detached shell and what this might tell me about this. And I could talk, I mean, we're going to have a meeting this afternoon about something like this. But I can really understand why someone who looks at a red dot in a high redshift universe does not really want to hear about this. So to sort of step away from what we think is really exciting and important and sort of understand what is useful to the other group of people I think we sometimes underestimate how difficult that is. And to make a presentation that also communicates this is really, really difficult. So something I think we can also learn to do better.
Yeah, then it really approaches outreach. So I think the word that you used it's a kind of outreach. It has to be popular. And therefore, I was happy to see a beautiful RSL on the ESO calendar. It's also outreach. It was in November, I think, or October.
Yeah, actually, yes, the ESO calendar as today asked Dore. No, actually, okay, now I talk to you from the other side because I've been in a lot of panels. I've seen a lot of presentation of people advertising. Also at ESO, we have so many people coming and presenting everything. Actually, I think we do quite a good job at presenting why people should care about what we do. Most of us always start by saying, that's the reason why you should listen to this talk. And it's open to everyone. While actually there are the people, now I'm sorry, maybe I will be unpopular, but the people from the exoplanet community, they just start and speak about, oh, there is this exciting exoplanet. And I'm like, yeah, it's 1 of 1,000. You discover 100 every day. Why do I care? So I think there we do a good job. I mean, that's my experience.
But isn't the common ground then that we take our example of AGB stars to trace the chemistry and the physics? Chemistry and physics are the same everywhere, but we have such a good laboratories to see how they combine and disentangle these things, and that we use our own AGB laboratories to go to the basics of the understanding and bring that basics then to the other communities.
Yeah, I think we are doing a good job. And actually, I hope that the young generation will keep doing it there.
Can I just add also, oh, sorry, did someone have their?
Go ahead.
Okay, thank you. So one of the questions I think where we can pull the galactic community in is the contribution of AGB stars, singles and binaries to galactic chemical evolution modeling. Back, I think a few sessions ago with the same conference, we had sessions on how our eels affect GCEs, and a lot of work in that space there's a big gap, and I know people like Amanda and others, and including myself, we're trying, is the effect of binarity on the eels and how that then goes into feeding galactic chemical evolution models. And I do vividly remember sessions where we had people from stellar populations and galaxies in the Why AGB stars care. So I think that's one way. The high Z galaxy is probably, as Martin said, it's a harder angle to go to because how do you find AGB stars there? But I think this angle is one. And the other one is the origins question, which is the very start of carbon and pre-solar grains and etc. I know that happens quite a lot in NIC and Nuclei in the Cosmos kind of conferences, but I think that's another angle to bring out some of the other people from other fields into the AGB stars. So the origins angle is something I think we've also maybe sort of ignored a little bit, but yeah, just.
So actually, that was a good lead into what I wanted to say, which is, there's nothing stopping whoever the SOC is from reaching out to find people to bring us and have them as invited speakers, have them coming with a specific agenda. And I get that that's hard, but I remember, and this was an asymmetric planetary nebula meeting, which is pretty specific. But they brought in someone who was specifically more of a binary dynamics person than anything to do with planetary nebulae, and it worked really, really well. And I think that's what you were getting at with, there are people that we can bring in. We just have to find the way to figure out how it fits well and find the right person. And it really helps if the person that's invited has a reputation of being a good speaker. Just saying.
Matthias, can you go to the next slide? I'm skipping the last one because it's my question, and we can put it on Friday if you're really interested. The second slide. So there is, I will start. It's a question to Lionel, including PAI lets two models that can account for many properties of J-type carbon stars, lithium abundances, and so on. But you have to add strong overshoot at solar metallicity. Of course, not all C stars are J-type, so the extra mixing cannot be present for all the stars. Is there an idea which physical ingredients determine the strengths of the extra mixing or not?
Well, the answer is no. That's puzzling because the models we developed, they show that we tick a lot of boxes to reproduce the J-type stars, high lithium, a low C12 over C13 ratio, no S-process elements. Also in terms of the nitrogen isotopic ratios that fit some peculiar grains. So it really ticks a lot of boxes. The thing is that to trigger this injection event, we indeed need a very strong mixing at the top of the thermal pulse, but not all stars go through that J-type phase. So why only a few eventually have this proton injection and would look like as J-type stars, and the majority of them won't? We could not answer. This is in the paper that we are just speculating. Well, there are many aspects that can influence the mixing processes, and I think that's a more general question. How can we calibrate the mixing? Because there are various mixing processes available in stars. There is overshooting, there is thermohaline mixing, there is rotationally induced mixing. What is the role of magnetic field? All these things are poorly understood, and well, we need hydro simulations, but even though, I mean, we should not believe 100% the hydro simulations because they have their weaknesses as well. So at the moment, we're just left with 3 parameters and we just explore them. But I cannot answer you, Hans. I don't have an answer why. Or maybe these injections are not the cause of those J-type stars. Well, it just fits the data, but maybe a different origin. But nobody before could find a site or circumstances that could reproduce all these chemical anomalies.
Yeah, but so that mixing that you need, I mean, mixing is in many phases of stellar evolution an uncertainty in the models. Just any zone between a convective zone and a radiative zone is problematic. But here it is really on-off, and so the physical ingredient which is missing, are there ideas about the physical ingredient that are missing? Is really the magnetic field strength or the differential rotation, whatever, or is it there are no ideas about what physics is really missing?
Well, it's turbulence because, well, you deal with convection. So as soon as we deal with turbulence, you know, it's even hydro simulation cannot resolve it. So yeah, it's we try to find yeah a culprit for that, but we could not. Yeah, what triggers mixing? Well, rotation can influence depending on the coupling between the core and the envelope. All those things are known, and are the magnetic field developing at this in these shear layers? Yeah, we are missing some physics. So we're just testing with very simple parametric models at the moment. Yeah.
Yeah, and just to add, there is not only this J-type star issue at high metallicities that show this potentially this PIE, that need this PIE event, because the hybrid stars, so enriched both in R and S elements, have been uncovered at lower metallicities, but now that they are looked for basically at every metallicities, they are found at very close to solar metallicity, minus 0.5 in Fe average. So there is a bunch of stars here at close to solar metallicities where potentially this PIE has occurred, but indeed, so not only the J-type stars, which are, of course, very remarkable.
Yeah, I think it's also a broader problem. I mean, if you look at some of the post-AGB stars and the diversity, I mean, there are post-AGB stars like the one that Devika found that appears not to have had any third dredge up, and it's of a mass, 2 solar mass, fairly low metallicity. They should have had it. So why not? I mean, I think that this is coming down to, I think, our understanding of convection in stars and mixing, even beyond pi events or proton ingestions. They're all got to be linked, and there's something there's a diversity that we can't explain at the moment. Something is driving it. And I don't know if it's rotation, actually. I'm a bit unconvinced about rotation. Anyway, I don't know either, which worries me, anyway.
Be worried. It means there are some exciting questions to answer. Okay, shall we go to the next one, which is for Amanda and Lionel, actually, to elaborate on the rapid rise of carbon relative to S over iron in many nucleosynthesis models. In most cases, the models become carbon-rich after only a few thermal pulses. Sophie briefly addressed this in her talk with the observations, but could you explain from the modeling perspective why this happens and whether there are any ways to mitigate or avoid this behavior? Who wants to start?
I'll start because I have been thinking about this a little bit. Especially, I remember seeing Shreya some of your papers in 2019. And yeah, I remember I was quite confused how these stars can become S-process rich without becoming carbon rich, because the models do show that. So I don't know. I mean, I think that again, looking to post-AGB stars, there are post-AGB stars that show enrichments in oxygen. So Megna's star, which doesn't show an enrichment in oxygen, is actually what we predict. We don't actually predict strong enrichments in oxygen, but stars, some of them are clearly being able to do this. And I wonder if it's more, I mean, people have talked about mixing into the CO core. I'm not sure, maybe. But another way, I mean, we model these stars in one dimension. The thermal pulse is clearly not a one-dimensional thing. Maybe we don't quite, and at the moment we don't get much oxygen because the carbon-12 alpha gamma reaction just doesn't have time to make much. But what if the thermal pulse cycle isn't as we predict it quite? So maybe if it ran a little longer, we could make some oxygen. And maybe there's even some diversity in how long that could take place. And so that could be one way of mitigating it. And even if we look at oxygen isotope ratios, it seems there is an enrichment in oxygen-16. And this is work, I know Falk talked about that a long time ago, and that was one of his initial motivations. So again, it looks like there's a diversity maybe making oxygen in these stars. And maybe that's where some of this is coming from. Or maybe the more metal poor stars are starting alpha enhanced as well. So then it's harder to make a carbon rich star. So you have maybe those two things working together. That's some thoughts. Lionel, if you have.
Oh no, I agree. It also, well, the enrichment, it depends if you have that. It's a good point, the metallicity, the initial metallicity, because you have nothing at the start and you inject a little bit, it will show up. If you already have some of these elements like carbon already in the envelope, the dilution factor will be different. So it might be different from species to species. That might explain why they don't rise at the same rate as well.
Sophie? And then Hans.
In that respect, so we had a look this morning at the Wittgenheit diagram, you know, these two mass diagrams separating very efficiently and in a reddening-free manner, the carbon-rich from the oxygen-rich stars. And at some points, it was shown there where the evolutionary tracks were shown on this diagram. And I thought it would be extremely interesting to see, actually, really, to really see when the tracks predict the star to become carbon-rich and how large is the discrepancy in this diagram. I think that would be an interesting point, and then maybe help us to focus and to try to address this problem. And maybe indeed, Amanda, it's on the oxygen the problem really is on the oxygen abundance, which is extremely difficult to measure in our stars. And so we should try to address that. Yeah.
Yep. Indeed. I mean, we have so many oxygen-rich stars where this, so it's the S stars, and now that we are detecting M stars with S process signatures as well. So it means, yeah, all these O-rich AGB stars that we keep talking about, we saw the populations insanely. And if we cannot explain the rates at which, yeah, this enrichment is happening, for it's really alarming. So, but yeah, as Sophie mentioned, observationally, it's very difficult. The oxygen abundance, the carbon abundance is a bit easier. So yes, it could be that our C over O ratios observation-wise could also be off. But the molecular signatures clearly say if it's carbon rich or oxygen rich. So that should be one thing easily. Yeah.
I think for the post-AGB stars, oxygen is easy to measure because it's just atomic lines. But I wanted to make another comment is that, in fact, today we heard very interesting talk about chemical evolution. And you see that the diversity is quite large at a given as an initial composition. And so we never take this into account, the diversity of the chemical composition to start with, but that's a lot. I mean, the scatter is quite a large fraction. So it can very well be that some objects were born slightly different, and that has an effect on the final abundances.
So that's our heliocentric vision, that we take the solar abundance and we scale it down. It might not be the case. Yeah.
Actually, Hans, I have a project, a student who might work on making some models next year, because even at solar metallicity, if we look at the isotopic ratios in the ISM in the nearby solar neighborhood, we see variations even in nitrogen 14 and 15 and carbon 12, carbon 13. So, and that's at solar metallicity. So we know there are variations that we don't model. But anyway, again, it's an opportunity. Let's call it that.
So we have 3 minutes, which is probably too short to go through this one. So what I suggest is that I put all these questions back, because not all of them are in Slack. And then depending how many do we get for the second discussion, otherwise we can follow up here. How does it sound? Democracy? Okay, or you can vote also for the one most relevant to bring it up. Thanks a lot to all of you. I think this was very nice. Yeah, we will continue to discuss those. Reminder to myself or to whoever is in the SOCs next round, make us longer discussion session.
First test, yeah.
I think the round room worked nicely.
Hello, everyone. My name is Thaisa Danilovic. I'm currently at Monash University in Australia, and I'm going to be talking about lifting the veil with observational astrochemistry. So this is very much complementary to Marie's talk earlier, but now looking at the observational side. So my talk roughly divided into 2 sections. First, molecules, and later, dust and dust-adjacent things. So before I jump into the new results, I just wanted to remind everyone that we can learn lots of different things from molecules. We can get mass loss rates, so for example, commonly from CO, radiative transfer modeling, and this lets us characterize the second stellar envelope, understand density, temperature, etc. We can find, of course, molecular abundances and distributions. This tells us on a basic level, what is the molecule doing? Where is it? Why? Why is it there? But depending on which molecule, we can also learn about the structure of the second stellar envelope, and not just from CO. And if we have, some isotopologues, we can get isotopic ratios. This can help us trace nucleosynthesis or perhaps the initial conditions, depending on which isotopes we're looking at. And there will be signatures of binarity. So before I get to the binarity part, which is what this session is about, I also want to remind people of some earlier results where various groups have looked at trends with different mass loss rates, so high mass loss rates versus low mass loss rates. So for example, it was found for all three main chemical types that SiO is less abundant for the higher mass loss rate AGB stars, probably because there's more dust. The dustier stars have more mass loss. The SI is in dust. Another example is that for SO and SO2, we found really different distributions for the low and high mass loss rate stars, where the low mass loss rate stars, these molecules are centered on the star. High mass loss rate stars, the distribution peaks further out in the envelope, and this has been confirmed with ALMA as well. We can see a bit of structure. Excuse me. But this is also something we can use as a kind of initial diagnostic if we don't necessarily have a mass loss rate. Does this give us an indication, because this is just a direct observable if we're using ALMA, does it give us an indication of should this have a high mass loss rate, should it have a low mass loss rate? And I mean, it's not concrete, but it did help us identify that a distance and hence mass loss rate was wrong in one of our stars, which we were able to then correct. And then there's a few other examples, which if you want, you can ask me about later. So we've seen many of these images before. ALMA, not only ALMA, all the high resolution telescopes have allowed us to see all sorts of asymmetries in the circumstellar envelopes of AGB stars. And I've shown some spirally things here, ranging from super nice spiral to chaotic, probably spiral mess, we'll see. But it's not only spirals, we also get some other shapes. Ta-da. And some of these are probably caused by binary companions, like the spirals. Some of them, it's less clear what is going on. Questions we all want to answer, or at least I certainly do. So this mostly CO so far, but this is not the only molecular tracer. So Mehdi talked about SIN and W Aquilae earlier, where we found a weird wedge of SIN around W Aquilae on the opposite side to where the companion is, which is actually an arc. But SIN forms through UV photochemistry, so therefore for this to have formed, the long orbital period, which was already known to be long, had to be highly eccentric, otherwise this doesn't make sense at all. And this result is also corroborated by the SIC and the NS detections. So in general, the idea is something like this. So the orbit of W Aquilae is pretty edge-on, so now we're looking at it face-on, and the observers are to the left. But the star, when it enters, so when the companion star enters the dense inner region of the AGB, wind outflow, it's able to trigger photodissociation, photoionization, sort of leaves a path of destruction behind it. These newly liberated atoms, ions, etc., interact with each other and whatever they bump into and form unusual molecules, whereas initially everything was locked in, for example, CO, H2O, maybe HCN, SIS, from the closer to the star. But with this source of UV, we can make these more exotic species. And then the companion moves on, and the exotic species like SIN expand outward as the wind is in general expanding outward, and hence what we get to see. And we don't really see any SIN near where the companion is today, which is just slightly further down on this diagram, because the wind there is much less dense than in the dense inner region. And chemistry in general, even when we're just talking about photodissociation, goes as the square of density. So we just have less, it's not detectable. But it's not only SIN that's interesting in telling us things. NS is another tracer of photochemistry, mainly because N, also in SIN, is normally locked in N2, which is very sturdy. So you need to destroy that to make interesting N things. And so NS was detected in IK Tau in the ALMA survey that Lane has. And then also in that same star and same survey, we have quite clumpy NaCl, which a former student deprojected. It's clumps that kind of look like a spiral, which is weird. What's interesting though, is if you superimpose that with the continuum, and the faint continuum emission actually kind of traces the same asymmetric shape, whatever it is. Also, there's evidence of photochemistry in CW Leo, as Mehdi and Mark have talked about with the HC3N. There's also SIN detection, so the Turner detection was single dish, so like unresolved, but Patel was with the SMA, and there's some interesting asymmetries there. It'd be nice to analyze in more detail. Amal has NS in II loop, which also has this spiral structure. So that's kind of two pieces of evidence that there's a companion in there. And of course, there's shells around CW Leo that people have been trying to explain for a long time. OH 30.1 minus 0.7 has NS. It has salts, not only NaCl, but also KCl. A lot of detail about the salt in my paper if you want to know. But I will focus a little bit on NS shortly. And this is not an exhaustive list, of course. So NS in OH 30.1 was detected with ALMA band 3. So unfortunately, relatively low resolution compared with what we might be used to with ALMA. So we can see that the emission is off-center, and that's pretty much all that we can see. So we need some higher resolution observations. But what is interesting is, it is off-center in this direction. It's hard to point. And in the continuum emission with ALMA, there is this weird blob off to the north, and that is actually exactly perpendicular, or as exactly as our data lets us tell, to the offset with the NS. So this is sort of similar to what we see for SIN in W Equilea, but, well, poorly resolved. And, it's not clear if this is really meant to be edge-on. It could be rotated. It's not that well constrained. So more observations would be really interesting. We could learn a bit more about the orbit of this star, because this is a pretty weird star. It's a intermediate mass AGB star. This looks better on my computer screen. Sorry. Unfortunately, it's towards a star-forming region, and there's a lot of contamination, even with the ALMA observations. So here in the AGB star, we have no resolved outflux except for in some of these channels up here, but all the rubbish around that central round bit is not part of the AGB star, and the diagonal bits is not part of the AGB star. It's very frustrating to analyze because you hope ALMA gets rid of your ISM nonsense, but sadly not fully in this case. But what was interesting is that, we did fully resolve and didn't resolve out the CO envelope here. And also, if you can kind of tell that the contours are stacked very close together around the edges, is that this represents a very abrupt period of high-ish mass loss rate. I mean, 10 to the minus 5, maybe 10 to the minus 4. I'm leaning more towards the lower side of that, or in the middle of that range. And this high mass loss rate started like a bit under 3,000 years ago, which is pretty weird. But this also explains why this looked weird in unresolved observations, because the CO2 to 1, which is what this is exactly the same size as the 3 to 2, 2 to 1. Yeah, they're the same size, because it hasn't expanded far enough. But I was talking about the continuum, and I can overlay it like that, and that looks awful, so I'll jump to the next bit already before we zoom in. And you can see that this weird ejector blob kind of corresponds with this weird dimple in the CO. What does that mean? Not sure. If you have any ideas, come talk to me. Or, look at the paper. But yeah, so there's something going on there. Binarity is probably related. This blob seems like it's some cold dust, but how it got there and when it got there is a bit mysterious. If it started when the intense mass loss started, it was moving faster than the CO is. Okay, so more about dust and other continuum emission. So to set the scene, we all know that there's dust around AGB stars, but what maybe some people don't necessarily appreciate is the scales that we're dealing with here. So starting on the left with the Herschel-Pax image of coal dust at 70 microns, I have also added some CO, which is most, but not quite all, of the CO around the star, and then the ALMA continuum, where we resolve the companion as well. And you can see that we're looking at, very small scales up to very large scales. And like this is quite a range. And this is really a recurring theme in AGB stars. For example, it's also quite hot near the star, quite cold far away from the star, etc. So sticking with W Aquila, we have the ALMA continuum that was also on the previous page. And this VLT sphere image, which we use to pinpoint the location of the companion, which is a main sequence star. In case you can't see it too well, it's roughly where the arrows end there. What was unexpected was that we detect continuum, like 5 sigma detection of the continuum at the location of the companion. And if we we performed a uniform disk fit to the AGB star. If we subtract that, also lower the resolution a little, you can see a little bit more clearly, just, because we increase the sensitivity. You can see there's sort of like a tail of dust maybe behind the companion. Right, so an F9 star, like a main sequence F9 star, absolutely should not be detected in ALMA continuum. So that was odd. Moving on to the other known binary, the atomium sample, is pi1 GRU, which we've already heard a little bit about, and I think we're going to hear more about later on as well. So this is one where in atomium, we detected this inner companion. So this image that I'm showing now is from the most extended data that we had. But if we also look at the combined ALMA data, and we had lower resolution as well, we can see a tail of, I'm going to just call it dust, kind of spiraling out from the star. We no longer resolve the companion, but we see this dust, which was resolved out in the extended data. And what's interesting about this is that it corresponds very well to the tail of dust seen in scattered light in our contemporaneous sphere observations, which, if you want more details, you can see Miguel Montajes' papers. So in case you don't believe me, you can also put the contours on top of it, of the continuum. So yeah, it's quite a nice match there. So this is another star where we know there's a companion and there's a tail of dust. What's going on? So I said before, AGB envelopes are large. The gas is relatively dense in the inner regions on the scale of stuff in space, and relatively rarefied in the outer regions. The inner sound speed is about 3 kilometers per second, depending on the star maybe. The outer sound speed is much lower, also depending on what you mean by outer. Any companion that you put in this envelope, anywhere that's relevant for any kind of envelope, stellar wind, circumstellar envelope interaction, is going to be supersonic. Like, the orbital velocity has to be higher than the sound speed. Otherwise, it's not orbiting. So what happens when you have supersonic motion? We have shocks. What happens when we have shocks? Well, hopefully, I will convince you in the next few slides that we get dust formation. Hence the tail of dust behind the stars, the companions in our observations. So if you can pretend that this is a video that's rotating. No, I mean, I thought about the effort of putting the video in, and this does actually show all of the information. On the left, we have, this is just no particular star model. We have an AGB with a main sequence companion, 5 AU separation, circular orbit. On the left is a density slice, so we see these spiral shocks, which are common in like all of these simulations. This isn't new. On the right, thanks to a routine written by Lionel, we call the dust nucleation rate, which is where dust forms because of these shocks. So in this is phantom smooth particle hydrodynamics. We don't have pulsation-enhanced dust formation, like that physics is not in the model. We just have dust that could form when something else happens, and in this case, when we have shocks from the companion. So you can see here, we still have a little bit of dust formation out at 50 AU, or maybe you can't see that. The numbers are a bit small, sorry. But 50 AU is this marker. Another example is this one. So this is a 20 AU separation model. Same idea. Our spiral is less tightly wound, of course, because the separation is larger, but we still have, well, actually even more pronounced, we have like a tail of dust formation around and behind the companion. So, okay, so what? Is this significant? Well, seems it is a bit, but we do need to do a little bit more work to get hard numbers out. But what we essentially have is two modes of dust formation. So on the one hand, we have the traditional stellar pulsations. You know, we heard about this from Suzanne, Bernd, Joachim. Dust forms in the wake of shocks in their simulations, you know, drives the wind outwards. But then we also have dust forming in the wake of the companion. So depending on what companion, like where it is, its orbit, this might not have much effect. So for W Aquila, this probably actually has a pretty minimal effect. The companion is currently 200 AU from the AGB star. The fact that we see dust is great, like that's quite interesting, but it's not changing very significantly, like the dust to gas ratio. So at that distance, it's not changing the mass loss rate or anything like that. However, if we have a companion closer to the star, then some of that dust is forming in the wind acceleration zone. So in this region where we would have infall, which in the models is out to maybe 10 AU, depending on the star, on the mass, some of that gas that would have fallen down could then be intercepted by some of this additional dust that is formed from the companion. Yeah, so we can get more of the gas leaving, which can potentially increase the mass loss rate. Yeah. So I put this slide in because I have mostly been talking about binaries. And you know, I've said that a lot of these shapes can be explained by binaries, but we're not seeing them, right? I use W Aquila and Pi Gru because we know that they're binaries. But then we have other stars that have similar, you know, structures in the CO or whatever, and some of these molecular traces, but we're not seeing the binaries. So one reason we're not seeing the binaries is probably because it's making dust to shield itself, but also because of an observational bias. Right? When we look at, like when we use telescopes, we want to look at things we know we'll see or hope to see. Right, so we look at the brighter stars preferentially, you know, especially when we're using something like ALMA, like up to now, right? We want to see stuff, and so we choose the brightest stars, which have the highest mass loss rates. If binarity increases mass loss rate, that means we're biased towards looking at binary stars. Right, this is one of the biases that the NEST survey that Sundar and Peter talked about earlier. Is working to fix, right? So the lowest mass loss rate stars, they probably aren't binaries, but they're not quite been counted correctly, statistically speaking. And a lot of optical observations want to ignore the dusty things because that's getting in the way of the optical observations, whereas we submillimeter people want to look at the dusty things because they're brighter. Also, I mean, the binary fraction should be like 50% and higher, depending on the mass. So this is not unreasonable, I think. Feel free to argue. So moving away from dust and a little bit just to other parameters in the stellar continuum. The atomium sample, we fit uniform disks to all of the stars. There's 17 stars, but in these plots, there's usually 16 points because 2 were a bit too far away and faint. This plot I'm showing now is I've called it monochromatic luminosity, essentially how bright it was at 1.2 millimeters versus the uniform disk radius. And those dotted lines that I've plotted divide the semi-regular variables in the bottom left from the Myras and also the red supergiants in the top right. So basically all the Myras are 2 AU in radius or higher, and the semi-regulars are a bit lower. And there's a bit of, that's probably not exactly the right line. It's a bit blurry, but it's something like that, which is interesting. Looking at these two properties and comparing with the pulsation period, we also got some odd results. For pulsation period versus radius, there's this trend, especially for the Myras, starting from 300-day periods, with the possible exception of Aracule, which is weird and may have recently had a thermal pulse, depending on who you ask. It seems to be behaving more and more like a semi-regular. Yeah. But on the other hand, when we're looking at the monochromatic luminosity, the trend, there is no trend until we're like above 500 days. And there's this frustrating gap here, so I couldn't really tell you where that starts from. But W Equale here has 490, and these are much higher, like 600-700. These are the WX Pisces and V1300 Equale, and the orange ones are the red supergiants. So together they somehow form a trend. There's no trend here. If you think there's a trend, it's just because the Myras are slightly larger than the semi-regulars, and semi-regulars have lower periods, but there's no significant trend. And, you know, while talking about periods, if we also look at the mass loss rates, we see there's below 300 days, there's not really a trend. There's this empirical relation from Vasiliadis and Wood, which kind of fits, but then the second part, the flat part of that does not agree, but we actually have this nice curve in the carbon stars. It'd be nice to interrogate that further. Also interesting to point out that these mass loss rates are all derived from radio transfer modeling, and also with new Gaia distances, so they're more accurate than like in this citation because the distances are better now. Anyway. Astrochemistry, I hope I've convinced you that it's cool. We want to look for binaries through molecular signatures, as well as just, you know, looking at the CO distributions, which has been ongoing. Then we can more clearly pinpoint what's going on with, you know, binary stars. How much are they enhancing the dust formation? What else are they doing, maybe? That's the general idea. And I will leave these QR codes up, but before I do, I just want to make an announcement that coming soon will be the Cool of Old Stars newsletter to replace the defunct AGB newsletter. Thanks to Miguel Montajes and me. Yes, we hope to have the form ready, but not quite. Coming soon. Yes, I'll go back.
Thank you very much, Thaisa, for this amazing talk. I'm not objective at all, but so is there any question for Thaisa? Yes.
Thanks for the talk. Also, thanks for bringing back the newsletter. A question with respect to the binary-induced photodissociation and its effect on the molecules. Which radiation field are you sensitive to? Because an F9 star is maybe not very hot, but do you?
Yeah, it's basically the sun. So Maddie's the one that did the modeling for that. Yeah. But yeah, in her initial paper, we had the sun, or yeah, it was the sun, white dwarf, red dwarf, coming soon-ish, probably next year. We're looking at more different stars that could be like plausible companions to see how different that will be and how much we can constrain what something is. So in the OH30 paper, we had a discussion related to the NaCl versus KCl ratios. It was kind of quite technical chemistry-wise, but in terms of what could and couldn't form based on the energetics. And yeah, so it seems that
it's purely the black body radiation of the star. There is no accretion disk or no just a, yeah, okay, because there must be some accretion disk with also quite some luminosity, no?
I mean, this is unclear. If it's far enough away, and like, okay, for W Equale, during periastron, it's whizzing by quite quickly. I'm not sure that there's, well, maybe there's a temporary accretion disk. Maybe that does have an impact, but that wasn't considered in the chemistry. And where it is now, there shouldn't be an accretion disk.
Okay.
Go on. Yeah.
So we have a question online for PTH Luna. First, he's a nice Taisa, and he asks I'm curious if the spiral choke are powerful enough to modify the size distribution of grain produced in the regular wind. Example, shattering them or triggering coagulation.
Maybe. I'm not sure. More modeling required. But yeah, this is a question we want to answer. We can sort of look at the stochastic grain size distribution, but it's also a basic implementation of dust formation, so it's like more work needed.
Okay. Yes, Jaime?
Coming back to Hans' question, in some cases there is an accretion disk. For example, in the case I exposed yesterday of T-Draconis, there has to be an accretion disk. Also, it's important to take account the dust attenuation because of ultraviolet emission can be very attenuated by the dust. So you have to take also into account this attenuation over the distance in the radiation field.
Yes.
Hi, Sundar Srinivasan, Area UNAM. Could you show me your mass loss rate versus period plot again, please?
Oops. The referee made me remove the appendix, so please look at the archive version of this paper.
Cool. Yeah, we have a similar plot in the Wallstrom paper.
Yeah.
Okay. Yeah. Thank you.
Yes, Theo.
Hi. Cool. Thanks for the talk. So when you show these observations of OH30, whatever is the rest, can you say anything about what mass loss rate? Can you set upper limits on the mass loss rate that it would have had before?
So, sort of. I tried to do some radio transfer modeling of this, like it's not in the paper. The mass loss rate I got was a few by 10 to the minus 5. I forget the exact number. K's model from dust is 10 to the like 2 by 10 to the minus 4. So that's like an order of magnitude difference. The lower mass loss rate is probably correct because probably there's extra dust, formed from the companion. I checked with the size of the CO versus like the photodissociation models of Mariam and so forth. At that size, if it was a few, I want to say 2 or 3, it's in the paper, by 10 to the minus 5, if that was an earlier, lower mass loss rate, we would not be able to tell. This is roughly that size of shell, but also because it's truncated, it's not, the edge of the shell is not from photodissociation. It's from being newish.
Sorry, I got very confused. So
if you think there was a lower mass loss rate and then suddenly we have a high mass loss rate,
yeah, exactly.
the lower mass loss rate, we cannot tell if there was a lower mass loss rate if it's lower than a few by 10 to the minus 5.
And the present day mass loss rate then?
Well, it's in that range. I mean, it's a bit hard to tell.
So it's not a huge, yeah.
Yeah.
So why is SIN, as opposed to all other molecules, I guess, so efficiently produced when the companion is at periastron?
That's a good question. So part of the answer is what I said before about N2 being very sturdy and needing to be destroyed to form it. We also need to liberate the SI from somewhere. But for W Aquilae, SIN gave us the nicest data, whereas SIC was just a bit noisy and NS was a bit blobby in the sense that it was more on one side than the other for some reason. On the other hand, I showed the OH30 data, which is not great, but I also have not shown OH26.5, which is a theoretically similar star to this. And then we have a lot more NS, and in neither of these do we have SIN, and I think it was covered in at least one of them. So maybe it depends on the other chemistry of the wind. So because W Cooley is an S-type star, SIN was a bit more favorably formed, whereas in the oxygen-rich stars, maybe NS is more favorably formed. Yeah, this is not 100% clear from the chemical models either, I don't think.
Very last question, maybe online, and then we started to get rid of time, so we ask question on the coffee break or online. Thank you.
We have another question online of Joseph Giron. Did you compare the size difference between MIRAS and SR with those from optical interferometry?
The sizes, was that? Did I compare the sizes? Yes.
Size difference.
Yes, it's a factor of about 1.2. Same result Valter got, but we had more stars. And only one epoch of observations.
Okay, so thank you very much, Thaisa, and let's applaud our speaker again. So now we have the coffee break, and one thing, please, I'm talking on behalf of the organization committee. Please tell us if you expect to not attend to the dinner conference, and if you registered. Like this, we know the updated numbers for the people at the restaurant. Thank you very much. And the lunch for tomorrow too. Thank you.
Can folks there see my slides?
Stevie, are you online?
Yeah, can you hear
Steve
me?
or Stevie?
Steve.
Stevie, okay. We are just testing for the speaker after you if the presentation is working, so that's why we interrupted your share screen. After I just tell you when you can share again. Thank you. You can share again your screen. Thank you, Stevie.
How does that look? Can you see the slides?
Yes, we can, Steve.
Thank you.
How's it going?
Good. How you been, Peter?
Good, yeah.
Okay, could you please go to your seat? We will resume this last session of the day. Thank you. So I'm Lionel Sies. I will be chairing this last session. And our first talk is online by Steve Goldman. It's about equatorial enhancement in the dustiest OHIR stars in the galactic bulge. Steve, are you online?
Yep. Can you hear me?
Yeah, perfect.
And you can see
so
me?
I will give you just a 5 minutes notice before the end of your talk, okay? So you've got 12 minutes.
Sounds good.
Perfect, okay. Floor is yours.
All right, thank you very much. So I'm Steve Goldman. I'm at the Space Telescope Science Institute in Baltimore, Maryland. And today I'm going to be talking about the really dusty AGB stars in the galactic bulge that we think are equatorially enhanced. This is a part of a paper recently published in APJ with Martin Groenewegen, Joyce Blomart, Libby Jones, and Jacob van Loon. And I also want to thank the organizers for allowing me to do this remotely. I have an infant at home, so this really helps out a lot. So thanks for that. So I'm going to be talking about the characteristics of two really dusty AGB stars. I'm going to be talking about some newish VLT Vizier spectra, some diagnostics for circumstellar geometry, and then I want to end with pulsation period. So I'm going to be talking about two AGB stars that we've mentioned a couple times before. First, OH26.5 plus 0.6. This is a source that's been well studied in the past half century. There's been over 300 publications that reference it. And here I'm showing the 10 micron silicate feature deep in absorption. That just means the source is super dusty. This is from Esther Marini's 2023 paper showing Spitzer IRS data. And then also this source has crystalline silicates detected. So as Angela was talking about, this needs to only occur in a high density environment, high temperature environment to anneal these dust grains. The source, as Hans mentioned, is one of the brightest maser emitters known for an AGB star. And it's a tool for understanding expansion velocity. So by taking half the peak separation from the center velocity to either one of the peaks, and assuming the star is spherically symmetric, you get the speed of the material either moving towards you or moving away. So that's really helpful. The source also has a very long pulsation period of around 1,500 days. I'll come back to this. And then lastly, this is an image I think we've seen before from Lane Desson's Nature paper in 2019 showing the confirmed edge-on over density or disk. Now I'm going to show another source that's been mentioned a couple of times that Thaisa was just talking about that shares all of these characteristics as well. These are characteristics we don't see in every AGB star and I think are relevant to this discussion that we're talking about now. So what did we do? We used the VLT's Vizier spectrograph to get mid-infrared spectra of 21 AGB stars towards the galactic bulge. We selected a sample for having really red IRAS colors to be bright and to also have OH masers so we can get at the expansion velocities. And what did we find? For all of these AGB stars, we see the deep 10 micron silicate feature. Also, we have detected crystalline silicates in all but one of these sources. These stars are very dusty and all have crystalline silicates. I'm showing the distribution of these stars on a Gaia projection in the top right. So in this figure, the Vizier spectra in orange. There's also some Spitzer IRS data in black. The available photometry, it's multi-epoch photometry, and these are variable stars. So there is a spread, and those are shown in gray. And then also a 1D radiative transfer model from Dusty is fitted to each of these and shown at the dashed line. Okay, so I also mentioned that we have wind speeds for all these sources. So from the maser mission, this is one of the example, which I've stretched to accentuate the maser peaks. For a sample source like this, we get an expansion velocity around 70 kilometers per second, and that's consistent with kind of our whole sample. You can also estimate the expansion velocity by using these radiative transfer models. As you can see, this model fits the data fairly well. And so from this 1D spherically symmetric model, we get an expansion velocity around a couple of kilometers per second. So there's a discrepancy here. What's going on? So we don't know the gas to dust ratios very well. We also don't know the drift velocity, so the difference in velocity between the gas and the dust. And again, I keep saying these are spherically symmetric 1D models, and so that's also a problem. So what I think is happening in this source and in many of our sources is that they're equatorially enhanced. What I suspect is going on is that the infrared data is probing closer in, where asymmetries are probably more prominent. Whereas with the OH maser, it's probing farther out where water is being dissociated into OH. And so, as has been pointed out by several groups in the past, like the DESTAR collaboration has pointed out that while closer into the star, there's more prominent asymmetries in the CO data, but farther out, the outflows are smoother and more spherically symmetric. So I think maybe that's going on here. I think the main takeaway is that these stars are probably not spherically symmetric. I fit these using the Dust Evolve Star Kit or the DESK package I developed. If you're interested, please let me know. This is great for getting an initial first guess for radiative transfer model before doing follow-up dusty modeling. You can do it across a bunch of different grids, and it's great for large samples as well. I've tried to make it as easy as possible to use, and I'm scooping up new grids all the time, so please let me know if you're interested. And ideally, I'd be using 3D models like Joachim Wiegert's models he showed on Monday, where you can have more of a lever on the different geometries in these stars. But as you can attest, it's quite challenging to make these, especially for large grids. So maybe this is something we do in the future. Okay, I also want to talk about pulsation period. We've talked about it a lot, so I don't have to do too much background. On the left is Peter Wood's foundational paper where he outlined these lettered sequences. And then on the right is from Michele Trabucci's paper, where the important things are that the C sequence is the fundamental mode. To the left of that, you have a couple overtone modes. And then to the right, sequence D is the long secondary period. And if you don't know, the long secondary period has remained a bit of a mystery for quite some time. The leading theory at the moment from Sinzinski et al. 2021, this recent evidence showing these secondary dips in the infrared, but not the near infrared and optical light curves. So what they think is happening is there's this eclipsing binary companion that's dragging along gas and dust in a dense cloud. And as this warm, dusty cloud dips behind the star, you get that secondary dip in the infrared, but not in the optical. While I think this is happening for many LSP sources, this is maybe not the case for the sources I'm going to talk about now. And there's a great discussion of potential scenarios by Goldberg, Joyce, and Molnar in reference to Betelgeuse that I would recommend reading. I liked that paper. So I'm going to set the stage first. This is just some data in the LMC, where the XAGB stars are the super dusty ones, the extreme AGB stars, and then Martin Groeneweggen's very dusty AGB stars and then the Magellanic Cloud are spread in the triangles here. We have the IRAC 3.6 micron data on the y-axis, and then the pulsation period. And this is what we would get for our data if we had data in this filter. We don't, they're very bright. So what I did is I took the model and I put it through the filter throughput of Spitzer's IRAC1 detector. And this is what we would get for that data. As you can see that they're all on the long secondary period or sequence D. You might be thinking maybe these are just fundamental mode pulsators that are super dusty, which would bring them down in luminosity even at 3.6 microns. But when we account for the dust, if we use identical models, but if you take away the dust, this is what you would get. So again, this is synthetic photometry, and I'm taking a model with no dust, but the point here being that even when you account for the dust, it still can't be described as a fundamental mode pulsator. Maybe they've evolved from the fundamental mode, but not currently fundamental mode pulsators. And then I also want to mention that the two sources I talked about at the beginning that share a lot of the same characteristics would fall here, using kind of a similar method with the spectra that are from ESO, I think. So I think the thing, if you take away anything from my talk, it's this. I think there is value in studying the very dusty long secondary period sources as kind of their own subclass, because I think the underlying mechanism for those is different than many of the other long secondary period sources. And if we try to isolate them just based on their periods and being really dusty, I think we'll find a lot more sources that look like this. And I think we'll be able to learn a lot about potential AGB companions. I won't speculate too much exactly about how the LSP is happening because I don't have the spatial resolution and I don't have the time, but I think we can learn a lot from them. I also want to mention that you can't just assume that a long pulsation period means long secondary period, or sequence D. We showed in this paper that I co-authored, the fundamental mode extends to really high luminosities, strangely enough. And as I said before, I'm bummed to be missing this conference. This is a picture that looks staged from our last iteration of this conference, where you can see I'm getting really into pulsation sequences. And this is when I started thinking about a lot of this stuff. So bummed to be missing, and I hope I can attend the next one. I miss all you guys. So I'll conclude by saying I think there's a lot of evidence for equatorial enhancement in these stars because of the 10 micron silicon feature, deepened absorption in all these sources, crystalline silicates in all but one, the big discrepancy between the wind that we model with the infrared data and the radio data, the long secondary period in all of our sources that we have data for. Ideally, in the future, we'd want to build up a larger sample to study them as a subclass. And ideally, we'd have more spatial resolution, maybe something with CO data, PNR, gravity, maybe some kind of coronagraphic instrument on James Webb. So I'd love to pursue this further. Along those lines, I did get a James Webb program approved for 30 hours in the last cycle. We're getting spectra of AGB stars in M31. We're going to have some beautiful spectra from 5 to 28 microns for oxygen and carbon-rich AGB stars. And the kicker is that these stars lie in clusters. And so we're going to have 100 plus AGB stars with beautiful spectra and metallicities and ages associated with each of these. So stay tuned.
Yeah, thanks, Steve, for the perfect timing. So we have time for questions.
Hi, Steve. Lien de Sin here. Thanks for your talk. I had a question on also, you summarized it on your last slide on the wind speeds, where you say that there is a difference between the radio and the infrared data. But don't you mean here that there is a difference between observed velocities in the radio data and predictions made by your dusty code? And
yeah, that's right.
There is an inherent issue potentially with how the wind speed is predicted in then the dusty code, or how the code might be called.
Yeah, I think that's right. As you get to, a couple kilometers per second, I'm not sure that those expansion velocities are even realistic. The point I wanted to make is that we probably don't have spherically symmetric envelopes here based on that, and we need more modeling.
Yeah, okay, thanks.
We have time for more questions. Hans, please.
Yeah, Hans Olofsson. So I seem to remember a paper, I can't remember exactly when, by Peter Wood, when he also saw these very long periods for a given luminosity, and he called it lengthened periods, and he interpreted that as the stars being very close to the tip of the AGB, and they sort of lost essentially all of the stellar of their envelope, and the mass is much lower and so on, and that would lead to the very long periods. So I mean, is that not a viable explanation for these long periods?
Yeah, I'm definitely leaving that open as an option. And Peter Wood also mentioned in his 2000 paper that the LSP is likely from binarity. So he was the first Charlie to call that. But I do think an evolution from the fundamental mode is possible. I'm not rooting that out. And these stars may not be binaries or have companions. That's still a possibility.
Maybe time for last question, if any. No, so let's thank Steve again for his nice talk. And we proceed to our next speaker, so invited speaker, Shazrin Mohammed, who's going to talk about the physics of binary interactions on the AGB, from massless transfer to circumstellar morphologies in 3D. So, floor is yours, Shazrin.
I have one. I'll just press. Can you hear me?
Super. All right. Thank you so much to the organizers for an already amazing conference. I missed seeing everybody over the COVID and things, so it's really nice to see everybody. And it's also nice to see a lot of new faces. So I thought I would keep this talk. I had grand plans for what I would cover, and I would cover everybody's models that I ended up with hundreds and hundreds of slides, and it was serious cutting. So then in the end, I just went back to, I'll just keep it simple. And my goal is really to give some background so that people understand the talks that are going to follow. And so everybody can follow along with what's good, what's going on there. All right. So these are my collaborators for some of the work that I'll show. And just in case I forget to say, Elia Saidi, who's was my PhD student, is now faculty in the US, Philip Podsiadlowski, who was at Oxford and is now in London, and Sophia, who was at Uppsala. All right, so I thought we should start on solid ground, where we know for sure there's a companion. And one of the strongest types of systems that we have where they're interacting, an AGB star interacting with a companion, are what are called symbiotic binaries. So these stars, in their spectra, they have a cool component, that's our beloved AGB stars, and they have a hot component, either a white dwarf or a neutron star, that's accreting from this AGB wind. And that accretion produces a lot of high energy emission, and that high energy photons ionize the material that's lost by the AGB star. And so you see those three components in their spectra. But these are just the tip of the iceberg, so to speak. AGB stars interacting with a companion can produce a whole lot of different phenomena. And some examples, stars can explode because they're accreting from an AGB star. So we have type 1a supernovae associated with the white dwarfs, nova explosions. We have a whole smorgasbord of all of these post-AGB progeny of AGB interactions. I'll talk a little bit about X-ray binaries at the end, and also a lot of bipolar outflows that we have in planetary nebulae. So all of these things at some point have had to have an interaction with a companion on either the RGB or the AGB. And so one of the ways that we can start to think about how they interact with each other is the first thing, gravity, right? You have a companion star there. And so we start with just the Roche equipotential surface. Everybody should have probably seen this. So we can define, the regions where all the material is sort of gravitationally bound to the M1 star, and this one to the accreting star. We can define these equipotential surfaces where a particle can move along without having to do any work. And the Roche lobe surface is where those two intersect and pass through this inner Lagrange point, the L1 point. And this teardrop shape here, we can get the sort of radius from that. We have the Eggleton formula. And you can see that as you go to wider and wider binaries, then this Roche lobe is going to get bigger and bigger. I'll also point out L2, because this is something that people might mention. If material can get out to there and come out, then it will stop, cannot continue to co-rotate, and you can actually form things like circumbinary disks. So that also comes up quite a lot. This is for circular orbit, so there's a bunch of assumptions that go into this, and more recently there's been modifications, and there's a really nice paper where they actually take into account things that we know are happening in these stars, pulsations and radiation pressure and things like that, eccentricity. So I encourage you to look at that. So what happens now as the star evolves, either to the giant branch or AGB, or the orbit shrinks, then the star will fill its Roche lobe, and then it will see, oh, there's a hole somewhere to escape. This material will see, oh, there's a great way to get out of here. And it will fall into the potential well of the companion, and it has some angular momentum, and so often will be accreted via an accretion disk. There are a lot of questions about Roche lobe overflow and exactly how conservative it is, how much of that material really does get accreted by the companion, how much gets lost from the system, how much angular momentum is transferred. And how stable this is. Our stars are convective, they have convective envelopes, and if the star expands as it loses mass, then you can have unstable Roche lobe overflow, and when that happens, you continue to dump a lot of material onto the companion. It can't cope, so it forms a common envelope, and when that happens, the two stars will orbit within this common envelope. If there's enough energy, you can eject the common envelope and the binary can survive, but that energy will come at the expense of the orbit. So you'll have a shorter orbital period. If you don't have enough energy, then the two stars will spiral and eventually you get a merger and just a single star rapidly rotating probably. And the idea here is if you have this kind of mass transfer, the orbit is going to shrink and get shorter. The orbit also, we heard already from Matt's talk, that here in these very close binaries, you have strong tidal interactions, tidal torques. That's going to circularize your orbit, also synchronize it. But so, these strong tides will really tend to get rid of any eccentricity that you might have. So that's Roche lobe overflow. What if we're not filling our Roche lobe? Well, you can accrete from a wind, and this wind accretion was sort of worked out in the 1940s. And the idea is you have this flow coming from infinity, uniform, constant density flow. You ignore pressure, so this was the starting point. You assume your gas moves along these ballistic trajectories. They pass your accretor. This is this dot here, and they cancel out at this midplane, this accretion line, and then the material that's bound to the accretor will get accreted, and the material that's not bound will get lost. And you can define the cylinder where you will actually capture that material. It's been applied to a lot of different things, from X-ray binaries, clusters, like a whole host of things. And you can calculate what kind of accretion rate you can get from that cylinder. And then Bondi extended this now to winds. So our winds are not constant density, they're not pressureless. And he had calculated what happens if you have just a stationary accretor and in a medium. And so he interpolated between those two cases to get what we call Bondi-Hoyle-Littleton accretion. And we can define this accretion efficiency. So how much mass, this is very small, how much mass is accreted versus how much mass is actually lost in this wind. And you can see that it depends. If you have a more massive companion, you'll accrete more. If your companion is orbiting much faster, you'll accrete less. If your wind is moving, very slowly, then you accrete more. So you can see these different parameters in here. Typically, you're going to just, with this kind of geometry, you're going to just accrete just a small fraction of the wind. Your outflow is going to be largely spherically symmetric. This works very, very well and is the case when you have a very fast wind compared to the orbital velocity. Yeah, and this is where it was applied to hot stars with 1,000 kilometers per second wind moving in a rather slow orbit. And the idea is that you won't accrete too much onto the companion and your orbit will widen. So those are the two kind of scenarios, along with our common envelope and tides. And when we apply this to some of the systems that we know, some of the populations that we know have gone through this, they did population synthesis. And actually what they found, so this is, so for example, barium stars, we already heard a lot about this from Sophie and from Pilar already. These barium stars, so this is period versus S-process enhancement. This is eccentricity versus period. And what you see in gray are the models. And in the crosses, those are the observations. So you want to transfer a lot of mass to this companion, which is what you're going to see as your barium star, so that you can see this S process. So you want Roche lobe overflow. That's going to get you a lot of mass. But that's, if you transfer by Roche lobe overflow, that's going to circularize your orbit and or make you enter a common envelope and shrink your orbit. And so what happens is we have this really bad mismatch between the observations and the theory. And we'll hear a lot of talks, I think, coming up about this. Anna's talk as well, Hans's and Peter's. But there are a whole host of these systems, blue stragglers, SEMP stars, post-AGBs, all show the same kind of issue and problem. So when we take our best physics, we can't really match things. And then there's some problems that we're still trying to figure out. Type 1a supernovae is one. I mentioned, either one or both of these stars will have had to, depending on which scenario you want, but the AGB is very likely to be involved and trying to understand what is the parameter space for actually growing your white dwarf so that it can explode as a type 1a. And this is a really good connection to the galaxies for nuclear synthesis and cosmology. And then the other thing we want to try and understand are these bipolar outflows. The idea is that you should have some kind of torus or equatorial disk or something like that, so that when your fast wind switches on, once you've lost your envelope on the AGB, then you have this dense material to confine your outflow, and you can make these bipolar structures. But there are a lot of problems with this. Where do these either circumbinary disks or density enhancements, how do you form them in these very wide binaries? And also when you look at some of these outflows, like jets, from kinematic studies, for example, Eric Blackman, it seems that there's too much mass and momentum. You can't really transfer enough mass in order to account for the mass and momentum that we actually see in these jets. So we need some detailed modeling, and there are a lot of problems, so much so, Joanna, who works on symbiotic stars, she published a paper, symbiotic stars, continuously embarrassing binaries. And that was, I think, sorry, it's really unclear, 2007. And then just last year they had a conference and still, unrelated embarrassing binaries. So we really do need a lot of models. So I'm really excited to see so many people working on this in this conference. Most of the models that you'll see are done with SPH. And so this is different than the models that, for example, Bernd was showing. There you solve your equations, your fluid equations on a grid. In SPH, what we do is we take particles and we have our fluid equations, conservation of mass, dV dt, the acceleration depends on the pressure gradient and any forces, so conservation of momentum, conservation of energy, and an equation of state. We take our particles and we use this smooth particle hydrodynamics to solve these equations. Each particle has a mass, density, temperature, momentum, and they will interact via these equations. And then to get back to the particles, what we do is we interpolate between the particles to get back your smooth fluid. So this was found in the sort of 70s already and has been used really extensively. It's extremely robust. So this is why people are using it, from engineering to melting snowflakes, geophysics, even the movies. Look away if you have not seen Lord of the Rings. But all of these fluid flows here are actually done with SPH. So it's very, very robust. Sorry, poor Gollum. The method that I use is Gadget. So it's a cosmology code, but you can modify it. And we modified it to include all of the physics that we need. And as I say, it's very, very robust. It's really good for arbitrary geometries, any geometry that you would like. You don't have this fixed grid. And it conserves angular momentum, energy, and mass by construction. So it's very, very good for the problem that we want to study. All right. I have no idea of the time. There's no, super. Okay, I will speed up. Thank you. No, I'm just checking. So what we usually do is we don't model the star. I saw this fantastic Cobalt 3D models now with the companion. I'm so excited if I don't get to say that. But what we do is we just have these point mass particles which represent the gravity. So this is the gravity of the giant and the gravity of the companion. And you see them here. And then what we do is we have a boundary where we inject the mass in order to get a constant wind velocity. And so we inject it at the amount of mass and at the rate that we want. And then we have to get this mass out of the potential well. Most of these free wind models, what they do is they just assume that exactly the gravitational acceleration exactly balances the deceleration. And so you can get rid of this. And this alpha is set to 1. And then we don't resolve the companion. It's really, white dwarfs are tiny, and we don't have that kind of resolution. And so we have another boundary, an accretion boundary, where particles enter that boundary, they start to lose mass, and eventually once they get to about 1% of their mass, we remove them from the simulation, and that way we keep track of the accretion rate. So this is just a cartoon, so you can see, but yes, looks very different on my screen. And then you can render this to see what the density looks like. And so this is what the gas density would look like with brighter, denser, and you see the spirals that you get. All right, so what's happening with these is that the companion is plowing through this wind. Some of that material forms a shock around it, and you get this extended tail. These models were already run for some time in the 90s. So Alain Jarison, who you probably know from our community, they were trying to study these barium stars. And so you can see they ran some models, and they found if it's adiabatic, you don't get a disk. If it's isothermal, you do. They were trying to really understand the accretion rate, and they found that the accretion rates that they got were very similar to Bondi-Hoyle, or slightly less. And then Mastrodemus and Morris, they were trying to understand the structures that you see on larger scales. So they really did zoom out, and we can see the spirals. And they were trying to find these equatorial enhancements to try and understand the planetary nebulae, these bipolar nebulae. And you can see the close binaries here. Indeed, you can focus material in the orbital plane, whereas the wider binaries, they have a much greater extension. The interaction is not so strong, and so they have this bigger structure above and below the plane. So much more spherically symmetric. So we ran some of these models, and the main use for them, so this is a slice in the orbital plane, and this is looking perpendicular at the gas density. And we were interested in what this spiral can tell us about a companion. We applied it to several sources. And as you can imagine, the spacing between the spiral arms, so that depends on the orbital period. If you have a companion whipping around, you're going to have very, very small spacing. Similarly, if your wind velocity is very, very long, then your companion, you'll have much, much broader spacing between your spiral arms. And also we can say something about the companion, its mass, based on how dense those spiral arms are, how much focusing you can actually give to your gas in the arms. And when we run these free wind models, you do typically get something like Bondi-Hoyle rates. And there's been a lot of work on this, and you'll see a lot more of these types of models. I'm going to skip this, because I think Owen will talk a lot more about what happens when you have eccentric binaries. It can start to look a bit more like a shell, and also the modeling comparing to the observations. So one of the things I wanted to say was these spirals and arcs are often interpreted as some signature of binarity. And I really liked Theo's talk, because maybe not always, and we have to be careful. You know, you can get these arcs coming off from the shocks from models like Susanna and them's. And so, you know, can we really tell the difference between single star effects and binaries? Can single stars make shells? And I've seen some models from Shell Ericsson, actually, these carbon stars, where you can get some episodic kind of ejections. Maybe one way is the chemistry, and we had Marie and Taisa talking about that. But then also there's a complication with this UV. Is it from a binary, or is it from the chromosphere? And so I think this is something that we should try and really nail down. When can we say for sure there's a companion, and when can we say, oh, actually a single star can do it? Oh yeah, there's Owen's talk to look forward to. All right, so these simple models, so to get back to where we know for sure we have a companion, thank you. These simple models can't really explain probably one of the best studied AGB binaries that we have, and that's Myra. And no matter what wavelength you look, so this is in the ultraviolet, this is Myra A, and this is Myra B. You see that there's a very strong asymmetry towards Myra B. This is looking at the titanium oxide in the ultraviolet with HST. And then in the X-ray, this is Myra A and this is Myra B, and you see this bridge-like structure between the two stars. Similarly, this is some older infrared data, and you can see this extension towards Myra B in this dusty extension extending away from Myra A. And this is surprising because we know that Myra B is a white dwarf, but it's at least 60 AU away, as Theo said. It's a very, very wide orbit. So to have such a strong interaction is a bit puzzling. And this is what inspired us. So we tried to understand, well, is this wind accretion that's happening? What's happening in Myra? It should be wind accretion. It's a wide binary, right? But it's very, very strongly interacting. And if you look, it looks so much like Roche-Lobe overflow. Like it's no-brainer. If I had to choose, I'd say definitely Roche-Lobe overflow. But of course, if you look at, we talked about the Roche-Lobe radius. If you calculate what the Roche-Lobe radius is for such a separation, then it's going to be at least 30 AU. There's no way that our AGB star, as big as they get, is going to get to 30 AU. So the star itself is not filling the Roche-Lobe. We are certain of that for this case. And so what we proposed is that you have a sort of combination of the two, which we call wind Roche-Lobe overflow, or case D mass transfer. And we said, in the case of Myra, it has a very low wind velocity, and that slow wind can actually fill the Roche-Lobe and get accreted onto the companion, and so look like Roche-Lobe overflow. And then we generalized this and said, actually, if you have an acceleration region close to the Roche-Lobe surface, your wind is going to be moving very slowly, and so you are going to be able to fill your star's Roche-Lobe up with dense material and then get it transferred through the L point. So that's the sort of idea. And so it really depends on where this acceleration region is, whether it's dust, or I'll talk about the hot stars for high mass X-ray binaries, but it depends where this acceleration region is relative to the Roche-Lobe surface. If it's close, then you'll get something that looks like Roche-Lobe overflow. If it's far and your wind is happily sailing away by the time it gets to the Roche-Lobe surface, then it's going to look something much more like Bondi-Hoyle Littleton accretion. And so those are the two sort of scenarios. And so we modeled this. Now we got rid of our alpha. We have a simple prescription for pulsations. And you can see here an eccentric binary. We have a pulsating AGB star here and a white dwarf companion. And you can see the material leaves the giant, gets transferred to the companion. Some of it gets accreted via an accretion disk, but some of it gets flung out in these spiral arms that you see here. And those spiral arms are really flattened towards the orbital plane. So you get a lot of focusing towards the orbital plane in this case. And if we now switch to that was quite a close binary, a wide binary now, and look at the gas density and go into the co-rotating frame. So we rotate with the binary, and so our stars will be stationary, and you can sort of see the Roche-Lobe surfaces there. What you see is that indeed this is gas density, dense gas filling the Roche-Lobe and getting transferred to the companion, and some of it coming out in these spiral arms. We made an estimate of what the dust opacity would look like, and what you find is that you have this big cavity here, you have dusty arcs that form, dusty spirals, dust in the tail, so you have a lot of structure, some dust near the companion, some dust not, so you get much more complex structure than the simple spirals that we see. And indeed, even for very wide binaries, this is 20 AU separation, When you look perpendicular to the orbital plane, you see that you can get those flattened equatorial outflows that we need for the bipolar planetary nebulae. So the focusing, as you channel material through the L1 point, can help with this kind of morphology. And this is just looking at the dusty structures and the cavities and what it looks perpendicular. So you can get very complex structures for these systems. Thanks to Sophia, we had amazing ALMA data, and so we could actually compare some of the models with what we see with ALMA for Myra. And you can see a lot of the features. So the Myra A is here. This is Myra B. This is these archy structures we see, I think, here as well as these extensions. So a lot of the features that we see in the simulations, we actually can see in the ALMA data. I'm excited to compare more with the inner part that Theo was showing. On a larger scale, not so much, but we expect that because here's Myra A and Myra B, and we see this big, when you look at the blue shifted emission, you see this big hole, and we think that's the effect of the companion destroying the CO, and so this is something like that Maria and them were talking about, and so yeah, that we don't see in our simulations. Some other observations, I think it fits quite well, and there's a lot of nice similarities in the different features. So I think this gives us some credence that windrow slope overflow is good. We were interested in what happens with substellar companions. I'm probably not going to have a lot of time to talk about this. Basically, we have, so when you have the pulsations, the companion can have a resonance with these pulsations. And so you can get multiple spirals or none. So you can ask me about this later. But the point I wanted to make was, even if you have a 40 Jupiter mass companion, so this is a really small, itty-bitty brown dwarf type companion, your mass loss rate, so this is mass loss rate versus time, for different companion masses, there's 5 Jupiter masses in black to 40 Jupiter masses here in red. And what you see is you get a factor of 2 higher mass loss rate with an itty-bitty, tiny little companion. And we think that a lot of these, most of our stars will have planetary substellar companions. And so this will really have a big impact on yields, on lifetimes, if you have these companions orbiting around. I didn't have a chance to talk about accretion. We form accretion disks. You get really high mass transfer rates. I'm going to take 1 more minute. Really high mass transfer rates. So you can see this is the mass transfer fraction versus orbital period. This is Bondi-Hoyle that we get from Bondi-Hoyle. And here you see just where we needed them for those barium stars and S process, we get this higher, much higher, even as much as 50% of the material transferred. Windrow slope overflow has been applied to so many different population synthesis now. It's showing promise for explaining some of these type 1a parameter regions. It's been used to explain, the SEM stars. Even applied, and I say this because Ilya is here, applied to high mass X-ray binaries. So the idea that we learned some physics from the AGB stars, a mass transfer mode, and now we're applying it across the board to a lot of different fields, I think is quite exciting. And so this is windrow slope overflows being used to explain ultraluminous X-ray binaries. So that's quite exciting. And I'll leave with my conclusions. Apologies for going over. Thank you.
Thanks, Shazet, for this very nice talk where we don't have much time. Well, maybe Ilek. Yeah.
Thank you, Shazarine, for the great talk. I had a question concerning the circumbinary disk that you mentioned at the very beginning. In most simulations, it's pretty rare to see it, and so its formation really depends on like the capacity of the flow to cool down, the whole thermodynamics. And because we have all these astrochemistry people in the room, I mean, now it makes sense to really include their insights in these simulations. But are we at the stage that we can predict the conditions of formation of this circumbinary disk? For instance, is the eccentricity, what's going to be the upper eccentricity, which prohibits the formation of this stable disk in a system like W Aquila, for instance?
Yeah, so I think there's been two groups simulating this. So the Guillermo and them's group in Ensenada, and another group, I'm not sure where they are now, I think in China. But basically they got completely opposite. So one group says, yes, we find a circumbinary disk, and the other says no. And I think the numerics is still coming. We need more physics, but I think also some of the numerical issues. They were both grid codes, so yay, SPH. We see how it goes. So yeah, maybe it has to do with the angular momentum conservation, but at the moment it's still an open question, like how do we really form these things? I think there's a danger that people talk about circumbinary disk when they mean equatorial outflows. I think equatorial outflows we can do. Windrow slope overflow, even if you have a slow wind, you can still focus material and you can get the conditions you need for planetary nebulae. But these proper, genuine Hans disks, yeah, those ones are hard. And I don't think we have a way to do it yet.
Okay, thank you. Well, I'm sorry, we have to move to the next speaker. Let's thank Shazrin again for the nice talk. So the next speaker is Camille Landry, who's going to talk about 3D hydrochemical simulations with MACE and Phantom.
Okay, yes. Okay, hello everyone. I'm Camille Landry. I'm a postdoc at KU Leuven. And well, my thing is more binary stars. Like everything Shazrin said, that's my jam. But today I will switch my focus a little bit to talk about chemistry and 3D hydrodynamics. It's a project that is a work in progress, so I'm going to make a lot of promises and not show a lot of results. But for the next YAGB, YAGB 6, I'll show you the results, hopefully. Or maybe not. Oh, that. All right. No, but I think it worked. No. Is it off? It is off. Okay, good. All right, so Marie talked quite a lot about astrochemistry, so I don't have to introduce it to you all. I will just remind you in general what it looks like for AGB outflow specifically. But basically, we have molecular reactions that impact the dynamics of the outflow themselves, dust formation, of course, that depend on molecular abundances, molecular heating, cooling, photochemistry on the outskirts of the outflow. So overall chemistry is quite tightly bound with the hydrodynamics of the outflow. On top of that, if we want to create synthetic observables from our simulations, we also need accurate chemical yields. Thaisa talked about the tracers of binarity with chemistry as well. So if we want to reproduce these nice ALMA observations that we have, we do need chemistry. So the goal of this project is to improve our 3D models by adding chemistry in sort of different ways. Now, the classical way of doing astrochemistry is just to directly solve the chemical kinetics under the condition of the stellar outflow we're considering. If we consider only 1 and 2 body reactions, that means photodissociation and photoionization, and then 2 body reactions that are controlled by temperature, basically. We get this set of ODE. So as ends, we have number densities. So that means we have as many equations as we have chemical species in our network. And K's are reaction rates. So we have as many terms in these equations as we have reactions. So you can probably already see how the problem scales up with the complexity. And that's one of the main issues of chemical kinetics. This set of ODE that I just showed you is what we call numerically stiff. That means that it can be unstable fairly fast if we don't control the time step in particular. There are some reactions that have very short timescales that need to be resolved well. And so it means that we need to solve it a lot more times than if it was not stiff, basically. The parameter space of stellar outflows also, as Marie said yesterday, ranges over very large scales of temperature, density, and so on. So that means that we also need to sample this parameter space well enough, and so that increases the cost of our simulation. So overall, astrochemistry for AGB wind specifically is very expensive to run. And for now, it's only been done in 1D, for example, by Marie and Silke Mace as well. But I don't need to convince you all here that AGB outflows are not symmetric. I think we know that. So we do really need to solve the chemistry in 3D. Now, we can already do astrochemistry in 3D. There are chemical kinetic solvers that are made to be portable enough to run with any hydro simulations you have. I think the more common one is called Chrome. And we can run it with our code Phantom, for example, already. The coupling exists. The problem is the cost. We need to evolve the set of ODE I just showed you for every fluid element at each time step. So, for example, in a good Phantom simulations, we have millions of particles. And to give you numbers, when we run Chrome on Phantom models, it takes about more than 0.1 second per particle per time step. That's a lot more than the hydrodynamical time, the time we need to solve the hydrodynamical time step. So this increases drastically the cost of the simulation. And on top of that, we have a massive memory usage because we need to store all the chemical abundances for all species for each fluid element. So that means our output files are massive, but also the memory usage while we run the code is gigantic. So the idea of this project is to actually step away from classical solvers and instead use machine learning to build chemistry emulators, which is what Silke Mace did for part of her PhD. And she built this emulator called MACE, which I now need to tell you how amazing it is. Hello, yes. So MACE is a set of neural network that has been trained to reproduce a chemical network of 468 species and more than 6,000 reactions. These were chosen very carefully by Marie and Silke to fit AGB outflows. And it uses these chemical abundances, so 468 abundances, and 4 physical parameters as input, density, temperature, and 2 radiation parameters. It then encodes this set of parameters to reduce the dimensionality of a problem. So we go from 472 parameters to 8. And then MACE evolves a set of ODE equations that have the form of the chemistry network with trainable coefficients here. And it evolves these 8 parameters over 1 time step and then decodes these parameters to predict the new molecular abundances after 1 time step. When Silke created these models, she trained them on data from 1D AGB outflows. And here you have an example where, I don't know if we see very well, but the dashed lines are the classical results and the full lines on top are the MACE predictions. So MACE is actually very good. And for these 1D outflow, they found that the solver is actually, the emulator is 25 times faster than the solver, so that's already quite an improvement. The architecture of the whole model is flexible, so that means we can adapt it to any other astrochemical environment, which I'd like to underline, yes, thank you. Because then if any of you is interested to do this for any other type of objects, we surely can. But most importantly, the ODE solver allows to run on variable time step. So that means we can couple this to a 3D hydrodynamic code to solve chemistry with the hydro time step. And this is my job. So first, I'm training MACE as a post-processing tool. So for now, it's trained on Phantom runs that have been post-processed by Chrome. So here is an example of a snapshot of Phantom. So we track the particle evolution inside. So we have all of these. We don't see very well, but Shazreen showed how SPH works. So we have all of these particles that we track the evolution of, and we calculate the chemistry on them from Chrome. So here you see the result. It's not very different from the plot I showed the slides before because it's the same chemical network. And then we train MACE with the Chrome results, and it gives the same results. So all good, the training has passed. We can now use it on any other AGB model that only contains a single star, because for now I'm only doing single stars, and that has physical parameters that are not too far from what MACE was trained on. So here is an example of what MACE did with a couple of different abundances that are more or less relevant. And well, that's not very impressive because Chrome can do this already. So like you may ask, why am I doing this? But Chrome is doing this in 0.25 second per particle per time step. MACE is doing it in 5 × 10⁻⁴ seconds. So there's a 500 speed up there, which means that if we have grids of hydrodynamic models, we can post-process with MACE at speeds that were unachievable before. Of course, the next step is to do this on binary stars because single stars are a bit boring to me. So we want to do this with binaries. And then we will post-process all of this with our radiative transfer called Magritte and hopefully create some nice synthetic spectra to compare with ALMA data, for example. So for the long-term evolution of MACE, I plan to put it in Phantom and actually solve it within the hydrodynamical time step. So thanks to Shazreen, I don't have to introduce you to SPH, but this is what Phantom solves at every time step, basically. And what we want to do is to evolve chemistry in latent space by having the 468 abundances and then the physical parameters for each particle. And then once this is calculated, we can feed it back as mostly a new mean molecular weight, but also if we're considering molecular cooling, then we have new abundances to calculate these cooling rates. And if we have dust formation, then we also have new molecular abundances for that. So really the improvements are endless. And this, of course, will improve the wind setup that we use, so that Lionel made and that we have improved on over the years between KU Leuven and ULB. So you will see my colleagues, Davide and Owen, will talk about their own models, but this is one of the planned improvement for our Phantom models. So I will leave you with my conclusions, but I would like to really highlight that MACE should be able to do any other astrochemical environments, provided that we train it well. So a lot of application there, and if you have any interest in this at all, it's open source, it's on GitHub. And we have a little training program with the Dirac Center in the UK where we made little, very small notebook and lectures on how to use MACE, how the architecture is built. So you just need to make an account on the Dirac training webpage, and then you can access all our knowledge on the matter. Thank you for your attention, and I'll take any questions.
So we have, thanks for keeping the time. So we have time for questions. Well, I may have one, well, as usual.
Yeah, sure.
How many latent species will you keep in the end?
That depends. So this is part of the hyperparameters of the model, and we can change that. For now, actually, I showed 8. That's the basic 1D model, but I'm using 16 because it, for some reason, trains better and it is faster. So for now, I'm using 16, but this is always something we need to explore every time we make a new MACE model. So unsure.
And what will be the complication when you include the binary?
Shocks. I'm not looking forward to it, but yeah. The main complication will be when I design the training set to make sure that we take into account the right physical conditions for the shocks.
Thank you. Are there any other questions?
Hi, thank you for a really nice talk. I was just wondering if there is any dust gas chemistry that will be included in this? Because that must surely open another door.
Yes, and if I were to do that, I would steal Marie's work. So I will not. It's like, it would be a nice extension once all of this is done. But we have, like, not right now.
Any other question from the audience? No? So if no, let's thank Camille again. Thank you. And so the next talk is by Davide Dionese on 3D hydrodynamical models of AGB winds, the impact of a companion on dust formation.
Now it works. Very nice. Yeah, hi everyone, I'm Davide and I'm a PhD student in Brussels working with Lionel. And I'm also collaborating with Dorota Skowron, who is based in University of Warsaw. And today I will be talking about 3D HD models of AGB winds. And in particular, I will focus on what is the impact of a companion on the formation of dust. Now, why am I interested into AGB binaries and dust? Well, because at the core of my PhD, there is the LSP. We have heard about LSP so many times during this conference. So I will actually be super quick about the introduction of LSPs. I guess by now everyone is quite familiar with it. One thing that I want to focus on, that I would like to underline, is one thing that I think has not been discussed yet about LSP, and I think it's quite peculiar and quite interesting for me. So if you look at the figure in this slide, here on the right-hand side, this is a light curve of an AGB displaying indeed LSPs. So the smaller wiggles that we observe correspond to the primary period, which is supposedly connected to pulsations, and then the larger oscillations are the LSPs. And what we often see in these light curves is that the LSP is not symmetric, but the oscillation luminosity shows this quick drop in luminosity and then a slower rise back to full luminosity. And this is really, really often observed in LSPs. And as you might guess, we already mentioned a lot during this week that we don't know what LSPs are caused by. And of course, my hypothesis is the binary one. Now we have seen this image, I think, already 5 times during this week. So I will not repeat what the binary hypothesis is about. And also the secondary eclipses in the infrared, we're already familiar with it. Instead, I will take a quick journey about all the LSPs mentions that they got this week. So we started by some people that are extremely bothered by the presence of LSPs in their observations. And then we have seen people explaining us how LSPs are connected to pulsations mode that we observe in AGBs. And then we have seen people trying to connect LSPs, or like mentioning connection between LSPs and the furthest possible phenomena in AGBs. And then we have seen the absence of LSPs in places that we could have expected LSP in. And I didn't include here the talk from Steve, because it was only 1 hour ago and I didn't have time to do it. But yeah, there was another mention to LSPs. And we have also seen people trying to suggest what could be the origin, or at least what could not be needed, which is indeed binaries, as Ben suggested yesterday. But as both Michele and Ben yesterday, and also Steve less than an hour ago mentioned, it could be more than one reason. So we're not sure, but there could be many things playing a relevant role here. So for this reason, I still think it's definitely worth it to try and explore the binary hypothesis and to test through my models whether a binary system could be able to explain some of potentially all of the properties of LSPs. So my setup is already been discussed actually widely, and thanks to Shazrin for introducing SPH and for introducing free wind and basically all the things that we are using. And since I'm using Lionel's setup, it's once again also similar to what Thais already described in her talk this afternoon. So yeah, indeed, we include the AGB, we include the free wind, we include the companion, and on top of the free wind, we also have radiation pressure exerted on the dust that eventually will form. And what we want to study with these models is the interaction between the AGB wind with the companion. We want to follow the mass accretion onto the companion, and then we also want to include dust in our models because we're really interested into the eclipses that could eventually explain LSPs. Okay, probably the major update that I made to the Phantom code is new cooling rates. Now, cooling are super important for us because we want to form dust, so we need the gas to cool down. I introduced new radiative coolings that I took from the, or adapted from the work of Glover 2012. And the species that I included are the ones shown in the table here. And of course, in order to compute radiative cooling, I need abundances. And in our models, we are using a small chemical network to derive abundances. So in the plot in the top, I'm showing what are the abundances of some key species in our models for a certain range of temperatures. And on the bottom plot, I'm showing what are the corresponding cooling rates for the same range of temperatures. So if you look at the bottom image, on the right, we see a dashed dotted line. And that corresponds to the H1 cooling rate that was already implemented before. And all the other cooling rates that we observe are the new coolings that I introduced. So as you can see, before we were only able to cool down the gas up to a few thousand Kelvin, and now we're able really to go lower temperatures where dust can actually form. Here is an overview of which are the most important cooling rates for a certain set of densities on the x-axis and temperature on the y-axis. I'm comparing it to the work of Wojtke, 1996. And although we are missing some of the cooling rates and some of the species in our network, we do find some good agreement. So we have HU vibrational rotational cooling and CO rotational cooling at lower temperature, CO vibrational atomic oxygen, and then finally atomic hydrogen cooling at higher temperatures. As I mentioned, we already include dust formation. So we create dust through a two-step process. We actually follow the formalism of Guile, which I think has already been mentioned this week earlier on. So first of all, we form the by now famous seeds. And seeds contain between 100 and 1,000 atoms, and the nucleation rate of these seeds depends on the abundance of the monomers forming them. And then once we have the nuclei, we can proceed to make them grow, and we account for these 4 species, so C, C2, C2H, and C2H2. First of all, I ran a model of a single AGB star. Thank you. And then here we are seeing what is the effect of the new cooling on the temperature on the top plot. So in red, we are seeing the temperature profile. So it's a single AGB star, so spherically symmetric winds. And the gas is cooling just due to adiabatic expansion, whereas in blue, we are seeing the temperature dropping much quicker thanks to the new coolings. And this has an important effect. For example, on the bottom plot, I'm showing the average grain size, and we can see that when we introduce cooling, we are able to form larger grains closer to the star. And then we can move on to full binary models. So yeah, once again, the setup has already been explained. The AGB is here in the dark spot, and the companion is here in the location at the tip of the spiral. And the top plot, I'm showing density, so we can see the formation of a nice spiral with higher density within the spiral. And at the bottom, I'm showing temperature. And so we can see that the temperature within the spiral is much, much lower. And then we have the formation of these sorts of 2 high temperature wings that correspond to where the gas in the spiral is shocking, creating shocks against the rest of the outflow. And if we look at the dust, so here I'm plotting the dust to gas ratio, so we can really follow the formation of dust. And we can see that it's really, really limited within the spiral originated by the companion, which is something that we already saw in Thais' models. Now, on the right-hand side here, I'm showing the same three images as before. Something I didn't mention, but similar to Chazrin's images, these are all slices through the orbital plane. So on the right-hand side is the same model as before. On the left-hand side now, it's the same setup, so same masses, but I didn't include the cooling. So as we can see in the temperature, for example, in this plot, the gas is not able to cool down, so the temperature remains very high, and the production of dust is much, much lower now. Also, the colors is, like the color map is about 2 orders of magnitude lower, so dust production is really less. And on top of dust production, I also included dust evaporation. So here I'm taking a zoom in around the companion. So the companion is in this dark spot in the middle of the accretion disk. On the left-hand side is the gas density, on the right-hand side is the dust density. But if you look at the temperature, now the temperature within the disk is very, very low. But closer to the companion where accretion is ongoing, now the temperature rises a lot. So we need to be able to evaporate dust there. So if you take a look at the dust to gas ratio, now we don't have dust in the center where the companion is. I also played a bit with mass ranges. So this is the same model as before, but the companion mass is now 0.1. So around the companion of brown dwarf, which is also around the masses that we need, that we observe. I mean, that we would need if LSPs would be caused by binaries. And as you can see now, the density structure is much, much different. The spiral is much narrower than earlier. And if you look at the dust to gas ratio on the right-hand side, once again, dust formation is limited within the spiral, and the scale is going to be different, so the production of dust is once again limited. And finally, an overview of the total dust produced in my system. So these are 4 different models, and in orange, I'm showing the total dust mass within models. And the first one corresponds to a single AGB model. And then going towards the right, we increase the mass of the companion to 0.1, 0.5, and finally 1 solar mass. And what we observe is that when we introduce a companion and we increase the mass of the companion, we're really able to form more and more dust within our systems. And this leads me to my conclusions. So I included new radiative cooling in our simulations, phantom simulations, enabling efficient dust formation. I ran first fully coupled 3D models, including both dust cooling, gas cooling, dust formation, and evaporation. And I have shown how the presence of the companion can really, really alter the amount of dust produced and also the spatial distribution of this dust. And the natural future steps that we want to take is to run some radiative transfer onto our outputs to possibly get some synthetic images and also eventually test the binary origin of LSPs. Thank you all for your attention.
Thank you, Davide, for this very nice talk. So we have time for questions. Hans?
Thanks for the nice talk. I have a question with respect to your first question, namely, how will this induce an a long period variable or so the secondary period? So what is the link between having a spiral with dust and the long secondary period?
So, well, this goes back to the binary hypothesis. And it's simply, the thing is, if we look at the top, the image top right, which is, of course, an artistic image, but the idea is that you have your dust cloud with very high density. And then whenever it's an eclipsing binary, or not really eclipse, like it's not necessarily that the companion is eclipsing but the dust cloud can be eclipsing it. And this is also was shown by Len in her last letter a month ago, that you don't really need the companion, but it's just a spiral needs to be passed in front of part of the stellar disk. And then you have, of course, also, I think also why it's nice, very important, the secondary eclipse that's coming from the emission of dust when the dust cloud is going behind the primary, and also the shape of the light curves. So you have a quick drop, which is when the dust cloud is getting in front, and then you have a spiral with decreasing optical depth, let's say, and this creates the slower rise back to full luminosity.
Thank you for this very interesting talk. So, did I read correctly that for the wind you use 10 kilometers per second, and was it 10 to the -5 solar masses per year? Is that right?
That's very possible, yes.
Okay, so I was thinking this that's the total mass loss rate of the wind, right?
So these are the initial conditions of our models. So it's what's happening basically close to the star where we inject the wind, right? So the wind velocity that I wrote down is the injection velocity. So where we inject the wind, it has, and then it gets accelerated eventually due to radiation pressure. And the mass loss rate is also given by how much wind we inject, right?
So they're the condition near the star, right?
Yes.
So my question is, this to me that sounds like a mass loss rate typical of a relatively evolved late stage mirror-like variable, where observationally it seems that long secondary periods appear for stars that are losing mass at a lower rate, like a couple order of magnitudes lower. So do you plan to explore also that regime that some, well, assuming the measurements are correct, should be more closer to the where we expect long secondary periods?
Yes, 100%. I want to explore different ranges for all the parameters. Also, the masses that I was showing in most of the models, the companion is 1 solar mass, which is indeed not what we're going to observe in LSPs. So this is more about dust, companion-induced dust production. So this was more about like how a companion can influence the dust production. Indeed, with this model, eventually we want to be able to try and simulate LSPs, but it's later on.
Okay, well, let's thanks Davide again. And move to the last speaker of today's session. So it's Owen Vermeulen, who's going to talk about the impact of a binary companion in AGB outflows on CO spectral lines.
Hello, yes. Hello, so I'm Owen. I'm a second-year PhD student from KU Leuven. Now I'll be talking about how a binary companion can influence the CO lines that we can observe from these outflows. So first, very briefly, the problem that I'm trying to address. Now that we have these very nice high-resolution images of these outflows, we know that these can exhibit these large-scale complexities as well. However, if we are modeling, for example, the mass loss rates, very often we are using low JCO spectral lines, and almost always these are being modeled under the assumption of a spherically symmetric single-star system. Now, this might not always be a terrible assumption, but we also know that there exist CO lines that show behavior that are simply incompatible with these simpler models. And I show some examples here on the slide, chosen such that these differences are, of course, the largest. The problem here then is that, well, maybe the mass loss rate that we derive might be then incorrect. And so I aim to work towards modeling these lines using 3D hydro simulations. So just like the previous two presentations, I'm also using the 3D smoothed particle hydro code Phantom. And so we have the setup of a mass-losing AGB star, again using the free wind that Jazreen already described. So we are not using yet any detailed dust nucleation or radiation pressure, but just injecting these particles into our simulation. And we combine them with a stellar companion because we are interested in a binary system. Now, to be able to create some different looking morphologies, I created a grid of 9 different models where we always fix the primary and secondary mass to 1.5 and 1 solar mass respectively. And then we change the orbital separation between 9, 15, and 25 AU, and the initial outflow velocities between 5, 10, and 20 kilometers per second. For simplicity, for now, I've only worked for circular models, so an eccentricity of 0, with also a constant mass loss rate, which is relatively low at 10 to the -7 solar masses per year. Also, one side note is that I've only included H1 cooling, so all of these fancy cooling routines that Davide was just describing, I have not yet included, but that's for later. So with this, we can have a look at what our simulations look like. So here I show first the models with an initial outflow velocity of 10 kilometers per second. And so on top, I always show a slice through the orbital plane, so the face-on view, and on the bottom, a slice through the meridional plane, so the edge-on view. And then the 3 different columns are the 3 different orbital separations. So first of all, we see always this very broad spiral structure arising in the face-on view for these models, regardless basically of the orbital separation. Whilst in the edge-on view, we see some more variety occur. At the lowest separation, we have these flattened arcs. I should also note that these slices are quite zoomed in. The full models are actually out to a few thousand of AU, such that the envelope size is somewhat consistent with also the 1D models that we're using. And so these flattened arcs are also what Shazrin described. Our global model is also more oblate, so flattened globally. This is not the case at the higher separations where we have more triangular looking arcs. And so these models do not have this global flattening. Also very briefly then, the lower initial outflow velocity of 5 kilometers per second, where we again have this very broad spiral structure in the face-on view, again, regardless of the orbital separation. And in the edge-on view, all these models have these flattened arcs. And so all of these models are also, again, globally flattened. Lastly, for the highest initial outflow velocity of 20 kilometers per second, where we also expect the smallest impact of this binary companion, we see that now the spiral structure is significantly more narrow. And in the edge-on view, we also have these more narrow arcs. And so these global morphologies are more or less spherical. With this, we can then start generating our CO lines. But before we start with the binary case, we first have to look at what actually a single star case looks like. So here I show a single star simulation where nothing really interesting is happening. It's just a spherical outflow. And then the resulting spectral line, which is created using Magritte, a 3D line radiative transfer code developed at KU Leuven. We generate the corresponding to the one CO line, which in this case is a simple flat top line profile, which is also what you would expect from an optically thin spherical outflow. And now we can then compare what our binary models look like. So here I always show the 2-to-1 line, starting for the V5 models. In the top row, I always show the face-on view, so at an inclination of 0 degrees. So this is looking directly on top of the spiral. And then the edge-on view is an inclination of 90 degrees, which I show in the bottom row. And the 3 different line styles, being the solid dashed and dotted line, correspond to the 3 different orbital separations of 9, 15, and 25 AU, respectively. And the first thing we can notice is that these line profiles, are no longer the simple flat-topped line profile that we would expect from a single star. But instead, in the face-on view, we always see these strong double peaks occur. And this is because this binary companion essentially levitates some material on top and below of the orbital plane. And so if we look from the top down, we have 2 distinct contributions at 2 distinct velocities, which give rise to these 2 peaks. And also noteworthy is that these lines are looking very similar for the 3 different models, which makes sense given how similar also these models look like. In the edge-on view instead, we see this strong central bump feature occurring on top of a more wider profile, which is essentially the same material, but which is now residing at at the central velocity. Then for the V10 models, we again see these strong double peaks occur in the face-on view. However, now we see some more variety in the width of the line. And again, we have this strong central bump feature. However, if we look at the largest separation, we see that this line profile is almost perfectly parabolic. So this is already showing that although our model showed a very strong impact in the density structure, when we're only looking at the CO line, this can go very easily unnoticed. Finally, for the V20 models, we immediately see that the deviations from this flat line profile are significantly smaller, especially when we look at the edge-on view, where they're basically almost perfectly flat-topped. Should also notice that here no instrumental effects have yet been taken into account. So if we start including some noise, these become completely, indistinguishable from these single star models that we previously looked at. Now, I would also like to take a look at what happens if we actually start looking at higher CO transitions, because looking at the 2-to-1 line is essentially probing the global structure. And so if we start looking at higher transitions, this is typically probing hotter regions, so more inner regions. So here on top, I show the 2-to-1 line that we showed on the...
Owen, sorry for interrupting you. Can you wait a second, because online they lost the sound.
Okay.
Because on the side it's okay. So if the person can confirm.
Can somebody online also confirm that it's not only Alan who lost the sound? Sorry, Owen. Well, anyway, we are recording, so please go ahead.
Okay. So what I was saying is on top, we have the 2-to-1 line that I showed on the previous slide. And on the bottom, we have then the 6-to-5 line. And this is for the model with an initial outflow velocity of 5 kilometers per second viewed face on. Yes. And the main thing I want to show here is that actually our line profiles for these models look very similar regardless of the CO transition, except for maybe these double peaks that have been somehow merged for this larger separation where we now have this more slight asymmetric feature. However, more interestingly, if we look at the V20 models that and viewing Edge-on, which I previously noted were very similar to this flat top line profile, if we go to a high transition, we again see very strong features occurring in this line profile. So how can we explain this? Now, if we take a look at the temperature distribution of these models, so on the left, I have the V5A9 model, whose line profile remains almost identical when going to a high transition. We also see that this temperature distribution is more or less smooth. And so if you go to hotter regions, you're essentially probing the same morphology, but just at a smaller scale. However, on the right, I have the V20 model at a larger separation. And here we clearly see that, is it going away? Well, anyway, you very clearly see that this temperature distribution is very strongly dominated by the spiral structure. This means that if we change from a very low transition to a high transition, we're also making a switch from probing the more or less spherical outflow to directly probing this strong spiral structure, thereby also creating then these stronger features in the line profiles. Okay, so with that, I can already make some conclusions. First of all, is that indeed including a binary companion in this modeling procedure can very strongly alter our CO line profiles. And then any observable feature could thus serve as an indirect evidence for binarity, with, of course, a very strong caveat that they can also very easily go unnoticed, especially when we start including any instrumental effects. Now, if you're interested in a far more in-depth discussion about all of these lines, I recommend you to look at the paper. For now, future work-wise, we're very strongly working on improving the physics of our simulations, thereby also making any synthetic observable far more realistic. So we've previously already seen David and Camille talk about dust nucleation and chemistry, but we're also talking about improving the radiation treatment in our simulations and also including pulsations. And I'd like to end this presentation by already showing an initial result of these pulsations. And actually within our group, we have developed two different setups of these same simulations. On the left, we have the SPH code Phantom, which I've been working on. And on the right, we have the same implementation, but in a grid-based code called MPI AMR-VAC, which has been developed by Florian Driessen. So here we already see that on the left, on the SPH, we again see this spiral arm occurring, which is similar to the Freeman models. However, we have an additional layer of complexity as this spiral arm is now also combined with the shocks that are due to these pulsations. And we see the same spiral arm also occurring in the AMR code. So it is very promising to see that these two very different approaches to modeling these same systems give such similar results. And with that, I'd like to thank you all for listening.
Thank you, Owen, for this very nice talk, and sorry for the disruptions. So we have time for questions. Are there any questions? Yes.
Yes, thank you for the talk. Sorry if you mentioned this, but in your slow velocity winds line profiles, you get an asymmetry between the two peaks. Is that relatively constant with all of your models, and where does that arise from?
So that arises due to an optical depth effect, because this region that is, creating these double peaks, you're looking at it from the different sides, because one, you're looking from top, but the other one you probe from the bottom. So you get a slightly different contribution from these two different regions. You also actually see it because if you go to the 1 to 0 line, it's more optically thin. and the peaks become more equal, and towards higher transitions, they become more asymmetric due to this optical depth.
So kind of following up on this, so then would it be, if you would observe an isotopolog of CO, like 13 CO, and you would see strong asymmetries in CO, but not in the isotopolog, would that be a way to potentially then pinpoint that these things are actually happening, or?
That could be the case, and it's also possible to do it with my grid. I just haven't done it yet, looking at 13 CO. But that's definitely an interesting thing for the future.
Any other questions? Well, might I have one? What would be the impact of this line asymmetry on the determination of the mass loss rate?
Of purely the line asymmetry of?
Yeah, when you use CO to determine the mass loss rate.
It's quite difficult to predict that, I think, at this moment, because the models are still quite far from being ready to really use for mass loss rate estimates. I think the only way of figuring it out is to apply the method directly.
Yes, just a quick follow-up on that. If you would shove whatever lines you get out into the basic estimators that are around, what do you get and how far off are you? Because that would be very relevant.
That I have done.
Very good.
And it should be in my extra slides somewhere, I hope. Yes?
You're very welcome.
So I just use like a very simple fitting procedure on these lines. And then you see, so the dashed line is the input mass loss rate. And then for the two inclinations, I derive it using this formula. And so I'm off by at most a factor of 2 typically, with one very big caveat. And if I apply it on a single star system, I'm also off by a factor of 2 actually, which is probably due to, well, first of all, the scatter of this formula, I think, and secondly, also the temperature distribution in these models are quite off because we haven't yet included detailed cooling. But so it's quite not as big as you would think, I think.
But that will be very much dependent on the mass loss rate. This is what we feel in general. So we are better off when we go to higher mass loss rates.
Okay, so let's thanks Owen again and all our speakers of this afternoon. So I don't know, Claudia, if there are any announcements.
Yes, so I spammed you everywhere, like on Slack and via email with the address of the restaurant because I realized you didn't have it before. So it's just to spam even more. It's at the end of the park, Bicentenario, here, which is next up, but it's not the direction of the city. It's in the other direction. Please be there at 7:30. And inform we will start at 7:30 and inform the people that will serve you about your allergies. For the moment, I think we have 16 vegetarians and 2 allergic to nuts. I think that's all. Thanks a lot.
On another note, these glasses were found. So if somebody lost some glasses, yeah.
Vieni con me adesso. It would be better if, sorry. You can stay here a little longer, but not until 7:30. So I would say at 6, leave. Sorry. But there is a nice park and it's beautiful weather.